So good morning, everybody, and welcome to the second day of our session on rates and dates, magmatic and volcanic processes from source to surface. We have 8 talks this morning, and the first one is by Chiara Petrone on a critical assessment of pressure estimates in volcanic plumbing systems, the case study of Popocatépetl volcano, Mexico.
Great. Restart. So good morning, everybody, and thank you for making so early. I'm going to talk about this work that we published a few months ago on LITOS, looking at the clinopyroxene liquid barometer and a reassessment, in particular on looking at the study of the Popocatépetl volcano. Okay. So first of all, why reassessing the clinopyroxene liquid barometer? I suppose that most of us have been quite frustrated when trying to apply a barometer to magmatic system, particularly in arc location, because most of the barometers are unable to really discriminate the pressure. And the reason is because, well, or at least we think, is because most barometers use the chemical composition of the mineral and the host melt, and they completely ignore some structural parameter like the cell and site volume, despite their known dependency on the pressure. So in this case, we reassessed the usage of 2 well-known CPX liquid barometer, the Niven-Putirka, which is based on chemical data, and the NIMIS 1999 based on crystal structure. They've been both used in combination with the geothermometer of Putirka 2008, in particular the equation 33. Okay, so the case studies Popocatépetl, a big stratovolcano in central Mexico. I'm not going into the detail of Popo, but just to let you know that there are 3, we kind of recognize 3 different types of clinopyroxene. The first one, the first population reported here in red, the T1 core that we think is crystallizing in the shallow part of the system here. The second population in T2 reported in blue, which on the petrological basis we infer is crystallizing in the intermediate portion of the transcrustal plumbing system. And finally, the third population reported in green a low calcium clinopyroxene that on petrological basis we infer is crystallizing in the deeper portion of the plumbing system from a more mafic magma. Okay, so what we did, we physically extracted some portion of the different type of clinopyroxene, and using a single X-ray crystal diffraction, we did a structural refinement to determine some of the structural parameters, in particular the volume of the cell. And I just remind you that the unit cell of a mineral is the smallest divisible unit of the mineral that possesses the symmetry, so we can determine the volume. And we also can determine the volume of the structural site, like in the case of the pyroxene, the M1 and the M2 site, crystallographic site, which clearly they already they have different size, and they can host because they can host different elements, but also the size of the M1 and M2 can change depending on the crystallization condition. And with the structural refinement, we can really assess which elements are hosted in each of these crystallographic sites, as we can see here, looking at the crystal size occupancy. In this 3 diagram, on the x-axis, we report the crystal site occupancy calculated on the basis of the real one, calculated on the basis of the XRD. Instead of the y-axis, we have the occupancy calculated on the basis, on theoretical basis, like from the Morimoto and Tal, or on the oxygen. Looking at the crystal site occupancy of magnesium and iron 2 in the M2 site and M1 site here, and the iron 3 content in the what we can see is that the real cation distribution calculated with the XRD structure refinement is very different from the site occupancy calculated on theoretical basis. And this is very important when then we try to determine the different end member of the clinopyroxene and then extract the temperature. So in terms of the result, here are the volume of the cell and the volume of the M1 site for all the clinopyroxene that we studied, and we can see a very, very good correlation with an increasing of the volume of the cell and the volume of the M1 site. And this coherent correlation can be due to different factors, the chemical composition, variation in chemical composition, variation in temperature, and variation in pressure. So let's look at each one of these factors one by one. Here is the compositional effect, the magnesium number and the occupancy of the 3+ cation in the M1 site against the volume of the cell on the x-axis. The blue line refers to the expected variation of the volume of the cell with each of these compositional data. So for example, for the magnesium, we have the variation between the diopside and bergite. In this case, the variation of the substitution of the jadeite and the gyrine and then the essonite here on this other one. Okay, so what we can see is that really there is no correlation. I mean, none of the analyzed clinopyroxene follow any of these blue line. So the variation of the volume of the cell cannot really be explained with compositional variation. Let's look at the effect of the temperature. So as I said, we use two different clinopyroxene liquid. The Nimis Niven-Putirka 2017 based on chemical data only, and the results are reported here on the left-hand side. And the Nimis 1999 based on structural and chemical data, and the results are reported here in the, on the right-hand side. They are both used in combination with the geothermometer of Putirka. So the temperature estimated, we can see that there is some sort of correlation in both cases, but the correlation that we can see with the volume of the cell for the temperature estimated on the structural and chemical data is definitely better. And also, it makes sense in terms of the petrology, because the low calcium clinopyroxene, they have higher temperature than the other two population. Instead, on the chemical, well, okay. I'll not try to go back. On the chemical data, the correlation is not that good. So, can I go back? Okay, yes. The correlation with the chemical data is not really that good. But the main thing is that this correlation that we see between the temperature and the volume of the cell contradict the thermodynamic. In fact, the higher the temperature, the higher the entropy, and so the bigger should be the volume of the cell. Instead, we have, Instead, we have exactly the contrary. So the higher temperature corresponds with a lower volume of the cell. So again, the variation of the volume of the cell cannot be explained with temperature effect. So we are left just with the pressure as a possible control on the volume of the cell. And here are the results, the chemical data only on the left-hand side and the structural and chemical data on the right-hand side. In both cases, again, we have a correlation, but the correlation with the structural and chemical data is way more effective. We can discriminate three different magmatic environments, so three different pressure where these crystallize. In agreement with the petrological data, and instead the discrimination of the three magmatic environment is less clear with the chemical data only, and also contradict in some place the petrological data. With this one, they should be deeper, instead they are kind of shallower. But the other thing is that there is a very good correlation between the increasing of the pressure and the decreasing of the volume of the cell, as we expect on thermodynamic basis. So clearly, the structural data, they give you a better constraint of the temperature, and the volume of the cell is really controlling the pressure. So let's put everything in the context of the POPO plumbing system. In this diagram, we have the pressure increasing downward and the temperature increasing on the right. And then here the plumbing system of POPO. So on petrological basis, we expected that the low calcium pyroxene, they were crystallizing at higher pressure, and indeed they do. And we retrieved an estimated depth of about 30 kilometers. The second population, the blue one, we thought they were crystallizing in the intermediate portion of the system, and they do. We estimated a depth of about 20 kilometers. And for the shallower clinopyroxene, they crystallize at depth of less than 10 kilometers. So clearly, determining the structural parameter really give you a better identification, estimation of the pressure, and can really make a difference for rescale the depth of the plumbing system. And this works for POPO, and we think can work also for other volcanic systems, particularly in ARC. So finally, just the take-home message. The single crystal X-ray diffraction is clearly the only method to resolve the actual distribution of magnesium, iron 2 and iron 3 on the structural side. And given the dependency on the pressure, it's really worth going through the pain to do the structural refinement, because actually this can give you really a better constraint of pressure. Okay, thank you very much.
Thank you very much, Chiara. Almost perfect timing. Any questions for Chiara?
Let's see everybody.
No, well, I have one. Doing single crystal XRD is quite tedious, I think, and time consuming, is that right? So you probably can't do a lot of crystals with that method unless you put a lot of time and effort in?
Yeah, it's very tedious and time consuming. You have to pick up physically and then go into the XRD and do one by one. So, yes, you cannot do on a lot of crystal, but we did on actually a few crystals. There were 12 crystals, and then we extracted portion because they were crystallizing in different portion of the in different magmatic environment. And still, we had a very good result. So you can do on few crystals. I suppose the main problem is that the crystallographic skill are kind of, we are losing people that are able to do it. That's probably the main drawback.
Okay, and you think the method can be applied to any volcano, any clinopyroxene, any? Yes.
We think definitely it can be applied to any clinopyroxene. Definitely works in ARC system. Probably if you start to look at the rift system, the constraint on the pressure for the CPX liquid are definitely better than the ARC system. So it might be not worth doing it in that environment, but for the ARC, it's definitely worth doing it. It's a painful process, but yes, worth it.
Okay, thank you. Any questions? Too early for crystallography? Okay, thank you very much, Chiara. So my understanding is that the next talk is online, and it's by Federica Totaro, A Taste of Poorly Known Volcanic Activity in Campania, southern Italy, before 110,000 Ka. And here she is. Excellent.
Okay. Good morning, everyone. My name is Federica, and the topic of this talk will be the volcanic activity in Campania before 110,000 years. During my PhD project, we studied several outcrops of Precampanian ignimbrite products, outcropping mainly at the foot slope of the limestone reliefs surrounding the Campanian Plain. The Campanian Plain is a wide Alpgraben depression that has been and continues to be a site of intense volcanic activity since at least 300,000 years. During this talk, I will deal with two different outcrops located at Valle di Maddaloni and near Taurano. The geology of the area is represented by shallow water limestones, here represented in green, and limestones and dolomitic limestones in pale blue, covered by pyroclastic rocks and non-volcanic post-orogenic deposits. The intense and voluminous volcanic activity has often buried or eroded the products of the older eruptions, discouraging studies in this time window. But in proximal area, we have several outcrops of Precampanian ignimbrite products, and in the intermediate area, several ancient ignimbrites were studied and dated. More recently, some widespread tephra markers from the Mediterranean area were also recognized in the field. But in distal and ultradistal successions, we have several tephra layers from a Campanian activity that has no terrestrial counterpart in the time span just before the emplacement of these markers. So, although we were aware of the difficulties, we tried to partially fill this gap. For this purpose, we characterized the volcanic glasses in terms of measure and trace elements, and also in terms of isotopic composition. Then we provided some argon-argon dating on the Sanidin-bearing samples. The Precampanian ignimbrite products in the field outcrop has quite well-preserved fallout deposits or thick ignimbritic successions, often separated by paleosols or humified horizons or reworked levels. But more often, the products of this ancient volcanic activity look like nothing more than a argillified pyroclastic deposit. The Valle di Maddaloni sequence is represented by two different fallout deposits separated by a bedded deposit humified at its top. The basal fallout deposit shows a color variation, being lighter at its base, becoming dark in correspondence of the mud tree level because of the presence of dark scorie as juvenile fraction, and then returning lighter at its top. The second fallout unit is mainly represented by several massive or inverse graded pumiceous levels. And then we have two ignimbrite units separated by another pumiceous level. These two ignimbrite units show a pervasive columnar jointing. The Taurano San Giovanni del Palco sequence shows the presence of the debris supply from the carbonate slopes that surround the area, and starts with a badly preserved fallout deposit, and then unconformably on this first volcanic unit and on a paleosol, we have a second fallout sequence that shows a color variation from lighter at its base to darker at its top. Other two badly preserved fallout units separated by humified syeneritic level, and then the last volcanic unit before the Campanian ignimbrite products is represented by a thinly bedded deposit, mainly made up of an alternance of dark and lithic rich and light colored and pumice rich layers. After the study of the described samples at the optical stereo microscope, we selected the sanidine-bearing samples to provide the argon-argon dating. And we obtained an age of about 180,000 years for the base of the Taurano sequence and 167,000 years for the MAD6 bis unit at Maddaloni. So, basing on lithological and depositional features of the studied levels, we made a first attempt of correlation between the basal fallout outcropping at Maddaloni and the Tau2 unit in Taurano. Then we characterized the glasses extracted from these levels in terms of measure and trace elements. The basal fallout outcropping at Maddaloni shows a composition ranging from phonolite to tephrophonolite, while the MAD6 bis unit straddles the boundary between phonolite and trachyte fields. The two Ignimbrite sequences show a composition that ranges between phonolite and phonotephrite fields. Some of the Taurano samples show the same arrangement of those of Maddaloni, while others fall into the trachyte field. So the next step was to confirm the correlation between the basal fallout at Maddaloni and the Tau2 unit in Taurano. Looking at the major element compositions, we found a very good correlation between the several levels that we analyzed from the two units. The most evolved compositions pertain to the basal level in the Taurano unit, while in the Maddaloni one, we have this kind of composition mixed with the less evolved ones at the top of the unit. These differences could be due to a variation in the direction of the dispersal axis during the sustained column phase. We decided to name this eruption the San Giovanni del Palco eruption because this was the first occurrence in the field of this product. And even if this eruption was not directly dated, it is well constrained between two dated eruptions. The isotopic composition and the trace elements data also confirm our first hypothesis. The overlaying fallout unit at Maddaloni and the Tau4 unit in Taurano show a composition that straddles the boundary between phonolite and trachyte fields. And if we look at the measure element compositions and the trace element patterns, and also their contents, we can point out a very good correspondence between these two units. Also, the isotopic composition confirms our correlation. So at the very beginning of this talk, I stated that in distal and ultradistal successions, we have several tephra layers referring to a Campanian activity in the time window before 110,000 years that have no terrestrial counterparts. So we tried to find into these records the products of the San Giovanni del Palco eruption. And we found it in a marine core drilled in the Ionian Sea and studied by Patern et al. In 2008, and also in the Lake Ohrid succession. Even if in this succession, we have only the less evolved terms of our eruption. Moreover, we reanalyzed some samples from the San Marco Evangelista Boreal near Maddaloni, and we found these products also in this succession in the sample SEP6. So this eruption has an age well constrained between 167 and 180,000 years. And as you can see in the map, it has a very huge dispersal area. The two Ignimbrite units that close the sequence of the Maddaloni succession point out a very good correspondence with the distal and ultradistal counterparts of the so-called Taurano ignimbrite, previously found in the Fucino Basin, in a marine core drilled in the Adriatic Sea, and also in Lake Ohrid succession. Also for this eruption, we found this product in another of the reanalyzed samples from the San Marco Evangelista boreal, the SEP5 sample, and Amato et al. In 2018 found some products referring to this activity most evolved and that only partially overlap our data. The age of this eruption is of about 160,000 years, and also in this case, we can outline a very wide dispersal area. So, despite the difficulties that we have encountered during this study, this work presents the first comprehensive glass characterization of at least 3 well-defined eruptive events that are constrained between 118 and 116,000 years and are ascribable to a Phlegraean-like volcanic source. The eruption year named San Giovanni del Palco, even if not directly dated, is well constrained between 167 and 180,000 years by 2 dated eruptions. And it could represent a good marker for the transition between the marine isotope stage 6E and 6D. Moreover, the glass chemical data acquired on the Taurano ignimbrite in the field confirm the wide compositional variability previously detected in distal and ultradistal counterparts. And finally, we would like to highlight that the joint use of trace elements and isotopic compositions can strengthen the correlations based on major oxide compositions and can be a very powerful tool to solve doubtful attributions. Thank you very much for your attention.
Talk. Is this working? Yes. Any questions? Well, then it's probably me again. You mentioned a Phlegraean type source for your tephra units. Are you able to specify this a little bit better? What that could be?
Well, yeah. Obviously, and unfortunately, because of the scattered nature of the pre-Campanian ignimbrite outcrops, we cannot reconstruct the location of the vent, but on the basis of the chemical and isotopic fingerprint, we can say that they have a Phlegraean-like source. And I think that in the next future, with more data about my several studied outcrops, maybe we can make some interesting and more detailed hypotheses about this ancient Phlegraean source, because it is not well known at this moment. But there is a Phlegraean affinity in the trace element data and also isotopic composition.
Okay, thank you very much.
Thank you.
So there are no further questions, so thank you for your talk.
Thank you.
And we move on to the next presentation by Janine Kavanagh on magma flow regimes within active dikes, the role of viscosity.
Okay, hi everybody. Really nice to be here. So I'm going to be talking about some analog experiments we've been doing in the past couple of years. The title is about active dikes and the role of viscosity. So there's abstract was submitted 2 years ago, and a few changes happened over that time period, notably the addition of Caitlin Chalk to our team of researchers who are working on this, along with Thomas Jones and David Dennis. And I'd like to start with a field image, which is very much an inspiration for all the work that we do in our analogue lab. I'm talking about dikes, which are an important part of the volcanic plumbing system. And many thanks to Soraya Hilmi Hazim, who's very creatively made this nice illustration of all the different ways in which volcanic plumbing systems can be studied. And we've seen lots of really nice examples of that in this session yesterday and also for the rest of today. And so I'm talking about analog models, so these guys up here. And what we're trying to do is explore the physical parameters, but ultimately they are connected to all the different kinds of signals of magma movement. And so that's why it's really great to talk to such a diverse audience today. And so the dikes are magma-filled fractures. They're cutting across the rock layers to feed the volcanic eruptions, and they're an essential part of the plumbing system. But most dikes don't erupt, actually. They're kept within the crust, and so the dynamics of the movement of the magma within the dikes is really interesting and something that we've been exploring in our analog experiments. So in our experiments, we use gelatin as an analogue for the elastic crust. And then we have a clear perspex tank just here, which is 30 centimetres high, 40 centimetres wide. And then that gelatin is cooled, and it's an elastic material. We make a small slit in the base, and then we inject into the bottom of that our magma analogue. In the talk today, I'm speaking about Newtonian fluids. So these are fluids which have a constant viscosity. And the fluids we're injecting have tiny particles suspended in them, which are passively tracing the movement of the fluid as we create these very thin penny-shaped cracks, which are analogous to dikes. And so the fluids that I'll talk about today are silicon oil, which has a viscosity of 0.45 pascal seconds, and also water, which is 0.001 pascal second. They have very similar density. They're very slightly less dense than the gelatin. And so this, so just to introduce our new laser imaging setup. So we have our perspex tank where we create a very thin laser sheet which is projected through the tank. So here's the tank, and this is. I realised whilst preparing this talk that there's quite a nice Greek connection, because we've called our laser Medusa, and that's because it has these sort of tentacle-like things sticking out of the end, and this really bright light, which if you look at it with your eyes would turn you blind. So we called it Medusa. This is the Caitlin in the back, with also known as Perseus, with her protective glasses on so that we can safely conduct our experiments. And so what we're doing is we're creating fractures and then illuminating them with this laser. The particles fluoresce, and so the videos I'm going to be showing you are basically those raw videos and then processed images to show velocity. And so the technique we use to process the images is called particle image velocimetry. And what it's doing is basically looking at two different time intervals and tracking the patterns of movement of particles. So you need quite a lot of particles. It's not tracking individual ones. It's more of a pattern matching technique over different time intervals. And that gives you a velocity vector field. So this is an experiment. The first one I'm going to show is with silicon oil. And so what you can see there, it's sped up a lot, and I know it's a bit faint here with all the projector light and stuff, but hopefully you can see tiny little particles swirling around inside the dike as it's created. If I could try and show you the edges. So the dike is actually a little bit wider than it appears here, because basically what we're seeing is the intersection of the laser with the dike, and so we have to predict where we think the dike will be and then hope in the experiment the dike will go exactly in the laser sheet. More or less it does, but sometimes it's a bit forward or backwards. So that's kind of our raw data. This is silicon oil, and this is a really slow injection. So this experiment, I showed it there in about like 10 seconds. It took about an hour and a half for that to happen. And then this is another silicon oil injection. But this time I've done the PIV on it. This one is much faster. Well, not much faster. It's 30 RPM, so 10 times faster. This experiment took about 45 minutes to happen. And then what we can see with the PIV is the flow vectors. And so we see a really interesting structure of a central vent, jet-like feature, and then recirculation of the fluid around the margins. And so the color here is basically showing you the magnitude or the intensity of the velocity, and then with arrows we're showing the movement. And so in this very simple Newtonian dike with most simple fluid that we can imagine, we're creating a thin penny-shaped crack, and we have these very interesting recirculation patterns inside the crack as it grows. So that's with silicon oil, which is brand new experiments for us. We've done a lot of work on water, so this is the first time we've been doing things with silicon oil. And so, yeah, we see these sort of key structures of a central jet, recirculation, but also these sort of stagnant regions as well. So basically no colour means no flow. And so interestingly, those stagnant regions are pretty stable within the dike, and the flow is moving much faster than the dike is able to grow. And so that's why you're getting that sort of gradual recirculation of movement. And then by using water, we're able to get to much higher velocities because we've got a less viscous fluid. So this is a water dike. And here we see some of the features. Just by eye, we see a jet, we see recirculation. But just by eye, hopefully you'll see that jet is pretty unstable, actually. It's starting to meander around, wiggle about, and then that's the moment there of eruption, and everything goes up and out of a very small fissure which forms at the surface. And so in the subsurface, the dike is much larger than the small fissure that's created, and then that moment of rupture leads to a pressure decrease, and everything just flows up and out. And so this is then the PIV, where we can see the flow structure. So we've got that nice recirculation again. We have our jet, but the jet is wiggling around. It's very high intensity. The wiggling sort of intensifies as it approaches the surface, and then we get that eruption and the draining. Those were 4 different experiments, 2 different fluids, and quite a range of different injection rates that we used. And again, this could be basically the same figures as the silicon oil injections I showed you, but we do have this noticeable wiggling around of the jet in the top part. And we believe this is sort of a transitional type of behavior, moving into a more turbulent flow. And talking about flow regimes, that's why I'm going to introduce the Reynolds number. So Reynolds number is basically a way of thinking about the parameters which are driving the flow. So the inertial parts on the top of the equation, density, the length scale, the velocity of flow, and then the viscosity, which is sort of on the bottom and resisting the flow. So we calculated the Reynolds number for all of our experiments, and it's a way that we can connect our flow regimes in the lab to those in nature, because these are all things that we can measure in nature as well. And so this is just a table of those 4 experiments and all of the different numbers that we get out. You'll notice the increasing flux here in green for our different experiments, the 2 different viscosities. Basically, the density of our fluids is exactly the same. The only thing that's different is the viscosity. And then on the end here is our Reynolds number calculations. And we've calculated that in 2 different ways. And basically, with these 4 experiments, we've been able to explore 5 orders of magnitude of Reynolds number. Interestingly, if you use the velocity of the movement of the fluid inside the dike in the calculation, which is actually what the fluid is moving, then you get a higher Reynolds number, one order of magnitude higher. But in nature, we don't really have those numbers, and so a tip velocity will also often be used to calculate a Reynolds number of a natural dike, but that could lead to an order of magnitude underestimation of a Reynolds number. And Reynolds number is basically telling you about flow regimes. So any kind of transitions to turbulent behavior might be really underestimated based on field observations or geophysical observations. So just a sort of summary diagram about those key features of a jet and recirculation. And then with our higher flow, low viscosity fluids of water, we think that we're getting the transition into more turbulent flow. And so we're exploring those even higher Reynolds numbers now in the lab. But the flow structure of that recirculation for these Newtonian fluids is really stable, and we've managed to map it over 5 orders of magnitude, maybe even higher than that. We still haven't got to that point yet. But the jet instability seems to be developing somewhere in the 0.02 to 30 area. So this is an interesting place to explore as well. And so just some conclusions about the work. So I've shown you about the flow regimes just with the very simple Newtonian fluid. And we get some really interesting structures. And I think these are important for helping to interpret the signals of magma movement in nature, because they're going to affect the geophysical signals, potentially the geodesy, so the way in which the ground is deforming, the geochemistry, the petrology. They're all going to be affected by this movement within the dike as it's growing. We've used a Newtonian fluid, and I believe that is most relevant to deeper parts of the system, where we've got a fluid and crystals, basically before gas exsolution happens, because that changes the rheology of the fluid, so deeper parts of the system. And basically, we think that these sort of conceptual models of movement of magma within dikes needs to be put into numerical simulations. And so I direct you to Caitlin's talk, which is on Thursday afternoon in the big hall, where she was going to be telling you about our efforts to put this complexity of fluid flow into numerical simulations. And that's it.
Thank you very much, Janine, for this interesting talk. Are we having any questions? I have one. I was just wondering, obviously, if you take a natural dike rock, which is the crystallization product of the processes you're trying to identify in your experiments, do you think there are any textures then that can be directly related to what you just showed in a natural rock?
Yep, so in a field outcrop, there are sort of macroscopic flow indicators. So, for example, stretched bubbles or even large phenocrysts which are aligned. And if you're able to map those out, then we might be able to see these kind of structures and in magnetic fabrics, so in the microscale and in the microstructures, potentially there's information there as well in terms of maybe the stress or strain that crystals are experiencing as they're coming up in the plumbing system. So yeah, it's really important to link analog experiments with field observations. Actually, we're going to Iceland in 2 weeks to do some more sampling and check out what's going on in real life.
Okay, thank you.
Okay.
I have a follow-up on that question, actually.
Yeah.
There is a question.
No, please go ahead, and then we come to you guys. Yeah.
In terms of really looking at the real case, particularly the turbulent flow, what you expect to see in the field, or where? I mean,
in terms of
the turbulent flow that you were
turbulent flow.
Yeah.
Yes. So basically, lack of any coherent pattern, I would say. So it is quite important to get constraints on the propagation flow patterns compared to the solidification flow patterns. And we've done some work with magnetic fabrics which have been able to untangle those different patterns that might be recorded. So at in the chilled edges of an intrusion, for example, you're more likely to capture the flow, whereas within, then you've got other processes which might have gone on to complicate matters or overprint an original flow fabric which might be there. So yeah, it's complicated in nature. That's why I stick in the lab.
Test. Okay. Just a quick question. So if I would try to understand this turbulent flow behavior, how would this translate in the real world regarding the seismicity? Do you think that this might generate higher frequencies of earthquakes, or do you have an idea about that?
Well, from our sort of preliminary experiments we've done at the very high Rayleigh numbers, the shape of the dike is quite different, and that might be something that could be expressed in seismicity patterns, and so the shape of the intrusions being created, and maybe the displacement of the rocks in terms of the geodatic measurements that could be made. Possibly there's something in there, but it's pretty early days to be able to say for sure. We need to do 3D experiments where we're imaging the shape of the intrusion in 3 dimensions and the flow in 3 dimensions, and then we should be able to understand that a little bit better, I would say.
Okay. Very interesting. Thanks.
Thank you.
Okay, we have more questions.
No.
Yeah, excellent talk. I was curious, when your dike hits the surface of your model, are you able to then assess how high a lava fountain will be, especially since that jet starts to go directly to the vent area?
Oh yeah, well I couldn't show it because of time constraints, but we did an injection at 400 RPM, which was, the experiment took about 30 seconds compared to an hour, so that was exciting. And then we had this fantastic jet which formed, and we can see that. We haven't done anything with it, but it would be really interesting to link those eruptive processes and with the dynamics of the plumbing system. That connection, I think, is really exciting. So.
Was there more question? Okay, we have time for one more.
Okay.
I jump in then. I'm a bit biased. I love those experiments. And I think you answered part of the question I had on what would be the strategy in terms of monitoring a volcano to extract some information during the injections and potentially have a forecast on the flux before the start of the eruptions. I have a forecast on the potential volume to be erupted. So if you have any thought on strategies.
Well, yeah, and I think in the shallow environment, the non-Newtonian behaviour becomes even more important, actually, because of gas exsolution. So the stuff I've presented today with Newtonian fluids, constant viscosity, I would say that's much more relevant for deeper parts of the system. I'm not sure from the geophysics and geodesy how much we can really monitor of that deeper part of the system. So I would say that the shear thinning experiments that we've done, which I couldn't present today, but they're going to be much more relevant to that monitoring side and the sort of remobilization of liquids and, definitely those kind of experiments I feel are a bit more applicable to the shallow environment.
Okay, thank you very much, Janine. So let's move on to the next talk by Alessandro Frontoni, a database of crystal-bearing magmas for the calibration of a rheological model. Oh, it's remote.
My name is Alessandro Frontoni, and today I'm going to present to you this work about a comprehensive database magma is subjected to within the conduit. Due to the complexity of such a polyphase system, several open questions remain for an exhaustive comprehension of magma rheology. Here, we focus our attention on the rheology of two-phase particle-bearing mixtures of natural magmas as a necessary building block for the comprehension of the behavior of magmas in natural environments. In this work, we present a comprehensive rheological database including most of the existing data relevant for crystal-bearing magmas collected from the scientific literature, covering the entire range of volcanic conditions in terms of crystal content from 1 to 80% of crystal content, crystal shape with aspect ratio ranging from 1 to 13, and strain rate between 10 to the minus 7 and 10 to the 2 reciprocal seconds. And the final result is a consistent quantitative description of the rheological behavior of particle-bearing magmatic systems. In general, viscosity increases as the solid phase concentration of the mixture increases according to a sigmoidal shaped curve here, semi-quantitatively described for the first time by Lejean and Richer in 1995, and then through a mathematical parameterization by Coste et al. 2009 in terms of relative viscosity, which is the value of measured apparent viscosity divided by the viscosity of the suspending liquid. And that is the first and only model able to reproduce the trend of the viscosity for a particle amount over the Phi-max value, which is this value here. And this model consists in 4 parameters, delta, gamma, phi star, and xi, and this is a semi-empirical parameters equation that describes the variation in viscosity of a melt as a function of the crystal content and the strain rate, and it is valid only for crystals with aspect ratio equal to 1, therefore spherical. Now, 4 different flow regimes can be recognized, diluted and semi-diluted, concentrated and hyperconcentrated, describing a weak nonlinear variation of the mixture viscosity in the regime characterized by non-interactive suspending particles, so diluted and semi-diluted, till the achievement of the critical value here, beyond which particles start to strongly interact among them, affecting considerably the increase of viscosity here in the concentrated regime, which is characterized by a strong nonlinear variation and a significant yield stress, so a non-Newtonian behavior. These 3 regimes depend not only on the concentration, but also on the shape, size, distribution, and orientation of the crystals. As the crystal fraction achieves its maximum packing fraction, here, the mixture enters in the hyperconcentrated regime, and as the solid fraction further increases, the formational mechanisms change and strongly depend on the material properties of the solid phase. A big number of authors have focused their attention on the modeling of the viscosity of particle-bearing suspensions as a function of the aspect ratio of the suspended particles, especially in the diluted and semi-diluted regimes. However, most of these studies did not consider the concentrated regimes and the effects of the strain rate on viscosity. It was demonstrated that at high particle concentration, the transition between Newtonian and non-Newtonian behavior occurs earlier as the strain rate increases. At lower strain rates, the behavior is Newtonian, and the increase in viscosity is mainly due to the textural features of the mixture itself. As the strain rate overcomes a certain threshold, the decrease of apparent viscosity occurs, explained by a non-Newtonian fluid behavior known as shear thinning. In addition, it was also demonstrated that at the same strain rate, the transition between Newtonian and non-Newtonian behavior occurs earlier as the aspect ratio of the particle components increase. Here. In order to consider all these parameters, we first had to collect a rheological database describing the rheological properties of magmas according to these parameters. The development of the numerical model involved the compilation of this database, including over 1,400 rheological data taken from over 40 scientific papers. Every data has been classified as a function of the material type, whether natural, synthetic, or analog. And then it's been specified the chemical composition where possible and the adopted experimental strategy, which includes the temperature and the applied strain rate, and also the phase components of the material, that is the crystal content together with the aspect ratio. Results were presented in terms of bulk viscosity at the related temperature, melt viscosity related to every experiment, and relative viscosity. Despite the huge bibliographic research, a large part of the dataset have been excluded for lack of information. The first step of this work involved the implementation of the pre-existing model of Costa et al. For spherical particles with a more complete dataset in order to improve the fitting. In these diagrams, reporting relative viscosity against crystal fraction, we added to the dataset from Caricchi et al. 2007 used for the calibration of the model of Costa et al. The new collected datasets. And the dataset, the entire dataset is reported with different colors as a function of the strain rate. Now, to further improve the fitting, a correction of delta M value here for the calculation of the delta parameter was performed in order to remove a mathematical problem and to improve the fitting also in the higher part of the curves. So, in order to extend the model to non-spherical particles, we first considered the most complete dataset at different aspect ratio at a constant strain rate of 5 per 10 to the minus 4 second to the minus 1. Now, for the case of the spherical particles, we used the fit based on the dataset from Caricchi et al. 2007, while new fittings were performed for all the other data with different aspect ratio. This allowed us to evaluate the specific constitutive empirical parameters for each aspect ratio, which you can see here, and the dependence of the empirical parameters from the aspect ratio was then described with power law and exponential relationships, which were further applied to the cases concerning different aspect ratios and strain rates. Once the parameters controlling the particle shape effects were estimated for the case of 5 per 10 to the minus 4 second to the minus 1 and the model generalized, the performance of the latter was tested on all the other cases for which there are less available data, preventing to use them for quantitative fittings as reported in the supplementary material of this work. As an example, the case for spherical aspect ratio and aspect ratio equal to 4 for different strain rates are reported. In particular, in this figure, we show the application of the model to 3 strain rates of 10 to the minus 6, 10 to the minus 5, and 10 to the minus 4 reciprocal seconds. And for these cases, we have the possibility to compare the results both in the diluted and in the concentrated regimes, which represents a very important novelty, as data covering the entire range of crystal fractions are typically quite scarce in the literature. Now, as mentioned above, the available data for different strain rates do not cover the entire range of crystallinity. Very high particle fraction datasets are populated only for spherical crystals. However, taking into proper consideration the data scatter and uncertainties, the model is in good agreement with the data. A high crystal fraction plateau-like relative viscosity region is recognizable for each dataset, which you can see here and here. And for a given aspect ratio, this plateau-like region is higher as the strain rate decreases, as you can see from here to here. This is evident in this figure where blue dots consisting in spherical particles and strain rate of 10 to the minus 6 second to the minus 1 show higher relative viscosity values, with respect to the orange dot consisting in a lower strain rate of 10 to the minus 5 reciprocal seconds, which lay in the middle, and even more with respect to the yellow dots consisting in spherical particles and strain rate of 10 to the minus 4 reciprocal seconds. Such a plateau-like region is clearly recognizable for the dataset corresponding to aspect ratio equal to 4, which you can see here, although it is achieved at much lower crystal fraction with respect to the spherical particles. In general, we can say that at a given strain rate, the sigmoidal shaped curves of the model are systematically shifted towards the lower crystal fraction as the strain rate decreases and the aspect ratio increases. Although data are lacking for the diluted and semi-diluted regime for higher aspect ratios, its lack of data is not very critical, as the model agrees with the dataset at lower solid fractions available for other values of aspect ratios and strain rates. These are just 2 examples of the application of the model, which can be applied now to all the aspect ratio and strain rates of volcanological interests. So to conclude, we can say that A wide rheological database was put together, highlighting also the issues in reporting data, and you can find the database at this link here. The model of Costa et al. 2009 is valid for spherical particles, was at first extended to all the natural strain rate and then applied to other aspect ratios, and for the first time there is a model able to forecast viscosity for all the natural volcanic system. This research has just been published on Scientific Data from Nature Portfolio, and it's open access. Feel free to download the PDF and contact me for further and more detailed information. And thank you for your attention.
Okay, so this was a recorded talk, so we can move on straight away to the next two talks. So the next two talks are all given by Simone Costa, and the first one is about kinetic crystallization of high K basalt melt undercooled in laboratory, implications for modeling open conduit dynamics at Stromboli volcano. And then I let Simone introduce his second talk in 15 minutes.
Okay. Thank you very much. Good morning, everyone. In this presentation, I will show you some of our results of our experimental study. But first of all, I would like to thank all of my co-workers, especially Fabio Colle, who's actually the main investigator behind this project. So we performed kinetic crystallization experiments to evaluate the effect of the undercooling on clinopyroxene morphology, and to parameterize an empirical equation to decipher the degree of undercooling in open conduit volcanoes. So the degree of undercooling is expressed as the difference between the liquidus temperature and the actual crystallization temperature, and is the thermodynamic force driving the magma crystallization. And by investigating the degree of undercooling, we can model the crystallization path of basaltic magmas under dynamic conditions such as in open conduit volcanoes. Stromboli, of course, as many of you know, is a worldwide example of persistently active volcanoes in an open conduit volcano, sometimes experiencing some transition between most energetic explosion from the normal activity, the so-called major explosion and paroxysm. Okay, the undercooling experiments were performed in a piston cylinder at the University of Pisa in a temperature range between 1050 and 1220 degrees at 300 megapascal, and both at hydrous and anhydrous condition. And as a starting material, we use a low porphyritic AK basalts of the 2003 paroxysm. And the resulting degrees of undercooling are from 15 to 140 degrees at anhydrous conditions, and from 10 to 110 degrees at hydrous condition. Okay, here shows some textural features of experimental clinopyroxene. At low degree of undercooling, clinopyroxene is euhedral to skeletal form and sometimes shows sector zoning. And at higher degrees of undercooling, the clinopyroxene became from skeletal to dendritic and showed dendritic zoning. Okay, the composition of experimental pyroxene depends on the degree of undercooling, and as the degree of undercooling increased, the clinopyroxene became progressively enriched in titanium and aluminium with a simultaneous decrease in compatible elements such as silicium and magnesium, as a consequence of interplay between crystallization and supersaturation in the melt in slow diffusive cations such as titanium and aluminium. Okay, we use the compositional dependence of clinopyroxene from the degree of undercooling to parameterize an empirical equation that is based on the least square linear regression of the experimental data for the calibration of an equation able to estimate the degree of undercooling. And we applied this equation to the natural composition of a natural clinopyroxene erupted at Stromboli. And on the right, you can see we coupled the predicted degree of undercooling with the temperature thermometer, with the temperature obtained by the thermometer of Butyrka 2008, and we can recognize three population basically of clinopyroxene. The first one is represented by diapsidic cores that shows higher temperature and lower degrees of undercooling, and the hagioric mantles of crystals that shows higher degrees of undercooling and lower temperature. And basically, this is a process that of decompression-induced crystallization of the magma. When the magma is under decompression, there is a loss of volatile that increase the liquidus temperature of the magma with the consequent increase of the undercooling. Then the trend depicted by the augetic mantles from higher degrees of undercooling and toward lower degrees of undercooling and lower temperature is interpreted as isobaric cooling. And then finally we have the mafic recharge that we found in mantles of the pyroxene that shows a higher temperature and lower degrees of undercooling. Okay, so thanks for your attention. This is.
So thank you very much for your first talk. So we have time for questions. Chiara?
So you used basically the diopsidic core mantled by the augetic rim for your experiment. That's from one of the paroxysms. Have you tried with any of the do some experiment with the normal activity?
Actually, the picture, it was both on normal activity and paroxysm. Yes.
Ah, okay.
I can show another time if you want.
Yeah.
Yes, their core are represented by the yellow one are from the normal activity and the red one are from paroxysm.
Okay.
And also for the mantles and the recharging bands.
And there is no difference?
No.
That's interesting. Yeah. And have you did any experiment with the crystal that have the diopsidic rim or
No.
No.
Not.
Mm.
We have to try, yes.
Yeah, because that will be interesting to
Yes.
see how the undercooling play on that one.
You mentioned a compositional dependence between undercooling and the clinopyroxene composition. So what's the reason for that?
Because at higher degrees of undercooling, clinopyroxene growth is dominated by a diffusion-limited growth, and the melt and the interface melt between and the melt at the interface between the crystal that grows became enriched in incompatible elements that have slow diffusion in the melt.
Okay, thank you.
I have another question, actually. You mentioned the sector zoning that is
Yes.
developed. Do you see at any rate or undercooling, or there is like a certain point where they develop?
No, we observe just until 60 degrees of undercooling, but it became progressively rare. The most common is observed at 10 degrees of undercooling. So there is a threshold. Basically, after 60 degrees of undercooling, we not anymore observe sector zoning. So we put the threshold to low degrees of undercooling and high degrees of undercooling at 60 degrees.
How does this compare with the similar experiments on Etna from Mollo and
okay.
and all the rest of the group?
First of all, we tested the model with the data set from the Etna experiments. Obviously, this equation is empirical. It's not thermodynamic controlled. We are working on a thermodynamic, more robust equation. But for the moment, that model is calibrated on experimental composition of stromboli. So the Etna, if you put the composition of Etna crystals in that model, it doesn't work.
Mm-hmm.
So it's specific to stromboli.
You have a question for me? Massimo. Sorry, Massimo, can you go to the microphone?
The other one.
That one?
You put the difference between two models.
Massimo, sorry, speak on
Difference
them.
between two models, Putirka. But for Putirka, you should equilibrate with a liquid.
Yes, obviously.
Which kind of liquid?
Okay, we use the wall rock. I forgot to mention, but we use basically before we test the equilibrium between the clinopyroxene and melt and the coexisting melt, and we then use the wall rock.
Okay, thank you. So please, let's move to your second talk.
So fortunately, we stay in the Aeolian Islands, and we continue to talk about clinopyroxene. So the most of eruptive activity worldwide is represented by low intensity and low magnitude eruption that, while in proximal and medial outcrops, this eruption produce often the emplacement of bombs and lapilli sites material. In distal, more distal outcrops, they produce the ash sites deposits that are rarely used to employed to acquire specific geochemical data to gain insights into plumbing system dynamics. So in this work, I present an approach that is basically based on a hierarchical cluster analysis of clinopyroxene chemical profiles that is appropriate for this type of hash site succession, but also for more coarse pyroclastic successions. As a case study, we use the Palizzi eruptive unit of La Fossa Vulcano in Vulcano Island. That is one of the most important eruptive periods of the last 1,000 years of La Fossa. And basically, it is constituted by a sequence of hash-dominated deposits punctuated by the emplacement of two main fallout layers related to subplinian events. And the particularity of this sequence is that going upward, it became progressively interested by the occurrence of the pause in the eruptive activity recorded by the presence of minor unconformities and epiclastic materials. Here I show some textural features of the deposits that basically as you can see, it's an ash-dominated sequence, and we have here on the right the chemiostratigraphy of the juvenile glass and of the wall rock that is available for the main pumiceous fallout. Essentially, the juvenile fragments of the sequence are shoshoniric in composition, with the exception of the first level emplaced after the rhyolite of PAL-B subunit, and then we have the trachyte on the top of the sequence of the PAL-D subplinian eruption. Okay, in this kind of situation, the study of zoning patterns of crystal can provide insights in timescales, obviously, and pumping system dynamics. And I investigated through all the stratigraphic sequence through 125 contouring chemical profiles, the composition of chemical pyroxene. But as you can see from the variation diagrams, the composition of clinopyroxene do not show any particular geochemical trend from the base to the top of the sequence. Moreover, a single profile can spine the entire compositional variation of the chemical complexity of pyroxene. So I performed a hierarchical cluster analysis based on the minimum variance criterion method and the Euclidean distance as clustering method. And with this method, the clinopyroxene profiles are simplified into a sequence of clusters, and each analytical spot of the clinopyroxene is assigned to a cluster. In particular, we found that our geochemical dataset is best represented by 4 geochemical clusters that different in their chemistry. Essentially, we have 2 clusters: the cluster 1, the blue one, and the violet, the purple one, the cluster 2, that are chemically similar and shows the higher content of aluminum and titanium among all clusters. And then we have the most different cluster in terms of chemical composition is the 4, the yellow one, that it shows the highest values of chromium, magnesium, and calcium. And then we have the cluster 3 that is sometimes similar, is a sort of mixture between the cluster 4 and the cluster 1, except for the chromium content, aluminum, and calcium that that has the lower content of these elements. Interesting things, we can see that the most of the analysis were assigned to the cluster 2, the purple one, with the 56% of analysis. Then we have the 33% assigned to cluster 1, and only the 6% of the total analysis assigned to cluster 3, and only the 5% of the analysis assigned to cluster 4. But the interesting thing is when we look at the distribution of the compositional cluster in the sequence and also in the textural position of the crystals. In particular, we can see that the main differences are highlighted by the position of the cluster 3, that for the 66% of the times belong to the crystal core of the crystals, and the cluster 3 that is basically ubiquitous in the top of the sequence of the Pal D eruption. And okay, and then we have the majority of cluster 3 that is represented at the base of the sequence. Okay, so by coupling clinopyroxene liquid equilibrium criteria and also clinopyroxene liquid thermobarometric calculation, and also considering the kinetic effects such the undercooling on the compositional, on the governance of the composition of the clinopyroxene, I interpreted I tried to give a petrological interpretation of the 4 geochemical cluster. In particular, the cluster 4 may represents a crystallization in a hotter Shoshone-Uric melt, and the cluster 3 it represents that is, if you remember, is basically ubiquitous only in the top of the sequence, represents growth in a shallower and cooler trachyric melt. And then we have the cluster 2 that shows the highest undercooling, having higher titanium and aluminum, followed by cluster 1, and testify to clinopyroxene growth at higher undercooling condition. So I tried to put everything together, and along the sequence I studied how the concentration variance of that chemical elements that represents either growth in amorphic melts such as chromium and magnesium or high undercooling vary along the sequence. And if you can see here, the magnesium and chromium vary together in an opposite way of titanium and aluminum. In particular, when the variance of chromium and magnesium increase, that of titanium and aluminum decrease, and vice versa. And this is also correlated, obviously, as we said before, by the fraction of just to simplify the question, the things I plotted only the variation, the fraction of the cluster 4, that is the mafic one relative to the cluster 2. Basically, when we have the increase in concentration variance in chromium and magnesium, we have an increase of the cluster 4 relative to the cluster 2. That it means that the cluster 2 increases only when the cluster 4 starts to decrease, and vice versa. With this criteria, I identified at least 3 moments of mafic recharge in the sequence, followed by periods in which clinopyroxene growth at higher undercooling following magmatic recharge. And as you can see, also the concentration variance decreased from the bottom to the top of the sequence, and also the fraction of the cluster 4 relative to cluster 2. I interpreted these things in 2 ways. Like, for example, the first one is that the mafic input is important at the base of the sequence and then it wanes from the bottom to the top of the sequence, or alternatively the number of the crystals in the magmatic system that records the mafic inputs became progressively lesser from the bottom to the top of the sequence. And this is reflected also in the textural features of the deposits, that basically when we have the main input, the deposit of the sequence are mostly represented by undisturbed hash layers. And then when the inputs of mafic inputs became less important, maybe the magmatic supply became less important, and in the sequence there is the occurrence of intermittent pause of the eruptive activity. And the other thing is that the main input is probably the triggering of the rhyolitic subplinian event that is intercalated in the sequence. And indeed, another thing that suggests this is that the clinopyroxene that we found in the rhyolites are not in equilibrium with the rhyolites, but evidently are xenocrysts that are in equilibrium with amorphic melts. And then the last part of the history is represented by the PAL-D units that shows a completely different composition of clinopyroxene. And I interpreted this composition with an interaction between, there is a paper that I published last year that shows all the geochemical features of this eruption that in terms of wall rock is enriched in barium, shows a positively europium anomaly, possibly is caused by the petrogenesis of this melt is caused by the interaction between the shosonitic melts, recharging melts, and feldspar-rich crystal mash. So with this approach, I highlighted that the clinopyroxene that grow in that melt are different from the rest of the sequence. Thank you for your attention, and I would like to thank also the IAVSEI and Springer for supporting me to the conference with the travel grant. Thank you very much.
Thank you very much. Do we have any questions for Simone? I was wondering, so without the cluster analysis, would you have picked up those variations as well, or did it? Without the cluster analysis, would you have picked up those variations as well, or did it really come out just through the cluster analysis?
Just with the cluster analysis, yes, because the difference in some chemical composition are subtle. So without the cluster analysis, I would not be able to find that. Also, the textural position of the analysis is relevant to me, I think.
Okay.
Just a question, please. How many crystals you sampled for each layer?
About 15.
15.
Yes. I would like to improve the statistics.
Okay, it doesn't seem there are more questions, so thanks again, Simone, for both talks. And we move on to the next talk by Guillaume Carazzo on the dynamics of partial column collapse during the largest known eruption of Mount Pelée volcano.
It's okay, I think I can just use this mode. Sorry, it's my bad, I was not here at the beginning of the session. I should have checked that before.
Maybe you can run it in non-full full screen mode.
I think so too. So good morning, everyone. So today I'm going to talk about Mont Pelée volcano in Martinique Island, which is located in the central part of the Lesser Antilles arc. This is a picture of the volcano, and Mont Pelée volcano is located here on the northern part of the island. And this volcano is particularly interesting because it has a very rich eruptive history, as you can see here, which includes many dome-forming eruptions, including the famous 1902 eruption, which destroyed the town of Saint-Pierre, killing 28,000 people within a few minutes. But the volcano is also capable of doing much more powerful eruptions. As you can see on this sketch, field work performed during the early 80s shows that there has been at least 6 subplinian and plinian eruptions from P1 to P6, P1 being the most recent one. So today I'm going to be talking about the P3 eruption, and I'm going to show you how we do classical field work and field reconstruction from the observations and physical models, and how we can use that to improve volcanic hazard assessment. So this is the field area in Martinique, where you can see the volcano, which is the orange triangle in the middle of the map, and all the locations of our outcrops. We have 250 outcrops, and we found the P3 deposit at 120 locations. On the western side of the volcano, the P3 deposits are characterized by a thick layer of grayish-white pumice fall, overlain then by a stratified alternating layer of flow and fall deposits. And if you go to the eastern side of the volcano, the stratification disappears, but you can still see a change in color from the base of the deposit, which is kind of gray, and the top of the deposit, which is kind of yellow, and then above that you've got the deposits from the P2 and P1, which are the most recent eruptions. Okay, so just some grain size characteristics. So the stratigraphic section, we divided that into 7 layers of fall and flow. And this is a grain size measurement at a single location located along the dispersion axis of the deposits, at 3.7 kilometers from the vent. And you can see that the grain size distribution in 5 subunits of the first layer are bimodal and mostly dominated by lapilli-sized fragments, except at the very top of the section where fine ash start to become more important. And in the stratified layer, you can see an alternating behavior, a change in the primary mode of the grain size distribution from ash size to lapilli size. And you can see this rapid change here with the median grain size and the sorting coefficients in the deposits. The lithic content is quite the same along the column. It's about 20%, and the maximum lithic size systematically increases from the bottom of the first layer to the top of this first layer, and then becomes smaller above that. This is an observation that we see at every location. Sorry about that. Okay, just a couple of stratigraphic correlation. Like I said, on the western side of the volcano, you can easily recognize the P3 deposits due to the very stratified layers, which are beneath the most recent Pinion eruptions, the P1 eruption, and there is a thick soil that separates the 2 events because there is 1,300 years between the 2 eruptions. And as you go to the east of the volcano, the stratification disappears, and if you go very far away to the east and to the south, there is only fine-grained deposit, obviously, which correspond to P3. Okay, the isopack map. So we were able to draw several isopack maps for all the fall units and the flow units, and this is the cumulative thickness of the fall units. And you can see that the dispersion axis is towards the southwest, which is consistent with dry conditions in the Lesser Antilles. You can see also that there are lots of deposits all around the volcano. This is the same map but for the flow units, and you can see that the diluted part of the flows are mostly located on the southwestern flank of the volcano, whereas the concentrated part of the pyroclastic flow are channelized in 3 main rivers. And you've got a picture here of the dense part of the deposits and one of the big pumice block that you can find in this deposit. Okay, so from that we can extract the total volume of the eruption based on the thinning behavior of the deposit. This is a very classical way to retrieve the volume of the fall units. You can choose many, different fits to extract a volume for this layer, and if you do the calculation for all the layers, you will find out the total erupted volume of 1 cubic kilometer, including 1 cubic kilometer, including 0.3 cubic kilometer of fall deposits and 0.7 cubic kilometer of flow deposits. The isoplate now, based on the distribution of the lithic fragments in the field, so these are in millimeters, and we sample basically the lithic fragments at the base of the first unit, the top of the first unit just before the collapse, and in the first fall right after the collapse, and from that we can extract quite easily the maximum height of the column. And so this eruption started with a 28 kilometer high column, which rose up to 30 kilometers before collapsing, partially collapsing. And then the column was only 17 kilometers high after that. Okay, so comparing this Plinian eruption with more recent eruption, these are three different maps for the three eruptions. You can see that the most recent one, the P1 eruption, has a dispersion axis which is consistent with the P3 eruption, again consistent with wet conditions in the Lesser Antilles. The P2 eruption has a dispersion axis which is different, but which is consistent with dry conditions in the Lesser Antilles, so it makes sense. If we apply the same reconstruction techniques to the P1 and P2 eruptions, we can retrieve also the total volume of these eruptions, the maximum column height, and the associated mass eruption rate, and you can see clearly with this comparison that the P3 eruption is the most voluminous and the most powerful eruptions that occurred in Martinique in the past 5,000 years. Another interesting observation is the fact that all the eruptions at the beginning form the Plinian column that ultimately partially or even totally collapsed on the ground, forming pyroclastic flows channelized in the main rivers along the island. And to try to understand this behavior and why the column collapsed during the P3 eruption, we compare the field observation with predictions from a 1D model. So a classical and elegant way to deal with this problem is to run 3D numerical models in which you can vary many parameters and understand what are the controls on the column collapse and the partial column collapse. If you make a number of assumptions, you can reduce the number of parameters that really matter in the problem, and this is an example here with the result from 3D numerical simulations from colleagues, where you can see that the behavior of the column mostly depends on the mass eruption rate and the exit velocity. So we try to compare these predictions with our field observation. The problem is that we don't have exit velocities for this volcano, but we do have exhaled gas content for the phases that we can find in the literature. And so in this figure, which is an equivalent to this one, we compare the theoretical predictions made by a 1D model, which is the dotted line here, which separates the conditions for which the volcanic mixture will be able to form a stable plume and reach very high altitude, to the conditions for which the volcanic mixture will collapse on the ground and form a turbulent fountain. The comparison between the theoretical prediction and the field observation here, this is the data we have for the P3 eruption, so the estimates we have for the beginning of the eruption in white and the end of the eruption in gray, and you can see that the transition from the stable plume behavior to the beginning of the collapse of the column is consistent with the prediction of this simple, simplified 1D model. And you can also see that the collapse of the P3 eruption was mostly due to a decrease of the gas content during the course of the eruption and slightly due to an increase of the mass eruption rate. And this is a little bit different from other eruptions, including the P1 eruption in Martinique and the Taupo in New Zealand, for which the column collapse was mostly due to a major increase in the mass eruption rate. But overall, the three eruptions that I compare here to the theoretical prediction kind of work, which reinforces the confidence that the field reconstruction provides eruptive parameters that are not too bad. Okay, so once in the column collapse regime, so our interpretation of the very stratified layer we see in the field is that the column underwent a partial column collapse. And to try to better understand this partial column collapse behavior, we cannot use 1D model, unfortunately, because the model are not valid anymore, but we can use an alternative approach, which is based on laboratory experiment. And the next slide is a summary of all the results we got with laboratory experiment in which we injected hot mixture of gas and particle in a tank of air. And we were able to reproduce, it's not very clear on this picture, but this is a stable experimental plume for which we were able to measure the intensity of collapse, which I define as the volume of the material that flows back to the ground compared to the total injected amount of material in the experiment. So this is one n-member regime, and the second n-member regime is the total collapse of the jets, for which the intensity of collapse is 1. And between these two extreme regimes, we have a partial column collapse behavior. And the partial column collapse behavior, we can, with a very simple scaling analysis, we were able to collapse all the data along a single master curve by using a single buoyancy ratio, which I'm not going to detail, but which is basically based on the balance between the stabilizing and destabilizing buoyancy fluxes at the separation height, where some of the flow continues to rise, and the other part of the flow flows down to the bottom of the tank. Anyway, so the experimental master curve, which you can see here, is reported on this side of the graph as the gray shaded area. And you can see that it is compared to a number of explosive eruptions which underwent partial column collapse and for which extensive fieldwork had been done by many colleagues, and for which we have enough information to retrieve both the intensity of collapse and the buoyancy ratio. And you can see that the natural data compares quite well with the experimental master curve. And this red dot here correspond to the P3 eruptions, which again falls into the field defined by the scaling law and is consistent with other famous Plinian eruptions. Another implication of this work, especially for hazard assessment, I'm not going to talk a lot about that because my colleague Audrey will be presenting that tomorrow morning. Basically, the idea is to see if we can retrieve from the eruptive parameters we estimated from our field measurement and physical models, if we can reproduce the dispersion of the deposits in the field. And for that, you need a 2D model. We use the ASMAP model, for which you need a wind velocity profile, which is this one, which corresponds to an average of 40 years from the ERA5 database during the wet season. And so that's one input. The second input is obviously the volcanological parameters, which include the maximum column height, the total grain size distribution, and the total mass of the eruption. And this is the output of the model of a single run, and you can see that the map is not too bad compared to the field deposit, and this is a comparison of the observed ground load, versus the computed ground load, and you can see that the agreement is not too bad, suggesting that overall our field reconstruction is not too bad. Okay, so as a conclusion, I just want to show you the P3 eruption, which is the most voluminous and powerful event in Martinique so far. The 30-kilometer high column partially collapsed due to the combined effect of a slightly mass eruption rate and a decreasing gas content, which is rather common for Plinian eruptions. The intensity of collapse is consistent with our experimental result and field data from other eruptions. And interestingly, the P3 eruption, well, we consider that as the maximum expected eruptive scenario for volcanic hazard assessment in Martinique. And if you are interested in that, I invite you to go to the presentation by my colleague tomorrow morning, which will be about a revisited hazard map for tephra fallout in Martinique. Thank you very much for your attention.
Thank you very much, Guillaume. Do we have any questions? How frequent are these sort of very powerful Plinian eruptions at Montpellier compared to sort of the dome-forming eruptions, for example?
There is a magmatic eruption every 400 years in Martinique, and two of the three are dome-forming eruption, and 1/3 is a Plinian eruption, which, well, yeah, it's about that.
Yes, please.
It's more of a comment, but in the ice core, there's a big two-phase peak shortly after 29 CE, and until recently was thought it was Vesuvius, but it's been proven it's not Vesuvius. So I was just wondering if your peak reduction could be the candidate, might be something worth looking at.
Yeah, well, the age of the eruption is surprising, and it's based on an average of 12 or 13 radiocarbon measurements, but the error on the age is 20 years. So it could be 20 years less or more, but I really like this value, so I keep this one on the slide.
It's not like the ice core are exactly great. Food for thought.
Thanks.
Any other questions? Okay, so this is not the case, so thank you very much, Guillaume. And we move on to the last talk of the session by Thor Hanstein on the role of a pre-eruptive fluid phase for the volatile budget and atmospheric influence of large explosive eruptions in Central America.
Okay, good morning, everybody. Can you hear me? Yeah, okay, nice, hard to hear from up here. Great session. So, no, wow, I did exactly what I shouldn't do. It's all about the buttons, right? Technology. Anyway, I'll take you back into the depths of the magmatic systems again. We were now up in the stratosphere more or less, and I'll take you back to Earth. And my comment now is that everybody's talking about the magma chamber fluid phase, but actually nobody has seen it. So I'll try to take you there now. So it's all about the criticality, or actually what happens before the eruption. Because I'll take the first conclusion first. What we've seen in the whole of Central America, because this is a regional study, is that actually every of the super large eruptions, VI5 and up, had fluid oversaturation well before the eruption started. So what it's about, I think I maybe will do it here. Yeah, it's about these guys, the fluid inclusions. So actually, these are very, very less prominent than the melt inclusions, which you have in all these plagioclases in the subduction zones. So from our experience, they are about 3 orders of magnitude less numbered. They are 3 orders of magnitude less in abundance than the melt inclusions, and that's why it's really difficult to find them, right? So this is my best one. This is about 35 micrometers across, and I think I'll do it here because I fuss up with the techniques here. If you see here, so this is in plagioclase, so this is glass actually. This is actually trapped bubbles from the melt, so this is glass, and this is meniscus, and this is water around, and this is actually a CO2 bubble inside it, right? Okay, so the background, Stefan Kuterhoff and others did this more than 10 years ago, the regional study, 1,200 kilometers of arc, and in this project here going from Guatemala in the northwest to the end of Costa Rica in the southeast, about 1,200 kilometers, there are about 93 Plinian eruptions over more than 300,000 years which were investigated, and this was followed up by marine cores from, I think, 3 cruises, Stefan, about 10 years ago from the German vessels Meteor and Sonne, and there were a total of 56 cores used for these studies. And you see this prevailing northeasterly wind direction brings actually most of the material into the sea, and that's why counting all the volumes together, you get a factor of 2 or 3 more volume typically for these eruptions than if you just study them on land, and I think this is a pretty impressive figure. So there are 15 volcanic complexes in this area by the diamonds here, And because of the fluid inclusions, which occur very seldomly, we were able to pick out 6 complexes with large explosive eruptions, 7 eruptions from 6 of these complexes, right? And I'll take you to one exceptional one, Los Chocoyos on the left, about 85,000 years, which is really big guy. And here is the more typical one, Chiltepetefra, about 1900 years on the right, which is really more typical. So it's about pyroclastic flows and fallout deposits all together. So this is what it looks like in the field. And of course, if you want to study the inclusions, you need the crystals. They are typically not crystal rich, these guys. Anyway, we need some good quenched clasts, because if not, the fluid inclusions will die. So we have mostly fallout deposits where this method actually functions. And you all know this, the petrologic method. You look at, in this case, plagioclase, and you look at the nice melt inclusions, and you analyze anything you want in them. Water, CO2, the halogens, and bromine. We did this also for a few inclusions, and you just know the masses before, the erupted masses, the dense rock equivalent, and you look at the concentration differences, and you make the budgets based on this. So this is the classical one, which everybody knows, right? And go on from there, the theme of today, the magmatic fluid inclusions. And you have them in some unique crystals to some extent. This is an exceptional case actually from Los Chocoyos, where you can actually see these guys up to 70 or 80 micrometers thick, but you don't really see that it's one in a millionth or something like that. Typically you have them like this, and you please note the scale, 20 micrometers down here, and they are typically single primary or on healed microcracks like this, and the typical size are 5 micrometers or less. So this is really very challenging to look at this. And the main points is what is here written to the right. I mean, if you have magmatic fluids in eruptions like this, you find inclusions, you know that this system was fluid oversaturated before the eruption, right? So this is no doubt about it. And the other thing is that you can actually study the composition of these fluid inclusions relatively easily under the major elements with a very traditional method. It's a basic method, but it's very effective, which is the microthermometry. Right, so these are the typical ones, actually the big ones of the typical ones which we're able to study. So please note the bars again, 10 to 5 micrometers down here. And what you typically see, I said this in the beginning also, so you just take home this also. There are small portions of glass around here. So obviously in this mostly silicic melts, what happened is that you have bubbles which are being caught with a little bit of melt with them. So we only used those with 0 to about maximum 10% melt, because if you have more melt, you will falsify your fluid signal, actually. And what you see here, all the cases, you have the liquid phase, which is the wetting phase, so this is around the inclusion. If there's melt or not, it doesn't really matter. And you have the vapor bubble, which you can see minor amounts of CO2 in it. And then it's a water-dominated system with small amounts of CO2 in them. So this is the apparatus. Somebody think it's old-fashioned, but I think you need to use the basic methods also before you use the high-tech ones. We also did laser ablation on this, but you know the masses of these systems are so extremely small, so even with the best laser ablation technology 3 years ago, we couldn't actually get the trace elements of this. So it's for the major elements today. So what we do, because these are very fragile systems, actually these ones in the plagioclase, which the plagioclase, like you know, have a good cleavage, so you cannot really heat those. And the trick is you need the composition of the system, which is basically seawater composition. We did this with microthermometry, and you have to estimate how much CO2 is in there, and then you can actually, based on this, do barometry, very precise barometry, if you know the composition and the volume proportion, and this is the trick. So it's a very basic method. And averaging everything which we have here, it's about 90% water, very roughly 5% CO2. This is the biggest variable, but the max is less than 10%. And actually, we found CO2 in all these felsic eruptions. And it's NaCl, it's like the salt you have on your egg in the morning, right? So it's quotation mark NaCl, because what you can measure with microthermometry is the freezing point depression, is the chemical behavior of the system. So you don't know if it's a chloride or if it's another salt, right? But it is dominated by salt. So that's the assumption being put into this, right? And these are the densities from visual estimates. Oh, okay. So it's again Microsoft, but I think you can see the histograms more or less. They would, on my screen, there are some signs here in the background, so you can actually see the density maxima, but I think you can see it like this also. So from Guatemala, we have from the Atitlan and Amatitlán complexes, from El Salvador, Coatepec, Ilopango, and Berlin, and from Nicaragua, Chiltepe, which I showed you in the other figure. So just jump to what this is about in the end. It's about pressures and about volatile budgets. So I go to the fluid inclusion barometry based on this. And what is very nice, if you know the composition and density, you have very nice equations of state. This is known very well through theoretical study, but actually basically this is done since a lot of years by the chemical industry. CO2 and water is very, very well known system. So you have equation of state, and you can extrapolate your measurements at low temperature to actually magmatic temperatures. So this is the formulation of Ron Bakker and others in 2010, which is a very good one, I think. And these are the densities, and the curves are so-called isocores, the isocomposition, isodensity actually lines in PNT. And if we put together all the work we did, the typical range of pressures from the fluid inclusions between 130 and 250 MPa. And this is actually, and this is no by chance thing. The new paper from Rasmussen and al. From one of the leading US groups from the Aleutian Arc with other methods actually so exactly the same range. So I think this is a typical mature subduction zone range for the starting point of large catastrophic eruptions. And to bring this to an end, to make the budgets, you need, of course, to compare to the data for each of the single eruptions. And then, in this case, we used the Papal et al. 2006 formulation for solubility. I say water here, but it's actually water and CO2 salt system, which we use in this case. Salt, because it's only like less than 5%, doesn't really matter. But anyway, for this pressure we obtain with the fluid inclusion barometry, we get between 4.2 and 6.3 weight % water at magmatic conditions in the magma chamber at fluid oversaturation, right? So what we do after that, we know now that we had the fluid downstairs, and we now know the original fluid content. We measure the chlorine content, assuming that everything is actually chlorine. This can be discussed. And of course, you extrapolate everything to the erupted magma volume, which is known from Steffen and others. And then you compare this data again on the chlorine and water to the petrologic method. So this is the whole story of it, actually. Some people like tables down here on the right. I don't like them so much. I like histograms and figures more. So that's why I plot it like this. So here are the fluid inclusions in green, and the petrologic data, the classical data only for chlorine, compared for each of these 7 eruptions. And please note that this is a logarithmic scale, because each eruption is, of course, very different. So I had to put this logarithmically so you could actually follow it. And what we see is only in 3 of 7 cases you have a pretty good match, actually far within error bars. And these are the 3 ones here. And actually most of them, which is no surprise, the fluid inclusion estimates give much, much higher volatile estimates. And please note again, this is a logarithmic scale, right? So it's really a serious thing, like we know as volcanologists and petrologists. One hint, which is very logical, is of course that the best fit is where the melt inclusions, coexisting melt inclusions, actually have the lowest sulfur. So where you have not only pre-eruptive, but early pre-eruptive degassing, bringing down the sulfur, you don't falsify the fluid inclusion composition so much, because the sulfur component is mostly away from the fluid before, right? So we can discuss this later, but anyway, the best fit is for the relatively low sulfur magmas. But on the other hand, all these magmas have lost most of their sulfur prior to eruption. We also know that from petrology. So it's a draw, I think. So I'll just take this to an end. So in all these systems, actually, there were about twice as much, where we only found like single inclusions. We've never seen a big eruption in Central America, which is not critical or not fluid oversaturated before eruption. And the middle one, it's something which, of course, will be discussed. If you believe this method, you can actually estimate the chlorine contents just from doing microthermometry and doing budgeting over the fluid inclusions. And then what we learn from this is, of course, that the degassing budgets from the petrologic method can be very much too low. This is what we know for a long time, but maybe this is a hint where we should go. And one thing in the end, because this is what we could not do with the fluid inclusion so far, this is especially serious for sulfur and also for bromine, which we worked on in a lot of systems, because the volatility and actually the partitioning of bromine into the fluid phase is much, much larger than that for chlorine. I don't want to discuss this today, but actually if these chlorine masses are right, actually we have much, much more climate effect of these eruptions due to the bromine that we could ever hope for, in quotation marks, right? So thank you very much.
Thank you very much, Thor, for this interesting talk. Any questions?
I do have a question. Yeah, very interesting talk. Well, clearly, I mean, the fluid inclusion are really, really difficult to find. So how many of them you need to have a good estimation?
As many as you can. I mean, it's about normal statistics.
Yeah.
So actually, we excluded the eruptions where we found only like less than 10 inclusions. So I mean, you have to search for months. This is actually the petrography work of this is more or less 2 years, a long arc, right, just to find the inclusions. And then you have to have special preparates. I mean, actually, the thin section basically kills the fluid inclusions because you polish them away, right? Yeah. So we make thick sections, about 100 micrometers thick and doubly polished, so you can actually find them only in the thick special sections. So it's a lot of work.
It's a lot of work, yes.
It's a lot of work, yes.
And you look at, I mean, only in plagioclase. How about the other clinopyroxene, well, pyroxene or olivine? I mean, is
yes,
any...
okay. These are silicic eruptions mostly, so plagioclase dominates. And quartz, you only have in a couple of them, and it's about statistics. I mean, quartz like the fluid inclusions better, to put it that way. But if you only have a few quartz crystals, it doesn't help you. So that's why we use plagioclase, right, to find the inclusions at all.
Any other question?
Did you use Did you use Raman? Did you use Raman spectrometry to analyze your fluid inclusions?
No, because these are water-dominated ones. I mean, in a few we saw probably extremely small, I mean, in per mil area sulfates, right, which have been, which we can demonstrate. But for the water phase, Raman is okay, but it's not really quantitative for these types of fluid. And for the CO2, actually you can do this very well with microthermometry. So actually the gas phase is really dominated by CO2. So I think actually the major elements are relatively well constrained except for sulfur. So this is the drawback. We couldn't really quantify sulfur.
Okay. There's one question.
Thank you very much.
Thank you.
Just a question about the chlorine and for the low pressures. Have you considered that there might be a brine also dissolving, and that maybe not dissolved in pushed the atmosphere but stayed in the ground?
Yeah, sure, but all these are critical eruptions. So I mean, you had fluid oversaturation during crystal growth. So I believe if you have VEI 5 to 7, the fluid phase gets blown out, right? So, but of course, the pre-eruptive situation is a very challenging one. You know the best about this. So, but yeah, I believe in these cases with the high mass eruption rates that you actually pump out most of the fluid phase at the same time as the large eruption.
Okay, there are no more questions. So thanks again, Thor, for your talk. And this actually concludes our session. So thanks again to all the speakers and everyone who was coming here to listen to the talks and everybody who asked questions. So thank you very much. And we can now go to the coffee break and discuss further. Excellent.
Thank you.
because I have to drive another,
So, good afternoon. This is the first part of a joint session out of 4 original submitted proposals for sessions. So it's unmanned robotic autonomous platforms on volcanoes for research, monitoring, and rapid crisis response, submarine volcanism, volcanic hazards, seafloor monitoring, public awareness, extant and extinct shallow submarine, hydrothermal geobiology laboratories, etc., and innovative and cutting-edge techniques for geological exploration, etc. So, a huge title for this session, and we have a first part now and a second part in the late afternoon, and we start now with Danilo Cavallaro, and he's presenting a morphostructural analysis of the Graham volcanic field offshore southwestern Sicily by means of bathymetric data and ROV images.
Okay, thank you. Good morning to everybody. So, in this presentation, there is no correlation with the name of the speaker of the plenary section before, because in this presentation, I will talk about morphostructural analysis of the Graham volcanic field. And I will present the result of a work that is a mixing between volcanology and marine geology. The study area is located offshore southwestern Sicily, within the Sicily Channel, which represents the foreland sector of the Sicilian part of the Apennine Maghrebian Fold and Thrust Belt. And the Sicily Channel is was characterized by 2 main geodynamic processes acting at the same time, that are the New Guinea north-south oriented collision between African and European plates, and the northwest-southeast oriented continental rifting that started in Plio Quaternary. These 2 geodynamic processes led to the formation of a north-south oriented transfer belt here that is made by 2 different transpressive, left transpressive faults. And along this transfer zone, there are evidence of old and recent volcanic centers that are here in red dot, and some other sedimentary banks that are in yellow. Along this transfer belt that is called the Capo Granitola Sciacca Fault System, that is 200 kilometers long, we recorded high seismicity both inland and offshore. Offshore, around the grabens of Pantelleria and Linosa, up to Linosa Island, that is a volcanic island are about 100 kilometers offshore Sicily, but also inland, especially along the Bellice Valley, which was protagonist of a strong earthquake in 1968. But as you can see in the middle, there is a large seismic gap exactly in correspondence of the Grand Bank that is the study area. The database is made by high-resolution multi-beam sonar data acquired with a Kongsberg 200 to 400 kilohertz that permitted to produce a very high-resolution marine digital terrain model with a resolution of 5 meters, increasing to less than 1 meter for some particular areas of interest. And together with the multi-beam data, we used some videos and images acquired through a remotely operated vehicle, Pollux Second. This is the study area. It is a morphological high with some 600 kilometers square of area, square kilometers of area. It includes the Nerita Bank, which top is located 50 meters below sea level, but it is a sedimentary bank which formation is due to the transpressive tectonic due to these two faults. Southward there is the Terrible Bank, that is another sedimentary bank with the top at 28 meters below sea level, with some volcanic evidence on the summit, while on the western area of this relief is the Gram volcanic field, which consists in some 10 volcanic cones that are aligned along a north-south trending and 12 kilometers long belt, lying in water depth between 150 to 250. These two cones represent the Gram Bank, that is the name of all these volcanic field, and the smallest of these two cones is the famous at least in Italy, the famous relict of the Ferdinandea Highland, which was a short-lived volcanic island formed during the 1831 Sarceian type eruption that lasted 6 weeks and was preceded by high seismicity, which was felt also along the Sicilian coast. After this eruption, this eruption produced an island made by poorly consolidated tephra and tuff rocks that was 6 meters high and 600 meters large. Here you can see a paint the time, but you have to know that this eruption led to a very important international dispute because it was born in the middle of the Mediterranean, so I'm talking about 25 miles offshore Sicily, so in international water. So there was a dispute between France, England, and Italy. This is why this island has different names like Giulia, Gram, and Ferdinandea. I used the Gram name because it is the international name, but this dispute ended when 5 months after the end of the eruption, the island was completely eroded by the sea, and now it is 9 meters below sea level. I would like to show you also these blue stars that represent the location of the ROV dives, and also this in brown the location of pockmark field located around the area. So the present day morphology of the Ferdinandea shoal, as well as of all the cones forming the Gram volcanic field, is the result of the interplay between different geological processes acting both in subaerial and submarine environment, like volcanic and tectonic process, wave erosion, mass wasting activity, in relationship, of course, with sea level change. So the focus of this research was to get a detailed analysis of the Gram volcanic field by using some morphometric parameters, like the shape of the cones, summit depth, diameters, the height of the cone, slope gradients, volume area, and, this is most important, the depth of summit abrasion platforms and depositional terraces, if present. Taking also into account analogies with other submarine volcanic cones worldwide. First of all, Sarsay Island, located offshore Iceland, and its 3 volcanic satellites, Surtla and other 2 names that are very difficult to pronounce. So the research goals were to confirm the monogenic nature of this volcanism, to prove the interaction between volcanism and tectonics, and to infer the age of the volcanism that originated the Grand Volcanic Field. That was very important also for volcanic risk assessment. Here you can see all the cones that were grouped in 4 different clusters using a spatial distribution of the cones. And now I will show you a sequence of these clusters where you can see that some cones are point, like this one. You can see the profile here. Some other are flat-topped. So that means that they were eroded by sea waves. Some of them present blocky faces at the base, suggesting the presence of very important mass wasting process. Some cones are isolated, like this one. Some other form coalescent cones, and probably they were produced during the same eruption. I am talking about small eruption because the volume is very, very low, very small. While this is the C2 cluster that is the most important because it is formed by these 2, so the Ferdinandea and the S5, that is the largest submarine cone of this field. It is more than 1.5 kilometers large, and it is the only one showing a lava flow at the base that you can see also imaged in this picture. Took from the ROV, the ROV. Look also the presence of the terrace in the middle of the S5 cone. This is the high-resolution image of Ferdinandea, the youngest, and you can see how steep are the slopes, and you can see also the presence of a depositional submarine terrace here, a summit terrace here with the ripples on top, took by the image by the ROV, suggesting the presence of very, very strong erosive activity, still acting on this cone, and also the knoll, so the neck of this cone that formed the island on 1831, that is now completely colonized by marine organisms like gorgonians and so on. Here is the table where we presented all the morphological parameters, like the height of the cones. It's around 100 meters or more for each cone. The volume, as I said before, is a small volume, and also the average slope gradient that could be important to assess also the age of the cones. As in fact, as you can see, the slope gradient of the Ferdinandea is the highest, presents the highest value. One of the parameters was also the basal ratio and the shape of the base of the cone, which main direction was northwest, southeast. So this represents the maximum elongation axis of the basis of the cones, while here you can see the main direction of the maximum diameter of the cluster in which they are grouped. So to confirm, to infer the age of the volcanism, we assumed that the past conditions were similar to the present ones, a uniform rate for tectonic uplift during the post-LGM, and we assume that the contribution of tectonic deformation and subsidence affecting the field was negligible. This is because the growth rate in Plio-Quaternary of the area was 0.2 millimeters per year, and because also the compaction, so the subsidence due to the compaction was very, very low. So, on the basis of the present-day maximum depth of the summit abrasion terrace, that is 28 meters below sea level of the Ferdinandea shoal, and taking into account the trend of its erosive rate compared with the other shoals offshore Iceland, we can put the local wave base level, that is the water depth behind which wave action stops to work, at 30 to 35 meters below sea level. So this value can be used as a proxy for reconstructing relative sea level position. In this way, any submarine structure shallower than 155 meters below present sea levels was potentially affected by wave erosion during the last glacial maximum, if already present. 155 means 125 is the depth of LGM plus 30, that is the local wave base level. So this is a picture where you can see the level put at 155 meters below present sea level. So you can see that the cones with a top shallower than 155 meters below sea level with a pointy shape are for sure younger than the last LGM. Otherwise, they should have been flattened by sea waves. So they are located here, S3, S6, and S7. The other 5 present a summit terrace between 90 to 100 meters below sea level, so they were likely eroded during the transgressive phase following the LGM, so, and probably during the younger Dryas, when the sea level was 60 to 70 meters below the actual one, and they are located here. S5 is more complicated, but I can say that probably it was partially eroded during the younger Dryas because it is the largest of all the field, and after was flattened when the sea level was 20 meters below the actual one, because we saw a summit terrace located at 50 to 60 meters. So in conclusions, we can see that the distribution and shape of the cones within the fields provided important information insight into the interaction between volcanism and tectonics, because the alignment of the cones, north-south, and the main axis of the cluster in which they are grouped, northwest-southeast, are consistent with those of the main tectonic structures in Sicily Channel. The analysis of the cones proved the monogenic nature of this volcanism, ruling out also the legends about re-emission of the Ferdinandea Island in the past. And the analysis of morphological features, such as the cone shape and the present depth of the terraces, allowed us to infer a post-LGM age for the volcanism forming all the field. Okay, I conclude.
Thank you. Unfortunately, you used the entire time, so no questions possible. But you can go afterwards. Okay. You can go directly to the other. Yeah.
Alrighty. Next, we have Professor Kenneth Rubin from the University of Hawaii, talking about the eruption history, caldera formation, hazard potential at Niuahatihi, Tahi, submarine volcano in Tonga. So take it away, Ken.
Aloha, everyone from Hawaii. Yeah, I'm going to talk to you about a very large submarine caldera volcano, sometimes shown on maps as Volcano O. That's an alternate name for it. And I am speaking on behalf of a group of co-authors that you can see there on the bottom. And I'm going to focus on Back Arc Basin that is adjacent to it in this area. Is the fastest opening basin on the planet. And the Niuatahi volcano has always been really interesting to our group, who we've been working in this area for about 15 years. There's a whole bunch of different active volcanoes that we focus on, and we've yet to have an expedition focused on this specific volcano. But every time we go, we spend a little bit of time there, and I've put together that kind of information with the hopes that we can now do a campaign that's dedicated to studying that particular volcano. So this is the bathymetry in the area, and Volcano O, or Niuatahi, is this volcano here in the center. It's a very large caldera volcano, about almost 20 kilometers across. This is some of the other features in the area. You might be familiar with West Mata volcano, which is a very active submarine volcano erupting bonanite that we've studied. There's Spreading Center off here to the west, and there's the volcanic arc off here to the east. And interestingly enough, this part of the Tofua Arc is very anemic, volcanically speaking. It's very tectonized, it's hydrothermally quite active, but I hypothesize that this Niuatahi volcano, which sits adjacent to but behind the arc, has somehow stolen the magmatic flux from the adjacent arc. In a recent paper, Anderson et al. Looked at structural domains within this region and isolated a particular area there shown in purple, which has Niuatahi as well as the Mata volcanoes, as having different orientations and structures that seem to imply that it was formed not in the back arc proper or along the arc, which are shown in blue and peach respectively, but it's in its own terrain. And the terrain is probably further subdivided into multiple microplates. So having such a large and potentially long-lived volcano in this setting is additionally curious. This is just a brief video showing you what the volcano looks like. We're flying in from the south towards the north, and you can see it's a large, complex structure with concentric rings in its remnant high, and it's got that small little cone in the center, which is an active part of the volcano known as Mohotahi. This is just another map showing you Niuatahi volcano oblique view and its relationship to West Mata, which is about 25 kilometers away. And that's the name of the what we infer to be the most active part of the volcano. I'll show you some images of it in a moment. I also just want to point out that there are a lot of concentric structures, both in the remnant high as well as on the caldera floor of this volcano, which suggest polygenetic and probably multiple episodes of caldera formation and filling at this site. There's also a lot of active hydrothermal activity, which I'm not going to focus on here today, but this is considered one of the best resources for the Kingdom of Tonga as exploitable deposits. So this is a plan view of the map of Niuatahi, and I just want to highlight what a profile going over the volcano, including its intercaldera cone, looks like. And you can see it's very complicated structures, very steep sides, inward-facing faults on the caldera. You can see the impact of these concentric rings on both the caldera walls and caldera floor. And this is just a few profiles across the caldera walls to show you the compound structures that it presents. So, there's various ways in which calderas can form, and we've yet to do a full detailed analysis of the caldera walls, both the deposits and structures that are present there. But I think our argument is that this is either an E or perhaps a D style caldera that has been filled and drained multiple times. Probably not a trapdoor setting like some other submarine calderas, because there isn't any significant slope to the caldera floor. These are just a few pictures from the summit of the inner caldera cone. It is very actively degassing with sulfur-rich, very acidic vapors. The water clarity is pretty hard when you work there. This is from an ROV dive in 2012. There's a thin patina of sulfur deposits pretty much everywhere. This is also up at that cone when the currents are blowing that material away from us. And this is a view of that sulfur deposit is very, very thin. It sits on extremely rich and fresh dacite deposits that are primarily pyroclastic We do see, this is down on the flanks, large bombs. We see lava flows. The size of the cone has not changed dramatically in the 10 years we've been going there, but we see evidence for changes on the cone and continued activity there. Now, when we think about the volcano of this size, we imagine that there's probably extensive pyroclastic activities, whether this is of the form of something like a submarine fall deposit or even something that breached the ocean surface, or they're more in the form of surges and flows. We don't really know, but this is a site that we visited about 10 kilometers to the northwest of the caldera, and this is this entire deposit is mantled by pelagic sediments, is probably not younger than about 500 years old, but the deposit itself is several meters thick and is full of lapilli-sized fragments, which we sampled here, which are compositionally the same as what we find erupting within Niuatahi. We also find in sites not too far away from that a welded ash deposit, which implies that it was deposited hot. It's lithified. It's only about 15 centimeters thick, but it's again compositionally very similar to what erupts at Niuatahi. Now, this is just an image from West Mata volcano showing you several meter thick tephra deposit that formed during its last eruption in 2017, and showing you the kind of tools that we use to determine the thickness and to sample these things. Once we, design a campaign to go to Niuatahi, we expect to do this same kind of sampling there. Now, I submitted this abstract back in, before when the conference was planned for 2020, and we didn't know Hunga Tonga Hunga Ha'apai volcano was going to have such a dramatic eruption earlier this year, but it did. And the combination of the extensive ash fall and surge deposits, as well as the tsunami, highlights the importance of these kinds of volcanoes for submarine-related volcano hazards. And of course, this volcano, we've known it's erupted multiple times this century, but there's no monitoring at the volcano, just like there's no monitoring at Niuatahi. And boy, wouldn't it be nice to be able to predict these things ahead of time by knowing more about these volcanoes. So this is just for comparison, a profile across Hunga Tonga Hunga Ha'apai. That bar is about 16 kilometers. This is topography, bathymetry collected before the 2022 eruption. I think you can see the size of the volcano and the caldera relative to it. It was about 200 to 300 meters deep. After the volcano, the data is not yet available, but I've heard anecdotally from folks at NIWA and elsewhere that the caldera has subsided down to about 600 meters, which means a 400-meter difference, which makes the present caldera depth more similar to what we find at Niuatahi, although the dimensions of it are still a lot smaller. And this is just to remind you what Niuatahi looks like, and a little bit of a comparison. The volcanoes are roughly the same diameters, but Niuatahi is dominated by a much larger caldera with a deeper caldera floor. And I think the idea that this was formed and evacuated in one large eruption or multiple eruptions is something that we still need to test. But the potential for very, very large eruptions, significantly larger than what happened at Hunga Tonga Hunga Ha'apai, certainly exists. So this is just an oblique view of the volcano and where it sits relative to sea level. I just want to show you a quick reconstruction that I made of the potential size. I realize this is a very back of the envelope kind of calculation, but taking the slopes of the volcano and projecting it back upward, we look at something like that might have been as much as 2 kilometers above sea level at some point. And at that state, it would have had a volume of about 300 cubic kilometers. The volume today is something about 35 or so, which makes a difference of something like 260 or 265 cubic kilometers. So there's a lot of missing material. We'd like to know where it is. One of the things that you might be aware of is that Bob Ambly and I have been working on very large, in fact, the world's largest known dacite lava flows that are in this area as well. There's 2 groups. This group in blue that are associated with Niuatahi are relatively small and sampled and compositionally similar to Niuatahi. There's these other very large lava flows in the area that are compositionally distinct, so probably not erupted from Niuatahi. But even with the dimensions of these flows, many, many tens of kilometers long, and using the thickness measurements that we've made there, these lava flows are something like 3 to 5 cubic kilometers. So there isn't any evidence that the caldera draining at this volcano event was something associated primarily with effusive activity. That's like 2 orders of magnitude less volume. So I also just want to spend a moment talking about tsunamigenesis and potential tsunami hazard. We don't know how often or when the caldera floor experiences vertical motions, but it's certainly within an ideal depth range to present a significant tsunami hazard. These are concentric 100-mile radius circles around Niuatāhi volcano, and you can see that a lot of the areas of Samoa, both American and Western, Walvis and Futuna, and other parts of Tonga are in this zone, potentially within an hour or so travel time of a tsunami. And just by comparison, this is where Hunga Tonga, Hunga Ha'apai sits down near the main island of Tonga, which is Nuku'alofa. And just to kind of zoom in, there are islands, all throughout this area. They don't show up so well in Google Maps, but for instance, Niuafo'ou is populated, as are these 2 islands here, as well as Samoa, and they're very, very close. They're something like 100 kilometers away. So just to talk for a moment, population density is relatively small in the Pacific. I think we all understand that this is one of the areas on the planet where there isn't a lot of land mass, there's a lot of ocean, but it's also important to recognize that these islands are very small, and many people live in very, very dense communities, primarily at the coastline. And so the population density in and around this volcano is pretty significant. And off to the side there, I've noted that, depending on how far of a radius you want to take from the volcano, there's, upwards of almost 500,000 or, nearly 1 million people that potentially live within the hazard zone of, in a short time frame of a tsunami from this volcano. And just to kind of put an exclamation on that, this is the tsunami propagation from an earthquake, a tectonic earthquake that happened on the Tonga subduction zone, about 50 kilometers away from Niuatāhi in 2009. And it had devastating effects in southern Samoa, and very little forewarning because there was no monitoring in the area. So my last slide here, I just want to make a pitch for, there are lots of volcanoes. Niuatāhi is a large one, perhaps the largest, but there are many other active submarine caldera volcanoes, both in the Tonga-Kermadec region, elsewhere in the Western Pacific, in the Caribbean, in the Mediterranean, that likely represent underappreciated hazards. They're not monitored. They have very infrequent campaign-style studies at them. We need, collectively as a global community, to put more effort into understanding these volcanoes. And so I and some other people are trying to organize some kind of group effort to start talking about what we can do to help these countries that have these volcanoes to beef up their monitoring capability so that we understand something about these events before we just happen to see a pumice raft or a tsunami deposit, as is shown there in the bottom. So this is just a summary of what I told you. I'm not going to go through it again, but just to highlight that Niuatāhi is an extremely large volcano in an unusual rear arc setting that has the potential to represent significant eruptive and tsunamigenic hazards in the region. Thank you.
Great presentation, Professor. Thank you very much. We have, since you stayed right to time, we have time for questions. Do we have any questions in the audience here or online? Okay. I don't see any. Professor, as somebody who's here as an engineer and not a volcanologist, I have to apologize to the audience. I'm probably going to ask a stupid question, but what do you think is the probability in, say, the next 50 years of a major event here?
Yeah, that's not something that we have enough data. We don't know anything about recurrence intervals yet, how long this volcano has been in existence. So I really can't say. I would say that the collective hazard of the 10 or so similar volcanoes along this section of arc stretching throughout the Kingdom of Tonga is probably highly likely that we're going to experience an eruption from one of them each decade, because that's what we've seen in the past at various other volcanoes along here. Which one it is and when it happens, we don't know because they're not monitored.
Yeah, thank you. Any other questions? Again, Professor, thank you very much. Great talk, and I, for one, hope that you get lots more funding.
Okay, so then we can continue with the next talk. So it's yeah.
Okay. This is Dr. Florian Schwandener, who is the chief of the Earth Science Division at the NASA Ames Research Center, not deputy chief. He's going to be talking about detecting volcanic CO2 emissions hidden in tropical volcanic forests using a fixed-wing small UAS.
Thank you. It's my pleasure to be talking about this. This research is ongoing, and there's many updates, but since we submitted this abstract and didn't change it, I stuck to the collaborators, co-authors that are here, and not the ones that are not here, who have new results. It's a so far almost 10-year ongoing teamwork, international, to attempt to tease out how we can use plants and their responses to elevated CO2 from volcanoes to enable a proxy early detection mechanism. And at the same time as I'm talking here, I'm convening another session in the Thera Hall. And I had to apologize to the speaker who's talking about the exact same topic. So this just shows that it's an overwhelming response to this conference, that we have so many people coming, that we have overlap. I think it's fantastic, and I'm learning so much at this conference so far. So let's talk about this. In principle, this is nothing new, but I often talk to ecologists and to atmospheric scientists, climate scientists. So the way I look at volcanic unrest is that it goes, like all natural disasters, through very basic phases that all these disasters have in common, and that is having a period of repose of not very much happening, the baseline state, a potential building phase where we start to build the potential to have something happen, and then an unrest phase and an event, possibly, not always an event. And these triggers that describe these transitions are observed in volcanic CO2 signals, in some cases months to years before an eruptive event. And conceptually, we understand these as magma intruding in the crustal depths between 8 to 12 kilometers and starting to degas fresh CO2, and that may express at the surface. So this phenomenon was the topic of a white paper we wrote in 2015 that had a lot of underwriting on the US side, at least, and some Italians and some Icelandic folks that contributed to push the early detection threshold to earlier than before. So that's the white paper, and it was informed by and has informed community consensus papers, including the Decadal Survey in the US by the National Academy of Sciences in the US, and several other documents. Now, we cannot instrument all volcanoes for CO2. It's an intense effort. I've done this at several volcanoes for dense time series, and it takes a lot of upkeep, a lot of funding. And while I would love to do this at every volcano in the world, it's not really feasible to do so. So remote sensing can help fill some gaps there. It doesn't replace the ground-based work, but in an observation system approach augments it. And so about 13 years ago, I started looking at GOSAT, that's a Japanese platform and instrument that observes CO2 in the atmosphere and has a fairly dense time series. We can get up to 2 observations each 3 days. And then later OCO2 launched by us at NASA in 2014. And that has a 16-day cadence, so it's not exactly a dense time series, and we cannot look through clouds. So what that means is that we only get maybe twice a year, 4 times a year, an observation that's meaningful over a given volcano, if we happen to pass over it, because it's not a wall-to-wall measurement. It's a thin strip of data. But we were lucky enough to get some measurements that actually work, and that's the lowermost left figure over Yazur. While it had an uptick in activity, we were able to image fragments of the plume, inverted that, and saw an enhancement, published it in Science. A lot of excitement, and then a lot of dampening of excitement. No, we can't do this at every volcano. It's not really possible. We just were able to show that it is possible to do so. Looking at, so on the left is that Science paper from 2017, the main problem we have with remote sensing of CO2 is that we look through an atmosphere that is stuck full of CO2. Thanks to us, it's getting more so. And we're measuring all of that CO2 that the light from the sun passes through the atmosphere to the ground and back to the sensor. So we're seeing the atmosphere twice, and then we get this little signal from a volcano, even if it's a gigantic signal on the ground, that maybe causes an averaged concentration, atmosphere average concentration enhancement of 1 ppm. That's our rough detection threshold. So if we have an emission of about 1 megaton a year, depending on where on the atmosphere we measure that, that's where we get about 1 ppm enhancement. And our noise threshold is at about half a ppm. So most volcanoes emit less than 1 megaton a year, and especially these early precursory signals are much weaker. So we're stuck there. We cannot really do that from space because we're looking through such a CO2-dense atmosphere. Now, the rescue came with a couple of papers that some folks had, seeing that there's an increase in what the plants do on volcanoes when they're exposed to this excess CO2. And they're starting to glow a little bit. And that shows in vegetation indicators from remote sensing data, like the NDVI and other things. And it also shows in the tree rings. So we set out to partner with some ecologists and figure out how can we potentially make use of that, either or as an archive of past CO2 exposure, or as a real-time indicator. And the real-time part is interesting because in the Calvin cycle, when water molecules split, provides energy for the cycle, and CO2 is made into sugars, there is a fluorescence effect of some of that light being returned, and that is measurable by remote sensing from space. So there's a potential proxy. The problem is it's really complicated because if you imagine plants doing that, they photosynthesize anyways. So I compare this to myself. I'm a big guy. I love to eat. So if you put more CO2 in front of a plant, it says, well, there's more food, okay, and you eat more. And then at some point, you start shutting your trap, and you're done. And the plants do the same thing. So the stomata, the pores on the leaves, close when they had too much CO2. That leads to an effect of heating up of the leaf surface, and that is also measurable by remote sensing. So we have an instrument on the space station called EcoStress, and there are several other sensors that observe these effects. Okay, so we set out, did some measurements, and figured, okay, so there's, on the top left, myself doing an air blank, doing CO2 flux measurements with chambers on the ground, and then looking at the adjacent trees to see if they have archived some of that excess CO2 that comes out there. Now, the CO2 coming out is not random. It's mainly controlled by permeability. And the permeability doesn't change so much. It changes day to day with moisture, but the overall bulk permeability of the underground doesn't change very much. What that means is that the entire CO2 degassing field of the volcanic flanks may be varying, but it mostly varies up and down. It doesn't vary spatially very much. So that means that if we look at a single tree and how much CO2 it may be exposed to relative to other sites, we could potentially see a signal that shows variation with time. So we did see that, and we looked at the short-term response and the long-term response. The long-term response is what creates an archive. That's on the right. So we saw that different species of trees metabolize that excess CO2 differently than other species. And that shows up in each of these measurement points is a CO2 measurement on the ground and a tree ring measurement. And also on the left, that's a chlorophyll concentration index. It's a fluorescence measurement that you clip on the leaf. So that's a real-time measurement on the left. And that also varies by species. So doing these experiments means that you'll have to have the same species all over the volcanic flank to be able to use it as a proxy. In the tropics, that works well. But it also shows that there's environmental conditions that affect what type of signal you get. So it means you need a lot of detailed information to really tease out a proxy signal. What that means is you need large areas. That is where remote sensing comes in. If you do that all on the ground, you'd be having a lot of people on the ground doing these measurements to get any meaningful effect. So to recap the problem, so satellites detect only about the 2% largest CO2 emissions in terms of CO2. The proxies using TRISA sensors, they work, but they're complicated. Okay, so that's the first take home. So what we then set out from that is to understand how we could go about doing these measurements. And to do so, we need large areas for a large data set to beat down the uncertainties and understand the confounding effects. The principle of what the ecologists and climate scientists get out of it is on the bottom right, and that is the projected future concentrations of atmospheric CO2 is reflected in these volcanic forests. They are essentially a window into the future, and that's the boon for the ecologists. So between satellite measurements and ground measurements, the sweet spot statistically that we figured out is to use drones, fixed-wing drones, not the little buzzers that everyone uses, but things that have a little bit longer endurance, longer reach, and can carry heftier sensors, and map out these volcanoes once in a while. And then learn from that, if we compare that with remote sensing measurements of the plant responses, to use the plant responses only in the end to understand those CO2 emissions. So we have this drone that was built in a public-private partnership. It's a fixed-wing drone that is the newer versions of that can do vertical takeoff and landing. So we can have a 20-mile reach doing measurements flying back. We've done that in Alaska under very difficult conditions. We've done it at Turrialba in Costa Rica at very high altitude conditions. And it can follow terrain and land and launch automatically. It's fairly large. You see I'm a big guy, so I'm about 2 meters. So you see me as scale there. The wingspan is about 2.5 meters. And so we launched it and flew it in a lawnmower pattern to image the plume that we knew was there. And lo and behold, it's there. So that yellow spot that says Arietta fumarole, there's a lot of data points in a spiral that are superimposed over each other. But that's actually an about 10, 20 ppm enhancement, so we could trace that with it. And this entire flight pattern is about 20 minutes. Okay, and here is the spiral on that diagram, CO2 on the ordinate, and on the x-axis you have time. The black line is the altitude. The green boxes are just the different types of operational constraints. So that second green box is the spiral, and you see those spikes in concentration going up. So that's where we intersect that plume at about 50 meters above the plume. And the right-hand diagram just shows you that we don't have a strong hysteresis effect on the sensor. CO2 sensors are notoriously pressure sensitive. So that's our validation for good measurements. Now, doing this from space. This is OCO3. It's a similar sensor like OCO2. It's on the space station. We can target areas and swing the sensor optics back and forth so that we paint out an area essentially. And that's what that is. So that acquisition on the left, that's the CO2 signal. The brighter colors are more intense CO2. Shows a little bit of an enhancement over Kilauea's downwind plume, but it's unclear from the data alone if this is actually CO2. It's within uncertainty. And for that area, because topography really messes up the signal. And what also messes up the signal is Kona. So Kona has a lot of CO2 coming out, Hilo a little bit. Then we have Trop-Omi, and it's too coarse and not specific enough to see anything. And on the right, we have solar-induced fluorescence. So that's the return light, the fluorescent return light from the Kelvin cycle. And it does show up as a little brighter, but the noise is tremendous too. So it's not the right sensor to do this, but we have another one launching in a few years called SBG, Surface Biology and Geology. And that will have the right resolution both spectrally and temporally and spatially to do the job. So looking forward to that. And then we're thinking of putting this all together into data products. We call this project Enhanced Levels of Emission Volcanically Active Tropical Ecosystems, or ELEVATE. So we're trying to elevate the community. There's people in Costa Rica, in Canada, in Europe, in the US, and one in South America too that contribute to this, and we're open to collaboration. I don't have to ever be on the front of a paper, I don't care. Other people can, the students should be, and the postdocs. So if you want to contribute to this and be a partner, you're welcome. So, wow. That's the cutoff, all right. Okay, so I think that's the conclusions. I can leave them up here. I'm not sure if there's time for questions. If not, I'll be here the entire week.
Thank you, Doctor. You actually came in right on the button. So there's time for questions. Do we have any questions in the room or online? Come on, we have to grill them. Come on here.
I like a good barbecue.
Yes.
I'm curious about any detrimental effects that other gas species may have on the actual measurements you see from space, because obviously there's a lot more than CO2 that's in these things. So might sulfurous or halogen species actually affect those measurements you see from satellites?
So that's actually a very interesting question to unpack. There's two answers to that, I think. One is the effect on the plants of those species, and the other is the effects on the measurements. So the fluorescent measurement is, as long as there's enough light coming back, it's not affected by aerosols or by other gas species. The CO2 measurements are affected from space, strongly by the aerosols, not at all by the SO2, not at all by the halogens. So it's mainly an aerosol effect that messes that up and causes a lot of that that scatter you see on the left. It's a very noisy measurement. The effect on the plants themselves, so if you go to a crater where you actually have SO2 emissions or a very hot thermal area, yes. But that's not the areas we're looking at. We're looking at the areas where the SO2 emissions are not occurring, where the CO2 emissions are not so strong that they acidify the soil and kill the microbiome around the rhizome, which is what, for instance, at Mammoth Mountain killed the trees. So those tree kill areas, we had this one paper looking at Mammoth Mountain. That's the bottom right, Carey Cost-Nicholson et al. In Biogeosciences, where we looked at the tree kill area, the area around it, looking at onion shells essentially, where the trees are suffering but alive, and then an area around that where they're happy as a clam or as a tree. And that area, that's the fertilization area. That's where they love eating, and it's not deleterious. That's where it's beneficial. And it reflects in a larger biomass signal. So they're actually using that CO2, eat it, make biomass out of it, store that in the tree rings. And there's colleagues of mine from the USGS that have measured the tree rings there and saw a strong signal of the volcanic CO2 in the Delta 14C data. So we've been using the Delta 13C and the 14C. We get a signal in both. It's the opposite, and that works too. So conceptually, as long as you stay away from the deleterious areas, you get to happy plants that are burping.
All righty, thank you. Do we have any other questions? I've got one. It sounded like you, and I love your eating metaphors, just sounded great. But it sounded like you can determine when there's an increase in carbon dioxide because it stops eating and there's a different fluorescent in the plant.
Well,
is that a predictive sort of?
Perhaps, we don't know. and we have a hypothetical framework there. We don't have good time series measurements to resolve that. Maybe our colleague in the other session has that. But what we do know is that it informs us what time of day we measure. The diurnal cycle determines the light availability. So at night, the plants respire, so it doesn't really matter. But at day, morning measurements will more likely show an effect than afternoon measurements when they're already full and sleepy. No, not sleepy, but the pores are closed.
Okay, thank you. Any other questions?
Okay.
Thanks.
So we're continuing with the next talk, and it's from Jens Carstens. It's a virtual talk, and it's about revising the volume of the Minoan eruption based on new marine geophysical and sedimentological data. It's yours.
Yeah, hello, greetings from Kiel. As Steffen said, I would like to talk today about revising the volume of the Minoan eruption. And the Minoan eruption is considered one of the largest eruptions in the Holocene. And some authors claim that it's actually the largest eruption. However, the measurements or the estimates in different studies for the Minoan eruption vary quite a lot, between 19 and 68 cubic kilometers dense rock equivalent. So luckily, Floyd McCoy yesterday gave a great talk about the Minoan eruption, so I can make only a very brief summary of the course of the events. So the Minoan eruption started with a Plinian phase from a subaerial vent located within the caldera. And with time, the eruption vent migrated in the submerged part of the caldera, and pyroclastic surges and pyroclastic flows and mud flows filled up the caldera and cut off the caldera from the sea, forming a tough cone filling up the caldera entirely. And then during the final phase of the eruption, violent eruptions formed large amounts of pyroclastic flows, and the caldera collapsed, and these two events caused the Minoan tsunami. After the eruption, the caldera was flooded again, and renewed volcanism formed the Nea Kameni edifice in the center of the caldera. I would like to give a brief introduction on how to measure eruption volumes. And this is again a little sketch about the Minoan eruption. So we had the Plinian phase, depositing tephra close to the island, but also quite far away in the Eastern Mediterranean and even reaching the Black Sea region. And then we had the ignimbrite phase, which deposited ignimbrite mainly close to the shoreline. And then we had the caldera collapse, downfolding the previous erupted material within the caldera. And to measure the volume of the entire eruption, we need to measure the deposits. And so we need to measure the ash or tephra deposits, the ignimbrite deposits, and the caldera infill deposits. And in our study, we're doing the tephra volume reconstruction based on sediment cores, the ignimbrite volume reconstruction based on reflection seismic data, and the reflection seismic data is also used to determine the caldera infill volume in combination with a seismic P-wave tomography. So volcanic products have a quite diverse porosity, and these needs to be corrected to dense rock equivalent or DRE to be able to compare the different components. So let us begin with the Minoan ignimbrite mapping. So here you see a map of newly acquired reflection seismic profiles. And I would like to show you one of these profiles here. So this profile crosses the Minoan eruption, Minoan caldera. It enters the caldera from the north through the northern breach, crosses the northern and western basins, and then leaves the caldera through the western breach. And I would like to point your attention to this part where we find thick deposits of the last 350,000 years of explosive eruptions at Santorini. And you can understand this part of the profile comparable to an exposed cliff in the caldera wall. So here you see an example of such an exposed cliff. This is the cliff of northwestern Thera, seen from Thera Sira. And you can see that the two shallowest stratigraphic layers are the deposits of the last caldera-forming eruption. On top, you see the Minoan deposits, so the Minoan ignimbrite in yellowish, and beneath this, the Cape Riva ignimbrite in brownish colors. To be able to compare this with the seismic data, we need to squeeze this photograph, and now it's 5 times exaggerated. And now I show you a 3D view on a digital elevation model combined with the seismic profile. And the solid white line you see here is actually the shoreline, and the profile and the photograph is actually located up here. And when we have a look at the stratigraphy of the marine part, we can see that there are 2 chaotic units emplaced on rather laminated deposits. And this resembles quite nicely what we see onshore. And if you continue the thickness and thinning trends of the onshore ignimbrites to the offshore domain, both fit quite nicely to the expected thicknesses. And this helps us to define the base of the Minoan deposit in the seismic data here in yellow. And so we map the Minoan deposit throughout our seismic data set. So we map the top and the base of the deposit, and based on this we calculated the thickness using an ocean bottom seismometer experiment to determine the seismic velocity, which are needed to convert from two-way travel time and seismic data into real thickness. And this is the resulting thickness map. And based on this, we could estimate a bulk volume of 15 to 17 cubic kilometers. And based on porosity estimates from onshore, we assumed a porosity of 48 to 68%. And this results in a dense rock equivalent volume of 4.6 to 8.3 cubic kilometers. And this is significantly less than the previous estimates. So here you see a map of the previous mapping attempts, which were based on single channel data. And these estimates resulted in a bulk volume of 54 cubic kilometers and a dense rock equivalent volume of 41 cubic kilometers. So our revised mapping is significantly smaller than the previous estimates. We use the seismic data as well to interpret the caldera infill. And here you see a zoom in, and all these colored areas represent post-Minoan deposits. And most importantly, the base of the green unit represents the boundary between Minoan and post-Minoan deposits. So we mapped out the base of this green unit throughout the caldera. And what you can see there is that there is a funnel-shaped depression, which you see on the right-hand side as well quite nicely, beneath the northern caldera basin and the Kameni edifice. And this depression correlates very nicely with a seismic velocity anomaly, which was detected by Emily Hoofd and colleagues in 2019 at the very same location, and which they interpreted as the deposits of the as a downfaulted Minoan caldera infill. So we combined both data sets, so reflection seismic and the tomographic data, and we mapped the base of the post-Minoan or the top of the Minoan deposits in the reflection seismic data and calculated the volume. And then we used the tomographic data. And Emily Hooft and colleagues figured out that there is a certain velocity threshold of about 3,200 meters per second, which marks the boundary between downfolded material and the surrounding bedrock. So if we use this as well, we can again calculate the volume, and the difference between those two volumes represent the downfolded Minoan material, which have a bulk volume of 8 to 10 cubic kilometers. And by counting the porosity, we end up at a DRE volume of 4.5 to 6.6 cubic kilometers. And this is, again, significantly smaller than previous estimates, which resulted in 18 to 26 cubic kilometers. So finally, we determined the tephra volume deposits based on marine gravity cores. So here's a map, and most of our analysis was done on newly acquired sediment cores from the southern Aegean Sea. And we have chosen some representative cores to do a more detailed analysis. And for this, we performed X-ray CT scans. So here you see core 20, and the Minoan layer is about 50 centimeter thick here. And what is quite nicely, which is quite nicely shown here, is that this Minoan layer is divided into 3 units. And using the CT scans, we analyzed the bedding and the grain size in much detail, and could find out that this central unit shows stratified beds which are partly discontinuous and have an inclined bedding and showing indications for cross-lamination. And therefore we interpreted it as a ground-based flow. So this is the volcanic turbidite of the ignimbrite phase of the Minoan eruption. And beneath this, the cores look very different. We have continuous normal graded beds with a low lithic content, which we see as an indicator that these are the deposits of the Plinian fallout, while we interpret the material above as the co-ignimbrite ash. So the particles are very small and we don't see any indications for crystals and lithics. So finding these partition in the cores, we reanalyzed many of these core, and we see the distinct boundary between the different units and basically all of the cores. However, these flow unit can only be found in some of the cores. And these cores actually are all located in this pinkish area. So they're located in a channel-like basin structure, which is extended eastwards of Santorini. And we mapped this Minoan turbidite, and it has only a DRE volume of 0.1 cubic kilometers. However, more importantly, we can distinguish between the Plinian and the co-ignimbrite phase in many of the cores, and we use this to produce isopack maps for both ash layers in the cores. And what you can see here is that the Plinian phase isopacks have a different orientation than the co-ignimbrite isopacks. And for both of these phases, we calculated the volume and added this together. And more importantly, or just as importantly, we used the CT scans to define the porosity of the deposits in great detail. And this resulted in a porosity of 62 to 64%, which is much higher as previously assumed. And this results in a a DIE volume of 16 to 21 cubic kilometers, which is again smaller than the previous estimates, but this is mainly due to the increased porosity. So if we have a look again at this map of this compilation of the 10 largest eruptions in the Holocene, and put together our estimates for the ignimbrite, for the caldera infill, and for the ash, and for the onshore deposits, which I didn't show, this results in a volume of 31.4 plus minus 5 cubic kilometers. And according to this, Santorini is not the largest eruption in the Holocene, but it's worth noting that most offshore deposits for these large eruptions are only poorly constrained, and this is especially true for the marine ignimbrites. So we used the new multi-method analyzers to revise the volume of the Minoan eruption to 26 to 36 cubic kilometers, and this reduction is mainly due to a significantly reduced Minoan ignimbrite volume. Thank you very much.
So, thank you, Jens. So maybe we have one quick question, because time is nearly over. I see no question, also no virtual question. So I think we can continue. Thank you, Jens.
Thanks, bye.
Alrighty, now as an engineer, I'm looking forward to the wake-up call I'm going to get from Dr. Carolyn Porchetta from the U.S. Geological Survey's Hawaiian Volcano Observatory, talking about robotic technology aids and novel data collections for examining volcanic processes. But the heads up is the scientists must help the engineers develop these capabilities. So go to it.
Thank you. Yes. I should have amended my title slightly, that the scientists, the civil defense folks, the first responders, all of us should be helping to provide input to engineering processes that are ongoing. There's a lot of great technology development out there right now, but if it's done in a vacuum, like, here, use this on the volcano, that's not going to work as well as us working together to build these devices. So, collecting volcanic data has, by hand specifically, has some limitations. It's great, it's exhilarating to be in the field. I think a lot of us who are field geologists love it, but it takes time, it takes money to travel there and support weeks to months of field work, and you're limited specifically to surface easily accessible areas. And so this is a photo of me from my PhD for scale, and I walked all around this fissure. I took samples of the ramparts, documented all that, but the one remaining question for my PhD was this fissure, and it was very clearly open into the ground, but it was not accessible to me, and that led to my postdoctoral work that involves some engineering. So we can improve with robotics some of these limitations. We can either get more data more efficiently and get out of the field quicker to save costs, or we can collect more data for the same time in the field. And this allows us to also collect more robust data that is, as long as we're not taking samples and modifying the surroundings, they're also repeatable by other scientists. So why robotics? This session has answered that gloriously. We've seen great examples of underwater robotics and UAS in the air with fixed wings. In addition to collecting data, robotics allow us to do broad monitoring for eruption response, specifically for our cities that live on volcanoes. We can also do targeted monitoring in science for specific areas of ongoing eruptions. Maybe you want to focus in on the vent for one type of area, and if you're seeing earthquakes just off to the side, you want to focus in with robotics on that area too. So it gives us a lot of flexibility. So a few examples of where that we've already kind of seen from all the speakers combined. UAS, this is an example of a UAS that I fly, but they can be any size, fixed-winged or rotor wing. This is an image on the lower right of Dante, which was one of the first volcano robots. It's the size of a large vehicle and was meant to crawl into craters and rappel off a tether to sample gases. We'll spend the rest of this talk on the robot that I built, which is VolcanoBot. And then there's also underwater robots that we saw in the last talk. Most of them are submersible, but there's also one called a wave glider, which is in the picture here, and it floats along the surface. So all of these can help us. This is probably the slide I'm going to spend the most time on, and we're going to talk about something called systems engineering that many of you may or may not have heard of. This is what engineers live and die by, and this is their version of the scientific hypothesis. So you need to have an operational concept of what you want this thing that you're building to do. What is the system that you're building and that you're trying to address? But beneath that, you can kind of think of our bodies as an analog. To be a human, you have a skeleton, you have a brain, you have eyes, you have all these systems that are working together as a subsystem. And each of them are kind of independent, but they make the system as a whole. And then below that, you have your components, and those are the individual parts that make up each subsystem. And so systems engineering will basically break down the question of what do we want to measure and how do we want to measure it, and let's build something that can do that. And so that's the realization phase, is that you either buy components that are in existence, or in our case for VolcanoBot, we built our own components, and then you start putting them together. You may need to include some computer software folks to write software for whatever you're developing, or if you're working with another company that's already doing the development, you may want to have them change the software slightly to accommodate what you're looking to measure. So then you go through a few steps of verification. At the component level, can the vision sensor see me? As simple as that. Then you step up to the subsystem level. Can the vision sensor with the cord to the computer, with the cord to a hard drive, can we record data? Can we scan a room and record that data? If so, then you integrate all those subsystems into your system, and you go out and do a field test, and it kind of circles back around. This is an iterative process. It's not a one-way path. And so if your field test doesn't go as planned and, you didn't quite document what you wanted to, you go back to the system and you say, what needs to change? What do we add? Or in some cases, what do we take away from the robot in order to get back to a field-tested system that actually collects the data we're interested in? So let's blaze through the VolcanoBot study. This is the first time I'm giving this talk where I'm not actually going to discuss any of the science. We're going to talk about how this thing was built and why it was built the way it was, in an effort to help inspire all of you guys to possibly build your own tools as well. So the system, the operational concept, is to collect data in confined spaces not accessible to humans, specifically in volcanic fissure conduits. Why is this important? There was a conference about 10 years ago where about 200 volcanologists got together and said, this is one of the biggest limitations. Knowing the conduit geometry of any volcanic conduit is a big assumption in all of our models and all of our theory and all of our interpretations of geochemical data. We don't know what conduits look like on a detailed scale. Geophysically, we can get to, at best, tens of meters, but we're still guessing. And so VolcanoBot is meant to go inside these conduits when they're exposed, as shown in these pictures, and actually measure that for the first time. So in the video in the background, you'll just see our first test deployment of, can we even get this thing in the crack properly? But to reiterate, the system level requirement is to make a 3D map of a volcanic conduit at the centimeter scale detail, so we have measurements that we can actually use. And you'll see a laptop in the background behind me. We need it to display data so that we know it's working and we know what it's seeing. We need to know if it's overheating, so it sends real-time health information of what the temperature is and if the motors are working. It needs to be able to move itself. Even though it's on a tether, we're not going to be able to help it if it gets stuck. So we had to address the mobility of how do you navigate inside this crack when you can't see it anymore and it's on its own. We also I put a requirement that it needs to fit into a 20 centimeter wide crack. The one in this video is very wide, but most of the fissures that we had access to were in the 20 to 50 centimeter range. And then because it's Hawaii, it needed to be waterproof. It rains a lot there. So architecturally, the subsystems, we need 3D mapping system. We need an IMU, which is an inertial mass unit. It tells you the orientation. So if you rotate to the left, it measures that with a gyroscope and an accelerometer. We had temperature, again, to make sure the robot wasn't overheating. We needed a backbone, which ended up being our tether, and that sent all the power to the robot. We put a protective shell on it. We put a computer on the surface initially that was the brain of the robot. And then we needed wheels and strong enough motors to have traction when it was out of our reach. So here's a video of how we put it together. We used an existing robot, this black one in the middle here, if I can get the mouse, and we just built around an existing robot. And we just said, here's the components we need. This is the vision. These two big blocks are some lights. We put some wheels on. You can see the case is almost as big as the wheels to protect it. And we just say, all right, that's our system. We have our components. Let's go test it. We tested each of them in the lab initially. And so on the left, you have a picture of it going into a fissure for the first time. And this is what data from that system looks like. On the left, you have a near-infrared image. Bright yellow is close to the robot. It fades out to black as you go farther away from the robot, except when it tips forward. And if it's too close, if the ground is too close to the sensor, you lose your infrared data, which is the data we're trying to measure. But as we come over the edge into the conduit, we're seeing a volcanic conduit for the first time. And that was really gratifying to see the system work, even though straight out the gate we found something we can improve on. So I'm going to just let this play for a minute, and hopefully that doesn't run me a few minutes over a minute over the 12-minute mark. But you'll see as this goes that our wheels needed to get over all these little bumps, but also we just spun around. And this is out of our reach. This is 5 meters in the ground at this point. And so that was another thing, cue to self, when we go through the systems engineering process again, we need to make sure we can handle the robot being upside down. And so the movie paused there for a second because we were like, how do we drive it now? So we realized we have to just drive backwards in order for the robot to move forwards when it's upside down. But it took a second to think that through. This was one of our first deployments, and we actually got a great surprise at the bottom of our descent. We went about 10 meters, and you'll see at the end of the video here, someone had thrown a Hawaiian lei into the fissure, and no one ever would have known that, except that we happened to descend right on top of this lei. So I'm going to let this play through, but that might run me 30 seconds over my 12 minutes. So you'll see we flip over again, and all of this is the first time learning of, there we saw the sensor tip up, and we lost our data for a second. All of this is just learning, how do you even move? How do you send a robot into a fissure and document it? And there's our lei. Okay, so we went through the iterative process again. It's very important to say, here's what we think is going to work, and take it to the field and test it, and then take it back to the lab and fix everything that didn't work. So we made better electrical connections because this thing would shut itself off sometimes. We made the cord more manageable because it had power and mechanical safety cord and the communications cord. So we narrowed that down and combined a few of those cables. We shifted for the second robot, the battery to be on the robot. That ended up not working very well. So in the third one that you see in this picture, we shifted the battery power back to the surface and we power it over the tether. We added more torque and mobility because we noticed on that first couple of descents, the first robot could pull itself into the fissure, but it couldn't really pull itself out. We had to do a lot of hand pulling on the tether, so we beefed up the motor so it could help assist its climb out. We tried to put a computer on board, and we started with Raspberry Pi. That didn't work so well. It just wasn't strong enough. And then we switched. We didn't need the visual lighting, so we ended up switching to a camera that was just the infrared. And that's one of those examples where you would take away a component to make the whole system work better. We also switched to fully 3D printed frames. So here's a movie of the second robot compared to the first one. You can see the interior robot is missing. That's all 3D printed. The motor housing is there now, but generally same construction. With one exception, we moved our homemade computer chip on top, and you can see now that the top of the robot sticks above the wheels, which was a mistake. As soon as this thing flipped over, it couldn't move anymore because the wheels couldn't touch the ground. So we deployed this and then scrapped it right away and moved straight to VolcanoBot 3. Improved electrical connections again because we found more things that needed to be improved. We increased the cord strength because on the first robot we actually needed to break the wheels off of the robot in order to pull it out. So we improved the cord strength so that we could do that again if ever needed. The goal is to engineer that you don't need to do that. And then we improved the battery life. We made the size much more narrow and again improved the torque on the wheels. So this is stepping through, I don't have a video of this one, but stepping through some of the changes from VolcanoBot 2. We'll take the shell off. This is our homemade circuit board up top right here, and we decided that actually needed to move down to the back of the vision sensor. And we also removed this Raspberry Pi in pink on this image, and we inserted a much larger computer similar to a Mac Mini or an Intel NUC, if you're familiar with either of those. This had the processing power to handle the data on board, even though the batteries were not on board. Then we put a shell around it and field tested it in California. You'll see straight away that from that image, we had modified it already to have a tapered end. Because we realize if rocks fall in, because the tether's going over some rocks, we don't want them landing on the components on the inside. So this works great. We tested on an andesitic dike right on the beach, and the idea was that this is the inverse of a fissure. And so we can see how it's moving and how it would move in a fissure without having another wall blocking our view. And it does great, and the motors were so awesome that it actually climbed over this rock climbing harness where you would put a rope through and just kept going. So then we took it back to Hawaii and dived right into the same fissure, and we got great data. You'll notice there's one more change that we did between those tests, and we added this back sensor. And that's because on the next slide I'll show you, there were some data gaps with only having one sensor looking forward. So if you want to measure a conduit in 3D, you need to see all of it. And we were missing anything that was upward looking on the underside of protrusions. Okay, so that's VolcanoBot 3 going in. So here is what the data looks like. This is one drop down. This is the whole video feed stitched together. On this image on the left, we're looking, the strike of the fissure is along the plane of the screen. So we're looking at the walls essentially, and the black is the outside, the white is the inside of the fissure. This, the side view in the middle, that's looking along strike, so the fissure would be coming into the room towards you. So then in the video here is the data just from the red box. And so once we've collected this data, we've stitched it all together, you can actually start to do virtual reality stuff with the computer. You can get better outreach to students and to other researchers, and you can just dive right into these fissures, literally. You'll see in a moment, we're gonna zoom in. But right here, whoops, where's the mouse? There's a gap, because you can see that the fissure kind of protrudes here, and everything underneath that gap is missing. So that's why we added the second sensor. You can literally put yourself inside a 20-centimeter crack and figure out, if I'm a cubic meter of magma, how am I gonna erupt through this 20-centimeter crack? So that brings me just about to the end. This is some LiDAR from my PhD, and the yellow box is an attempt to try to image the shallow conduit, which failed. We did not get any data points from that, and the goal is just get the width of the conduit. But the robot provided all of that yellow data, and so we have every 10 centimeters in depth, we have a horizontal contour. This is the same data you saw on the last slide, but now shaded for a surface topography. And we can contour that not just horizontally, but vertically. And so now we go from having at most one data point from the LiDAR to having hundreds of data points along a single drop in the fissure. And this robot was successful enough that the third one mapped 100 linear meters of fissure 30 meters deep. So we had quite a lot of data from a successful run. So in conclusion, we can and should use robotic platforms to help us collect data we need. We should be asking, what data do we want to get that we don't already have? And so there's currently existing UAS for aerial stuff, UAVs for underwater that are great, and they may serve your purposes exactly how you need. But if not, the engineers who build these things often are looking for input from us. How can we make this better? If you want to get this specific type of data and we're not quite getting it for you, how can we modify so that you get what you need to make your decisions as emergency managers or to understand the system of the volcano better as scientists? So I challenge you to think of what research questions you might want to ask that would necessitate possibly building your own tool or modifying someone else's tool. Because anything on this volcano conduit diagram, on this volcano diagram is fair game for robotics. And while I address, this shallow conduit area right here, really there's nothing we can't engineer to help us. It's just a question of how do we do it, and that we do that through systems engineering. So working together, we can collect a lot more data and data that we've never had before to better understand volcanoes, our landscapes, and the cities that live on these places. Thank you.
Dr. Porchetta, that was friggin' brilliant. That really was.
Thank you.
I'm going to lead off with a question right off, and then put the audience. Is the planning, the plans, the CAD drawings, the software available? Is it open sourced, or is it something that is closed source? In other words, if somebody in the audience is interested in building this robot, can they get the plans for it?
Sure, yeah, I'd be happy to share the plans for it. They're not open source right now, but it was done in SolidWorks, and I'm sure it could be imported to other computer drawing programs. I'd be happy to share the plans for that, yeah.
Fabulous, thank you. Okay, now I'm going to give you all a chance. Do we have any questions from the audience? Anybody here in the room or online? Yes.
Thank you for your presentation. I was wondering if this type of tools or robots needs an expertise of robotics, or if they will be used for instance, traditional geologists with some practice to manage in well way the robot, or is necessary some robotic expertise to conduct the research?
That's an excellent question. So what I didn't say in my talk is that my background is exclusively science, and when I got to NASA, the Jet Propulsion Laboratory, to build this robot, I had zero engineering background. We built the first robot in about 3 months. So as long as a scientist, you're willing to ask questions, which I assume all scientists should be willing to do, you don't need to be a roboticist specifically to build something like this. You do need to learn robotics. You do need to learn basic, mechanical engineering and electrical engineering to build and wire the machine. And then I did hire on a programmer, I collaborated with a programmer who programmed the robot for me because I don't have that programming skill set either. It's a very advanced programming skill set. But as long as you are willing to work with the folks that have those skills, you can develop this as a lead scientist and not necessarily have a robotics background of years or decades. I had 3 months of background that I learned as I was building this. So it's a tool that we can all use, and you don't necessarily have to be the expert in it.
Okay, thank you, Carmen, for your answer.
Yeah, you're welcome.
Okay, I don't see any questions online, but do we have any more from the audience? Yes.
Just as a very quick follow-up to that, for people looking to establish those kinds of relationships as a scientist with engineers, do you have any advice from what you've seen, on either side of that field for those of us, looking to how could we begin that process?
Yeah, that's a great question. Maybe 2 things jump to mind up front. And the first is that there's going to be a slight language barrier. And so as long as both sides are curious about the other side, the engineer is curious about why is this important for science, and the scientist is curious about what do you call a system, what is a subsystem, what are the components. As long as you can connect on the language level there, you'll have a really smooth interaction with engineers. The next question is where to find them. So I would start with the institutions that you know about and anything that's connected with the university you're at. So go talk to your own home university's engineering department. You can also branch out to companies, so Liquid Robotics, Honeybee, I believe, is another robotics company. Go just search for robotic companies that build the kind of robot you're looking for, and then reach out to them. The few times I've reached out to companies directly that are their own private sector, they've been very welcoming of, oh yeah, let's modify it, let's do this, that's great. And then the other option is just, conferences. Just the networking of, hey, you know someone who knows someone, let me go talk to them, can you make the introduction for me? But yeah, I think as long as you can describe it and know there will be initially some conversations of, well, what are your requirements? I want to do cool science. So as long as you can get past that and lay out the system, the subsystem, the components, and what the scientific data goal is, then from there, you guys, the sky's the limit. Yeah.
All righty, we're technically over, but if there are any other questions, we'd love to have them. If not, I'd like to thank our 5 great presenters here.
Yeah, so we are continuing at 6 o'clock with the second part of the session.
And there's going to be free beer, of course.
Good afternoon, and welcome to this session entitled Pyroclastic Density Current Transport and Emplacement Mechanism Insight from Field Experimental and Modeling Studies. Alessandra, good afternoon.
Hi, everyone. Good afternoon, Matteo.
And so the presentation, as you know, will be 15 minutes each, and I will advertise you when 5 minutes are left. And we start with Per Francesco Dellino with the presentation Recent Advances on the Positional Mechanism and Air Entrainments in Pyroclastic Density Currents from Large-Scale Experiments.
Okay, thank you, Matteo. Thank you, everybody, for being here after this opulent lunch. And I'm going to speak about something of the new issues that have come from my group. This is one of two presentations. This is the base of the second one. If you lose something here, you do not understand anything on the second one. Anyway. And let's start with a synopsis, because generally I forget everything in this period was after the COVID. So anyway, I'm reading. So the phase of pyroclastic density currents is to sediment the solid particulate material and to cool down by the mixing of the hot magmatic gases with the ambient air that they entrain along and out. In doing so, the momentum and the strength, the force of the flow diminishes, moving away from the vent. At the impact of the eruptive fountain on the ground, a massive layer of sediment, likely linked to a highly concentrated and less mobile undercurrent, will form, while the upper highly diluted and turbulent part, somebody call it a surge, will decouple and continue moving. If we had models of air entrainment and particle sedimentation and could scale deposit structures, I mean the facies or the dunes or the lippers, we could elaborate a method to reconstruct past disaster-making events, which are, in most cases, the only thing we have about eruptions. With this aim, in this work, large-scale experiments were used to model air entrainment, sedimentation rate, and deposit structures. Models were applied to deposits of past eruptions, as the example of 79 Vesuvius at Pompeii, which I'm doing here, for helping in the assessment of the impact that currents can have on buildings and population. The flow strength starts from a model of multi-phase stratified boundary layer. This is the basic concept of a code that has been released on this. First things first, we reconstruct the physics of past currents, starting from the equivalence of the No.
It's the small, the upper button.
The upper one?
Yeah, and we have to hold it for 1 second.
Okay, anyway, this U star at the position is equalized to the settling velocity of the material.
You hold it?
Okay.
Takes 1 second.
So the settling velocity of the material is calculated from the deposits that we sample. And this is calculated for all the components. After this, we have a system of equation that starts from this solution. This is the shear strength of the current. By this, we have the shear velocity, and then the stratification of the current, in where we solve for particle concentration, the density of the mixture, etc. And from this relationship of the turbulent boundary layer over a wall, we resolve for the velocity. This is just a sketch of the model, which is solved probabilistically. So the experiments, we want to use experiment to validate the results of this model. The experiments, many of you have already seen something from these experiments. This is the formation of a collapse from a column and the formation of pyroclastic density current. At the bottom, you have the deposits that are formed, the massive deposit at the impact, the stratified like ripples deposits and away, thinning out. Okay, we measure things during the experiments. You can see here some sensors and also mock-ups to see the effects over a building of a current. And then we start modeling other additional things like the entrainment. We think that the entrainment is quite important in stressing the fate of the current. Okay, the entrainment is defined by the ratio of two velocities, the stream velocity and the cross velocity, which means the increase in height, which is, we know from the literature, proportional to the Richardson number that has to do with buoyancy. In the experimental measurements, the entrainment is defined by this equation. And these are measurements of the entrainments and other parameters of the experimental currents, velocity, the density of the mixture, the height, and the sedimentation rate. And after this, we can collapse the data, both of the most problematic points that there are where there are a lot of acceleration of the flow, and all the things collapse very well with this relationship, which, astonishingly, is quite identical to the entrainment rate of snow avalanches. So, you know, things in nature are very well educated. And then we go to the sedimentation from turbulent suspension, which is quite important because mostly pyroclastic density currents exhaust because they lose the sediment, and so the density contrast with the ambient is zero. And after the experiments, we are able to measure the sedimentation rate. Why? Because we know the parent population and of the material. For example, you see that at the impact, the massive deposit is not different from the parent grain size in the cannon. And this is the difference from coarse material and from fine material experiments between the grain size in transportation and grain size at sedimentation. From this, we can calculate Dix proxy, which is the concentration of the sedimented materials against the concentration in the parent flow, against the particle Rose number and the normalized Rose number, which is the Rose number at which you have saturation in the current. And the collapse of data is quite well. And from this one, you can have this awful relationship, which anyway is the sedimentation rate, in which you have the grain size, the density of all the components, the Rose number, whatever you want, the setting velocity. So we can have also the difference between the measured sedimentation rate and the calculated sedimentation rate. We can scale the structure of the deposits along the flow to these parameters. During the experiment, you have the massive deposits and various structures, and we can scale this compared to the bed load transportation rate, which is how much of the material lost in the background is moved by traction. And more or less the same quantities appear in the bed load transportation rate, but with different scaling and with different ratios. And after this, we can construct a diagram. In this diagram, you have that the bed load structures and the dune structures and the ripple structures scales in this diagram, which has only two entries, the bed load sedimentation rate and the sedimentation rate. In this case, we have experimental data as some data from real deposits. And this is the application of the model to the Pompeii eruption, which has massive deposits near the vent, and at Pompeii, only stratified deposits with ripple structure reach there. We have this fantastic opportunity to see what happens to people, and you see from the plasters that people were not had not broken arms. Also, the clothings were saved. So let's calculate the flow strength at Pompeii. These are the three probabilistic solutions. This is the 50 percentile, the 16th percentile, and the 84th percentile. And if you see the average solution, the velocities there is more or less around 20 meters per second. The dynamic pressure is less than 1 kilopascal, which means that the mechanical effect of these currents at Pompeii was not very high. The density of the mixture is a little bit higher than 1 kilogram per cubic meter, and this is the particle volumetric concentration, which is more or less 0.001. So let's start calculating the flow temperature. To have in the flow temperature, you need to know the balance between the magmatic gas and the air. And we can calculate the amount of magmatic gas by this relationship or by the entrainment. So we can have the balance between the magmatic gas and the ambient air that entered by two methods. And the two methods more or less give the same results. So the temperature was a little bit higher than 100 degrees. So what happened? What happened is that if we know the thickness of the deposits and the aggradation rate, the velocity at which the deposits grows with time, and we know the sedimentation rate and the density of the deposits, we can calculate how much time, for how long the current was moving over Pompeii. It's 17 minutes, which means, in our opinion, by these results, that the dynamic pressure was not very high. In fact, bodies are intact. The temperature was a little bit higher than 100 degrees, not very high. In fact, clothes are intact. The particle volumetric concentration, this is fine ash, it was 0.001, but the flow duration was about 70 minutes. So the conclusion is that the flow duration combined with the concentration of ash particles was long enough to cause death by asphyxia at Pompeii. The recent literature on the subject suggests, in fact, thanks, for example, to Peter Baxter, that the exposure of fine ash, even at low concentration at low temperature, can be survived only for a couple of minutes. And the conclusion is that in these localities, the force impact of dilute pyroclastic density current is not so severe, but the presence of fine ash in suspension for a few minutes represents a major deadly effect. Many thanks for your attention. I was a little bit longer.
Perfect timing and very interesting presentation. Thank you. Any question? Yeah, Tommaso?
Thank you, Piero. A quick question about the sedimentation rate. So what can you quantify how much the sedimentation rate is reduced by the effect of the turbulence or the suspension or anything with respect to, for example, sedimentation rate calculated with the settling velocity of the average grain size?
Thank you, Tommaso. That's really interesting because the sedimentation rate is definitely dependent on the turbulence, but it also depends on the acceleration or deceleration of the flow, because there's a maximum amount of particle concentration can be sustained by the current. It's like having particle saturation in the current. And so at that point, you can have two effects. Turbulence is lost. It could happen. Or the current decelerates quite much. For example, when you have a breaking slope, or for example, when you are in front of a big building, and this dramatically increases the sedimentation rate, and also dramatically increases the entrainment. So the two things are coupled. The entrainment rate and the sedimentation rate, it seems that go together. And the strange thing, the good thing, is that it happens also on snow avalanches. There was another one over there.
So thank you for presenting these studies. So you said that there's quite good agreement between what your model predicts and what your experiments deposited and what was in the field. But was there any scaling issues you had to consider when designing the experiments? And do you think there's a minimum threshold volume for creating the processes that are active in the field?
Yes, in fact, the experiment were designed exactly to form structures in the experiments. And it was quite huge because we were using some half a ton of Vesuvius ash for having good structures in the case of collapsing columns. When we were modeling plumes, you could use also less of that. But that's important, very important. The amount of material that you use to scale things to the real situation is an issue.
But how did you choose the minimum volume that you had to use?
Because we knew that in volcanoes, structures start to form with a thickness of a few centimeters. When you scale things, and after the first experiments, you know more or less the dispersal area, which is something like 30, 50 meters of radius, then you can scale.
Okay, thank you very much.
Any other question? Yeah.
Hello. Thanks for the presentation. I'm just wondering about that. You talk about the temperature of the flow, right? But because we are talking about the dynamics of the flow as well, do you consider that it would be, I don't know, the correct word is more useful or not, but are you considering to give the interval of the gradient of temperature for the flow instead of just one temperature value?
Yes, that's possible when you have the stratification in the current. You are meaning the gradient of the temperature inside the flow? Yeah, that's possible by the stratification. I was calculating the temperature assuming a 2-meter height, which is more or less the survivability of the people. But because we know the stratification of density and also the stratification in terms of the magmatic gas and the air, we could have a gradient, which is not shown here, but yeah. And also the deposits has a higher temperature.
Okay. We have to move to the next one. Thank you, Pierfrancesco.
Thank you.
So the next presentation will be virtual. It is Sarah Oakburn presenting pyroclastic density currents from the field to the f of x to the forecast. When you want, you can start. Thanks.
Thank you. Good morning or afternoon or night, wherever you might be in the world today. I'm sorry I couldn't be there in person. Right, so pyroclastic flows from the field to the function to the forecast, or put another way, how statistical analysis of global databases, like the FLODAT database, can help inform models used for forecasting PDC inundation. We just heard a great talk about using experiments to inform conceptual models of PDCs, and there's a great lineup of talks on both field investigations and modeling of PDCs coming up later in the session. My talk is going to focus on how we might bring all of this data together in community databases like FLODAT that can be used for statistical analysis, can inform conceptual models, and can help derive model input parameters for probabilistic modeling of PDCs. The FLODAT database in particular contains information about many different kinds of mass flows, including PDCs, lahars, volcanic and non-volcanic debris avalanches, as well as submarine and extraterrestrial avalanches. I'll just focus on PDCs today, though. This plot shows some of the previous efforts to collect PDC data that FLODAT is built upon, with the number of the individual PDCs recorded by each effort shown on this graph. FLODAT currently contains varying levels of information about almost 4,000 PDCs.
Sorry, Sarah. Sarah, excuse
Yes?
me. There is like a little bit of problem with the microphone. I don't know if we are hearing a little bit of noise. I don't know if you can. Yeah, go further. Yeah, maybe try to not touch the microphone or something like this. We hear some noise. Thanks, but go ahead.
Okay. Sorry about that. I'm probably gesturing and touching my face. Is it okay as long as my hands aren't moving? No?
Go ahead.
The database started with a focus on dome collapse PDCs, and these make up the majority of the database. The database also includes column collapse PDCs, rock falls, lava flow front collapses, mixed avalanches, surge-derived flows, and lateral blasts. However, many entries are currently undefined. That is, either no information exists other than some type of PDC occurred, or more detail is yet to be populated. FLODAT also records a number of different property types or parameters about PDCs, such as runout length, height dropped, H/L, bulk and DRE volumes, directions, velocities, precursors, as well as a lot of deposit morphology parameters. Where possible, these metrics are recorded for different parts of the PDC as well, such as the ash cloud surge or the dense basal undercurrent or the center of mass. However, many flows in the database have only a few recorded parameters. Many of these parameters are useful for modeling as they can be used directly as input parameters for different models. This table is showing some of the potential input parameters needed for different models of varying complexity, from simple empirical models to multi-phase models. And obviously, we'll hear a lot more of these parameters today throughout the talks. Obviously, for probabilistic modeling, it's also really useful to have probability distributions for each of these input parameters. In the rest of the talk, I'll highlight some of the information in FLODAT about PDC volumes, initial directions, and H/L or basal friction. These plots are showing PDC frequency volume distributions on the left and PDC frequency runout distributions on the right for all PDCs except the very largest ignimbrites. rates. Note the axis break for the largest volume flows. I show these frequency runout distributions here as well as a proxy for frequency magnitude, because as you can see, orders of magnitude more PDCs have runout information than volume information. Those previous plots showed the frequency magnitude distributions for all PDCs in the database, which might not be the most useful for more specific PDC modeling. So what might affect these frequency magnitude distributions for dome collapse PDCs, for example? The size of the dome isn't obviously a limiting factor for the maximum PDC size, but we know from other studies that things like extrusion rates or explosive activity, debuttressing or undercutting of the dome, and even extreme rainfall might play a role in PDC size. So we can examine this role that other factors such as explosivity or seismicity or dome growth play in PDC volume distributions by using detailed eruption chronologies like you can see in this timeline for Pezzimiani or Merapi, for example. You can see PDCs of various runouts plotted alongside other observational data such as dome growth and extrusion rates or even explosions of different sizes. These frequency runout length plots from FLODAT are sorted by periods of dome growth in green and pauses in dome growth in gray, and show that PDCs are both more frequent and have longer maximum runouts during dome growth than during pauses. Similarly, this volume data for Soufriere Hills volcano shows much the same thing, that PDCs are more frequent and larger in volume during dome growth than pauses. And these different frequency magnitude distributions for PDC can be used for probabilistic modeling that better reflects the current conditions for a particular volcano. So for example, these plots show probabilistic Titan 2D model runs at Soufriere Hills for 1 year of dome growth on the top versus 1 year of dome quiescence on the bottom, with the red color showing higher probabilities of inundation. And as you would expect, the probability of inundation is much higher when the dome is actively growing. Data from FLODAT can also provide frequency magnitude information for column collapse flows, as well as volume partitioning information like is shown in this plot that's comparing PDC volume to the total erupted volume. This preliminary data shows a wide range of collapse behavior from hardly any collapse to near total collapse of the column, with the median percentage around 32% of total erupted volume collapsing into PDCs. FLODAT also contains quite a bit of information regarding PDC H over L ratios, that is the height drop versus the runout length through the coefficient of friction. And regression analysis of H over L data from FLODAT can be used directly in simple models like the energy cone model, or can be converted to basal friction parameters for use in many geophysical models. This plot shows H over L versus volume. The lower values of H over L for larger volume flows reflect the increased mobility of these large flows. Also, different volcanoes can have differences in PDC mobility. Sioux Hills volcano data is shown in yellow there, for example. And these differences in mobility probably are due to effects of channelization and topography. However, it's reasonable to assume that the H over L versus volume metric, while not exactly the same across different volcanoes, is controlled by similar processes and can be assumed to vary according to some probability distribution. Hierarchical Bayesian modeling, like shown in this example here, allows one to borrow information from a global database like FLODAT, leading to better quantification of uncertainty and improved accuracy and hazard assessments. It's shown in this example for Semaru volcano, which, as you can see there, is pretty data sparse. Initial direction is another input parameter needed by many models. And while column collapse flows are pretty uniformly and radially distributed, dome collapse PDCs often have preferential directions affected by things like summit topography, like breached craters, by the direction of the growth of dome lobes themselves, and by the direction of previous collapses or the height of the dome. I'll just illustrate one example from Sioux Hills volcano regarding the effect of dome height on flow direction. So this is a photo of the dome taken from the observatory, as marked on that map there, looking to the southeast. And you can see that the dome rises above these old domes in the foreground that essentially block PDCs from traveling toward the camera when the dome is smaller or shorter. These plots of many hundreds of PDCs from Sioux Hills volcano show that the distribution of directions is quite different when the dome height is below about 950 meters above sea level in blue there, than when it's higher, as shown in the green plot. When the dome is relatively tall, these flows are able to overtop that confining topography and travel to the northwest. So these plots show probabilistic modeling of PDCs, again, using a uniform direction in the top plot versus using the distribution from FLODAT for when that dome is higher than 950 meters above sea level, showing how the uniform distribution might underestimate inundation towards that northwest direction when the dome is really high. Finally, I'll just end with a few thoughts about some of the challenges faced in using global data for statistical analysis and forecasting PDC inundation. I'd like to point out that a lot of these input parameters that I listed in the beginning, I didn't talk about today, and there's many more that we'll hear about throughout this session, like initial velocity or mass eruption rate, particle concentrations. And while many of these parameters are included in FLODAT, not many PDCs have all of these parameters available, and some of them are actually quite difficult or impossible to measure for real flows. So this might be a case where it might be useful to include experimental results in community databases such as FLODAT. You'll probably also notice that I used Sioux Hills volcano for many examples in this talk, and while I do love that volcano a lot, it's really because most other volcanoes don't have these really rich data sets. And many volcanoes actually have really sparse data from which to derive model input parameter distributions. And so those more sophisticated techniques like hierarchical Bayesian modeling might be useful to leverage the global database for more sparse data conditions at other volcanoes. And finally, I'd like to just float some ideas to you all regarding potential community efforts for best practices for PDC data. So for example, the Tephra community has developed best practices both for data collection in the field, as well as some of these community resources, such as the eruption source parameter database and the papers associated with it. There also seems to be room maybe for leveraging some of these global databases for some of the model benchmarking exercises that we'll hear later in the session from various people. I think Sylvain is giving a talk on this. And finally, we're really hoping to develop FLODAT into more of a community resource that can be used for modeling, So over the coming years, we hope to have an easier to access web portal and things like that, and also to organize some community meetings for input into some of these efforts. Thank you.
Thank you, Sarah. Very impressive work.
Thank you, Sarah.
Any question from the audience? Yeah, Tommaso?
Hello, Sarah. This is Tommaso Esposti-Ongaro. Nice work, and I'm really happy that this database survives in these years and is developed. So, from the point of view of a modeler, I really urge, and I think as a community we should recognize what is needed really for trying to merge our studies, that the most important data that we are sometimes still missing are not only the volume of the pyroclastic flows deposits, which is sometimes very difficult to estimate, but also some idea of the isopachs or the thickness decay with the distance. As Piero said, most of the PDCs stop because they lose their momentum through the sedimentation, and this information is sometimes very difficult to find. Sometimes outcrops are difficult to find. It's difficult to make this estimate, and the same is true for the temperature. An idea of how the temperature decreases along the distance is an information which would be really precious. So I understand that it's not easy to find, but if we develop this database together, I think that we have to go in this direction, and also in some more detailed spatial distribution of pyroclastic flows. But again, thank you for this effort. I think that it's worth joining our energy to compile this database.
Thank you. Yeah, FlowDat does include some of that information, so some of these parameters with distance or more spatial information. However, it's really difficult to sort of put that information into a flat file like an Excel file and kind of post it on the web. So that's one of the reasons why we're hoping to develop a user interface to access more of the data that's in the full relational SQL database.
So the database is also like map functionality? So you can see maps, no?
Not really map functionality, but some of that more spatially varying data is captured in the full database.
Any more question? Okay, thank you very much, Sarah. So we can move to the next presentation that is again virtual. That is given by Natalia Liepienko. Sorry for the pronunciation of the name. Experimental modeling of the entrance of pyroclastic flows into water.
Okay. Good afternoon or good evening. It's just gone midnight over here. My name is Natalia Liepienko, and I am a PhD student at the University of Auckland. I'm working on tsunamis generated by volcanic eruptions, and today I would like to present my experimental modeling of the entrance of pyroclastic density currents into the water and tsunami generation. So volcanic tsunamis are obviously tsunamis generated by volcanic eruptions, and here are some examples all around the world. They've been observed around the world. So there is a Karimsky eruption in Russia, Santorini, where most of you are right now. Then we obviously have Krakatau and 1883, Anak Krakatau, and then the Tonga eruption just this January, which was probably the first time that most of the people heard of 10 volcanic tsunamis, and then a large pyroclastic density currents in the Montserrat eruption in 1997 and 2003. And although the volcanic tsunami has been observed all around the world, they're still relatively rare. But even though they are rare, they do account for almost 20% of all the deaths associated with volcanic eruptions. And the reason for that is they expand the radius of hazards posed by the volcano well beyond the eruption itself. And they're rarely included in hazard maps because the generation mechanisms are poorly understood. So the volcanic tsunamis can be generated by the entrance of pyroclastic density currents into the water, caldera or flank collapse, underwater eruptions, or a combination of all of the mechanisms. And a prime example is the Tonga eruption in January. And that's when things get really interesting. So the destructive nature and the complexity of the phenomena makes it really difficult to study them in the field. So the field data is limited, and most of the studies include experimental numerical modeling. So I would like to present my experimental work on tsunamis generated by pyroclastic density currents. So we have designed a novel experimental setup and built it in our lab to model PDC-generated tsunamis. And these tsunamis were modeled by releasing a granular column of glass beads from the reservoir. The beads then ran down the ramp and entered a water-filled flume, generating waves. And to mimic the dynamics of PDCs, we introduced compressed air supply below the reservoir and below the ramp to fluidize material so that it behaves like a fluid, like a PDC. The granular material was made up of ballotini glass beads of 2 different diameter size, and they were mixed at various proportions. And that was the main objective of our study, to explore the effect of the particle size distribution within the flow on wave generation process. And in order to do that, we analyzed the process in 3 stages. So first we looked at the kinematics of flow on the slope. And then we analyzed the entrance of the fluidized flow into the water and the subsequent wave generation. And finally, we analyzed the data collected in the near field region, so the leading wave and the underwater gravity current. So firstly, we have the fluidized flow on the slope, and from these we were able to determine the properties of the flow, so the properties of the wave maker. So here are snapshots of the flows moving down the ramp before they enter the water. I will refer to the experiment types by the proportion of small particles. So we detected the boundaries of the flow and the velocity profile. So we found not only the average velocity of the front, but velocity profile. And with increased fraction of large beads, the velocity profile becomes more uniform, but the average velocity decreases. And then we characterize the flow by 2 Froude numbers, so the flow Froude number and the impact Froude number. Flow Froude number, we have it larger than 1, and it informs that the flows are relatively thin, kinetic energy is dominating the motion, and the impact Froude number might be potentially more interesting because for the tsunami generation, because it informs about the ratio between the average flow velocity to the shallow water wave speed, so the speed at which that generated wave is able to leave the impact zone. And as long as that impact Froude number is greater than 1, the flow will keep pumping the energy into the system and generating waves. So then we move to the second part, so the entrance of the fluidized flow into the system, into the flume, and upon entrance, the flow transfers much of its kinetic energy into the water and generates a forced leading wave, and it will keep forcing that wave until the Froude number is greater than 1, so its velocity is greater than the shallow water wave speed. And from these, it has some snapshots for all the experiment types. So we noticed that there is more violent braking with higher proportion of large beads. And we can also see that the underwater flow front becomes more inclined with higher proportion of large beads. So for the flows with 100% of small particles, the flow is near vertical and it kind of pushes the water away. These videos were also used for particle image velocimetry. So usually we would introduce some seeding particles, but here the movement of the flow particles was tracked based on the color difference between the flow and the water and within the flow itself. And a very interesting result that we found was that upon entry, the flow separates into a part that's advected by the with the wave crest and a part that's propagating along the bottom of the flume. And we observe that regardless of the particle size distribution. And then we have the third wave generation stage, so the near field. And as mentioned at this point, the impact fruit number is less than 1, so the leading wave is propagating freely of the flow. We see some advected particles, so that part that kind of separated, and the part that propagated along the flume floor now generates this underwater gravity current that's propagating along the flume floor. And this gravity current undergoes many different processes. So it releases air, so the air from the fluidization, but also the air that got entrained during the entrance. We also see a lot of instabilities. And again, here are the snapshots for all the different experiment types. So we see the bubbles, advected particles, instabilities, and although we treat the processes as two-dimensional because the flume is quite narrow, even in that narrow flume, we do see clear three-dimensional features. And when we look at all of those, there seems to be no clear, no significant relationship between the leading wave, the underwater gravity current, and the particle size distribution. So we identified the boundary of the gravity current and found the front and tracked that in time to calculate the velocity of the front. So here we have plots presenting the distance traveled by the front of the gravity current as a function of time and the calculated velocity. So again, there's no clear, no significant relationship with the proportion of the large particles and the velocity. And the overall trend seems to be that within our limited camera window, the velocity is decreasing of the gravity current, and it seems to be about 10% of that flow that was on the ramp before entering the water. And finally, we detected the free surface elevation. So the entrance of the flow into the water generates a high amplitude, solitary-like leading wave, followed by a much smaller trough and some trailing waves. And so this plot presents data for 10 repeats each. And given how turbulent the processes are, the repeatability of the waves is remarkable. We see very subtle differences in the wave amplitudes. The amplitudes are slightly smaller for flows with higher proportion of large beads. We've also calculated the wave celerities by tracking the wave crest and all the waves that are traveling just under the shallow water wave speed. And we've also estimated the potential energy of the waves from the surface elevation and the celerities. And then from that, assuming equipartition of energy, we found the efficiency of the wave generation. So the ratio between the energy of the waves, generated waves, and the energy of the fluidized flow. So in conclusion, what we found is that regardless of the particle size distribution within the analyzed range, obviously, we see that the flow separates into the part advected by the wave crest and the part that propagates along the flume floor, regardless of the particle size distribution, and the kind of ratio, the proportion of the large to small bits has a negligible effect on the wave amplitudes of the generated waves and the velocity of the underwater gravity current. And further work will include particle tracking velocimetry analysis. So this is similar to the PIV, although now we did include the seeding particles. So these are the stars, and that will give us the velocity field within the leading wave and within the water column around the underwater gravity current. So right now that's the leading wave propagating, and the gravity current should be somewhere along the flume floor. And the next part will be to explore the effects of the flow mass and the water depth on the wave generation. And here are some preliminary results. And we've also modeled PDCs using natural pyroclastic material. So we used ash from Taupo. And yeah, all of this were already, all the experiments are done, but they are waiting to be analyzed. Okay, thank you.
Thank you very much, Natalia. Very interesting. Also, for These kind of experiments make me think, for example, of also about Stromboli, the pyroclastic flows that we had in 2019 in Italy, and so this kind of experiment for sure is very important to better understand the behavior there. And I have a question about just to clarify a little bit. So for me, so you think that which are the main parameters? So if I want to correlate the height of the wave generated by a dense flow like this and the parameters of the flow, you think that, so grain size distribution is not important. What is the, so, but is more important like the velocity, the potential energy, the volume? So you need like the integral characteristics of the current, like the volume, or something more specific like the velocity and the height? What do you think?
Yeah, so this is the, now that this kind of, my screen is not there anymore. So because the grain size distribution proved to be probably secondary parameter affecting the wave amplitude, we looked at different water depths and the flow mass, and that seemed to be affecting the wave heights quite significantly, especially the flow mass. And then obviously the flow mass affects the velocities, the impact velocities. So it would definitely be the velocities and the flow mass and so the volume. It looks like there is some sort of limiting water depth that at some point it doesn't seem to be making that much of a difference. And then there's kind of this ratio of the thickness of the incoming flow to the water. And at some point, it doesn't really make any difference anymore. So this is this kind of next steps that we are looking into right now.
Thank you. Any more question for the audience?
Matteo, I have a question.
Yeah.
Hi. I have a question. It's more a curiosity. I was just wondering if adding a parameter like temperature, do you think that the steaming can affect the sedimentation rate or the generation of the waves in some way?
That was the initial plan, but then COVID happened. And we had to change.
I know it's
everything.
difficult to insert temperature like a parameter, but I was just, curious.
But yeah, this was our plan, to have a look, and also to have a look at the kind of heat transfer between the flow coming in. So I don't think it will be a big difference, but it would be really interesting to see how much it would affect. But yeah, that was the plan. Really
thank you.
fun.
No, it was just a curiosity. Thanks, Natalia.
Thank you.
Any more questions? Okay, thank you, Natalia. We can move to the next presentation, which is
Pete Rowley.
Yeah.
Yeah, it's velocity profiles in sedimenting pyroclastic density currents. Pete Rowley from University of Bristol.
Okay.
Go ahead.
Hi, everyone.
Hi, Pete.
So the work I'm presenting today is very much the work of Greg Smith, who's our PhD student, but unfortunately can't be here to present it, so I hope I do it justice. We've spent a lot of time looking at PDCs over the last 30 or 40 years, and what's become increasingly apparent is there is a huge catalogue of really interesting bed forms in them. And I think maybe in the earlier kind of, when people were first starting to look at these things, a lot of the strat logs ended up recording cross-bedding or dune bed forms. And I think what we're beginning to learn now is that actually doing some really careful sedimentology on these is going to allow us to get a lot more information from these deposits in the same way that fluvial geomorphologists have been doing for quite a long time. And Greg's really been looking at this over the last kind of 5 years or so. So there's just some examples here. On the top left there, we've got Neapolitan yellow tuff. We've got Mount St. Helens in the top right, Colli Albani bottom right, and Tongariro in the bottom left. So a whole range of different things getting deposited by these currents. And what we do is tend to look at these through an experimental lens. And in particular, what we're interested in is the propagation of dense granular flows. And in order to do that in a way that's realistic to pyroclastic density currents, we've got a fluidization system in place. So in a natural pyroclastic density current, you have a lot of outgassing from the juvenile fragments. You've got a lot of entrainment of air from the natural system. In the lab, we're dealing with much thinner flows, but we're stuck at the same grain size. We have to use the same kind of things as in the natural currents. So we have to simulate this fluidization. And the way we do this is having a porous base in the flume that we can then inject air through. So we fluidize the current. And with this particular apparatus, we've got separate chambers in the base, so we can have different levels of fluidization as the flow propagates. What that allows us to do is to start with a fully fluidized current moving in from the left, and then we can defluidize it to enable it to start forming a deposit. And when we do that, one of the cool things we've found is that pretty much any time we do this, we start forming bed forms. And depending on the flow conditions we've got, we get different styles of bed forms. Pretty much all the slides I'm showing you, in fact, all the slides I ever show, flow is pretty much always from left to right. So we get everything from very shallow kind of planar, almost kind of stratified bedding type forms, all the way up to very steep backset kind of stoss bed forms that in a hydraulic system might be related to a hydraulic jump, those kind of things. So in different conditions, we have formed all of these different types of thing in a dense granular current. And I'll keep emphasizing this dense granular thing because there's similar bed forms being seen in the turbulent and dilute regimes. So we're able to form quite a range of bed forms in quite a range of different conditions. But the important thing with the dense system is that you have to pass this sediment down through that dense current. So you have a dense granular flow and some kind of substrate underneath which it is grading, it's gradually forming. The interface between that substrate and that granular flow is not as straightforward as we'd like. Now, as far as these bed forms are concerned, and this is already well-published stuff, but essentially looking at different parameters of currents and the kinds of bed forms they form. So in blue circles, we've got very steep, we've essentially just very easily simplified it here to steep, shallow, and planar bed forms, depending on whether they were 0 to 5 degrees, 5 to 15 degrees, and above 15 degrees. And looking at different flow parameters that form these different kinds of bed forms. But what we then wanted to do was go on and really think about the processes that are doing this. And this is a figure, we've just added some color to it. This is original from Brenny and Koklar in 2002. And it's an amazing document, and they propose some great ideas, but a lot of the ideas put forward there were fairly poorly ground-truthed. So what they have here is 4 end members of pyroclastic density current structure, looking at the concentration of the current in red and the velocity of the current in blue here. And we've always got some kind of substrate, and we've always got some kind of current above it. And that interface between them is absolutely critical. Now, lots of PDCs, we have just a turbulent overriding dilute current, so we have a very sharp interface, and we can develop bed forms on that quite easily. In the lower half of this diagram is where we start getting into a mess, which is these dense granular flows, because we have to have a very, very high particulate concentration, and then we have this loose substrate underneath. And as you can see, we've got this kind of flow boundary indicated. That flow boundary is indicated here as a kind of sharp line. In reality, we have to start thinking about a flow boundary zone. And it is a thing with some thickness. At the bottom of that, you have static deposit. Above it, you have free-flowing current. And in the middle zone, you must have some velocity gradient that takes you from 0 into the main current. And it is not at all straightforward. Little sidestep for a minute. We are not the only people talking about density currents. The turbidity current people have been looking at these things for a long time in Newtonian fluids. And I've spent the best part of 15 years being very, very cautious about listening to anything the turbidity current people say, because it's a Newtonian fluid, they've got it much easier. But they have got this idea of a viscous sublayer. So you have a turbulent, clear water flow, but it has to contact the edge wall, and there has to be a static movement condition there. And so they have this model for a viscous sublayer which grows with the thickness of the flow above it. And it's a way of describing a slower moving area at the base of the velocity profile in these turbidity currents. And this viscous sublayer is pretty well defined in the Newtonian system. Now, what we're interested in doing here is taking a model for a granular flow and understanding the nature of this flow boundary zone. The flow boundary zone must have some thickness, and the way we think about it conceptually when we've been doing these experiments is you must have a granular flow, and the granular flow must have an increasing velocity at its, as you move up from its base. Below it, as you go into the flow boundary zone and down into the static deposit, eventually you have to end up with a zero velocity condition. So what we do in our experiments is measure the velocity profiles, and we look for this inflection point between a growing velocity in the flow boundary zone to a linear velocity gradient at the base of the flow itself. Okay? That's how we define the flow boundary zone in the experiments. What we're going to come on to talk to a little bit later is this idea of a viscous sublayer. We'll come back to this image. But this is the critical definition we've been using in the experiments, because this is something we can go and measure. So we run a whole bunch of experiments, and we do some both PIV and PTV to track particles, track velocities through these currents. So these are velocity maps of currents moving from left to right. In the top, we've got something very similar to the presentation we just saw, actually, where they were sending a fluidized current down a solid base into water. You have a very, very uniform velocity gradient through the current and a very, very sharp velocity gradient at the base of the flow. What's interesting is as we start forming a deposit, which takes us to frames B, C, and D, the current slows down and the gradients within this thing start becoming a real mess. And if you look at panel B here, we've got a very high velocity zone at the top where we've got a nice free-flowing surface current, but actually we've got reasonable velocities inside what would normally be thought of as the deposit. So we have shear within the deposit going on. So we start looking at these, and these are a series of panels as the current is propagating with velocity profiles put through. So these have been done computationally and then manually checked. So we've got a good vertical resolution on these. And as you can see, actually, the shape of this velocity profile is pretty variable. This top panel B, actually what you can see was getting highlighted in the velocity map is we have a, excuse me, get the pointer in the right place. This very, very high velocity zone here is actually some kind of transitional bit between dense and dilute. We've got a weird area on the top of the current that is moving quite quickly. But we do have an increase in velocity internally to the rest of the current. We have something quite odd going on here. In the other panels, you can see again, we have a changing velocity profile. So these profiles are quite variable. And importantly, these profiles are systematically changing with the angle of the bed forms that we're generating and the shape of the bed forms that we're generating. We can also look at it in terms of, in terms of the flow thickness to what kind of bed forms are getting formed. We can look at it in terms of the thickness of the flow boundary zone in terms of the bed forms that are getting formed. And we can think of it in terms of dimensionless parameters like Savage number. So essentially looking at whether things are increasingly frictional or not. And as we get to steeper bed forms, we have increasingly frictional currents and increasingly frictional conditions in the flow boundary zone. Now let's just pop back to this viscous sublayer for a minute. This is defined by essentially the thickness of the current and the shear velocity within it. And if we take these values and we ignore the fact we're not in a Newtonian situation, but we can calculate shear velocities, we know flow thicknesses, and we plot what we measure as a flow boundary zone thickness and our calculated viscous sublayer, actually what we find is a really amazingly good correlation. It starts to go a little bit funny as the currents slow down and we go to these quite steep bed forms. But in general, it appears like the viscous sublayer may be a way of approaching these flow boundary zone thickness estimates in other settings where we don't have sidewall observation to get our velocity profiles out. If we can get flow velocities, if we can estimate shear velocities, then we can use a viscous sublayer model to think about how thick the flow boundary zone is and therefore what kind of bed forms we might be generating. Finally, that brings us on to the idea of the law of the wall. Law of the wall is related to the whole viscous sublayer thing, and essentially it's a way of looking at being able to calculate shear stresses. And we can do that then for some of these currents that we're depositing, and it's the same panels here, same parts of the flow. We have the velocity profiles in pale blue, and we've got the calculated shear stress using the law of the wall through the current. Now, I am not going to pin my reputation on these, but this does give us a way to start thinking about shear stresses in these dense, granular, and flow boundary zone controlled conditions, which then opens the doors for us to start doing some other pretty cool stuff. So, that's me done. some quick notes. The maximum velocity tends to be closer to the free surface in non-depositional currents. There's a really wide variety of velocity profiles, even in simple dense granular systems. The flow boundary zone does correlate to different bed form growth conditions, and viscous sublayer law of the wall calculations might be a useful tool in approaching some of these otherwise quite difficult to access dense granular systems.
Thank you, Pete. One fast question. Thank you.
Okay.
What about the velocity profiles are quite interesting. So how far are there in the boundary layer, how far are the profiles from the logarithmic shape that you expect? And above the boundary layer, do you have in the literature any hint about the shape that you can expect there?
The flow boundary zones are, now we've only looked at it with so the charges we're using are simple single grain size, but with a 5 or 10% doping of large particles that we can use for tracking. So in this situation, we've got a fairly monomixed simple current, and everything we've looked at has been with that same grain size. Under those conditions, the velocity profiles, the ones I've shown you, are basically representative of the full set we're seeing. I suspect as we start going to more complex mixtures, we're going to start seeing some really weird interactions with how grain size and sorting mechanisms start propagating that flow boundary zone into different depths and heights into the substrate. But we are definitely in this process. That flow boundary zone is not just the flow slowing down at the base. This is entraining loose material into the current. So, and in terms of flow energies, accelerations, decelerations, momentum, there's a really complex series of things going on here. So yeah, as far as the depth of that penetration and where exactly it's going, in these conditions, basically what I showed you, it's propagating maybe a centimetre or so into substrate. But yeah, in different conditions, I suspect it's going to get weird.
Your experiments are underwater?
No, this is it's a dry, gas fluidized granular flow in air.
Okay, any other question from, yeah, Ilaria?
Which grain size are you using for your experiments?
Funnily enough, exactly the same ones as the previous talk. So these are 63 to 90 micron. They're a sandblasting media. It's a silica lime Ballatini spheres, microspheres. Yeah.
Okay, thank you, Pete.
Thank you.
Thank you. We can move to the next presentation. It is by Pierfrancesco Dellino. Inverting sediment bed forms for evaluating the hazard of dilute pyroclastic density currents in the field.
Okay, this is the second part, when we more or less understand that we are doing two complex things for people living in the field. Okay, so we know that there are plenty of models. This is the synopsis, you know. I need to read because I forget everything I write. We know that there are plenty of models for simulating or reconstructing pyroclastic density currents. We also know that the more we implement models with differential equations and input parameters, the more the only people that can actually use and take advantage and knowledge from these models are just the modelers. We were wondering, is there a way to simplify the models without losing too much of the mathematical and physical underpinning, still making them usable and useful for the volcanological community working on volcanoes, that is, working on the field? With this aim, we inverted some of our recent models of dilute pyroclastic density currents so to use field data as input in a diagram and retrieve the impact parameters of the parent flow, because we are interested in the parent flow. Okay, as shown in my presentation, previous presentation, we model PDCs by means of a multi-phase turbulent boundary layer approach, which is more or less the equation you were seeing on the upper part as Peter was showing. The word is all the same. And everything moves at the base is in the boundary zone, which is in the viscous sublayer, even in turbulent boundary layers. By experiments, we get additional models of entrainment, sedimentation rate, and below transportation rates. And by the combination of the models, we construct an experimental diagram, we have seen that team, of bed forms that link deposit structure to the sedimentation rate and bed load transportation rate. I remember the bed load transportation rate is the amount of material that is moving at the base. More or less the thing that Peter was showing us, but we are at the base of a fully turbulent thing. The diagram then has been validated by application to actual deposits. This is the sedimentation rate and the bed load transportation rate. You see that the most important thing, as Peter was saying, is the shear velocity. If this thing is going to work, it should be better anyway. And by combining things, we saw this diagram. Now I'm showing some of the actual deposits that fit in the experimental diagram. Okay, it doesn't work. Then, in this work, we focus the attention just on the stratified part, not on the massive part, and populated the diagram with additional field data from wavy layers of PDC that range in median size from 4 phi, which is 64 micrometers, to minus 2 phi, which is 4 millimeters, and wavelength from 10 to 200 centimeters. The deposits come from Vesuvius, Phlegraean fields, and volcano in the Aeolian Islands. This is a recent paper on it. So this is the diagram, which is populated by additional data. This is, for example, a dune-bedded deposit from a pyroclastic density current and Vesuvius. And this is a ripple-structured deposits at volcano. Okay. This is more or less the range of deposits we measured and plotted in the diagram. Then we inverted the model equations to obtain a system in which the only independent variables, the field data, should be grain size and wavelength of the dunes and ripples, and the dependent variables were the input parameters of the current, dynamic pressure, particle volumetric concentration, and always the guilty shear velocity. By doing this, we lost some of the details of all the mathematical and physical implementation of the original model. Anyway, the data collapsed well in the simplified diagram with high correlation coefficients. I'm showing 4 of the diagrams where you have as independent variable here the bed load transportation rate, here the product by shear current and particle concentration, here the sedimentation rate, here lambda, which is the wavelength, and other variables by which we can obtain this system of equations, which when you set wavelength and grain size of the deposits, you can retrieve the shear velocity, the particle volumetric concentration, and automatically by the boundary layer, the velocity, and the dynamic pressure, which is the mechanical effect of the pyroclastic density current on a building. And plotting results, for example, you can see that when you have a very long wavelength and a very coarse grain size, you reach velocity in the range over 100 meters per second, which is more or less the velocity that we expect by very big pyroclastic density currents. This is the case of the wavelength against the particle volumetric concentration. And you have high particle volumetric concentration where you have very big, very long wavelength and very coarse grain size. And in this case, you have wavelength against the particle mixtures, the density of the mixture, which is higher in the case of the coarser grain size. Then the dynamic pressure, which reaches values over 20 kilopascal 20 kilopascal means that you are destroying concrete buildings. And when the grain size is very coarse, and at the end, the sedimentation, the wavelength against the sedimentation rate. Then we can also plot all these data in a table, and in this range of values, this is the wavelength, and this is the grain size. You can have this table in the field, and you are able to measure the wavelength of these dunes and ripples. And have an idea of the grain size, you have the range of values of the dynamic pressure, particle volumetric concentration, and the sedimentation rate. So this can be used in the field. And okay, I'm quite finished. And we hope that the use of these PDC metrics can be of help to field volcanologists in the reconstruction of the impact of DPCs and for the other assessment of active volcanoes. So colleagues are encouraged to stress the metrics and report their experience. In the original publication, there are other tables that are more easy to use in the field. So we take the responsibility of the range of results, which are expressed at the average plus or minus 1 standard deviation unit of the probabilistic solution of the model, because deterministic solutions are not at home here. If you remember the problem of measuring velocities in granular flows, you understand that the deterministic ideas are not at home here. Thank you very much. I'm finished.
Yeah, super in time. Any question for the audience? Or from the virtual audience? No, I have a question. Don't escape.
It was a system.
No, I would like to better feel the meaning of this model that is very interesting and also is can be like very usable. No, so as far as I understood, it's a shallow water model. Like no, it's not a shallow. So I would like to understand where, which is the physics that create waves in the deposit. Now, from where is flowing? From where are coming these typical frequency or this lambda, if you want?
Okay, the dune beds and the ripple beds.
Sorry, we cannot hear you. Okay,
yeah.
Thanks.
Let's say when we speak about bed forms, starting from centimeters to megadunes that can have wavelengths of tens of meters and height of meters, we are speaking of something that was experimented in flumes for the fluvial part, and in part but with less success for turbiditic currents, but we know they are in turbiditic currents. That way, we inherit this, let's say, from mechanical sediments starting from sedimentology. Then you can use the principle of the waves underwater when you have a free surface, when you think about the difference in velocity between the bedload that is moving and the current that is moving at the free surface, okay? That defines the waves. The other problem is that in free surface fluids, like turbidity currents and pyroclastic density currents, the real meaning of these waves and how they are formed and the celerity is a little bit less well defined. But anyway, we know that in the case when you identify free surface, this has to do with the difference, let's say, in velocity between the free surface waves and the material moving at the bedrock. Let's say it depends on the Froude number, or let's say it depends on the modified Froude number, in which you use as a gravity the excess gravity, which is the difference between the density of the mixture and the density of the surrounding fluid. So the celerity and the formation of the waves depend on the Froude number. Then from that, the story of the supercritical and undercritical currents forming different propagating or regradating bed forms is a classic in classic sedimentology. The problem is to define the velocities, the shear stress, and the velocity profile in the current. It's quite easy to do that in a quite lowly concentrated current when you have the logarithmic velocity profile, which is the lowered wall. The problem starts when you have a big part of the sediment that is moving, which is the bed load. But in that part, which on the turbulent boundary layer is the viscous sublayer, everything happens that forms the bed forms and the various integrations. So we have experiments by the flumes, and we have this. But the basic is the modified Frog number, which is something that works in volcanology also, even when you form collapsing columns.
So you can use this model just for surges, or do you think that, so for a field volcanologist, when there are some prescription that you want to suggest to people that want to use this model?
Okay, since really now volcanology is an hobby for me because I do administration. I think that me and Peter, we speak in the same language with different words. First, we have to adjust the languages, then we can use these concepts everywhere. But we need to adjust the language. As in volcanology is a problem also for communicating risk.
Okay, thank you very much, Pierfrancesco.
Thank you.
So we can move to the next presentation by Valentin Guignot. Benchmarking of concentrated pyroclastic current models using synthetic topographies and large-scale experiments.
Good afternoon, everyone. Sorry, it's not Sylvain presenting today. The confusion. I'm going to present my own work, so I think it's fair. So this is the result of my postdoc. I've been working in the past 2 years with Sylvain, 2 to 3 years. And as Matteo presented, it's about the benchmark initiative. Started a couple of years ago in the community. So I think after all this talk, we can all agree about the complexity of pyroclastic density currents. And today it's still very challenging to model them, even partially. So we have a large diversity of numerical models today, and it's time now to try to develop methods to define their ability to reproduce key flow dynamics, and especially for PDC hazards. It's very important to try to evaluate that. So in 2020, in this study of Tommaso and collaborators, we have now a framework, try to evaluate PDC models, try to follow all these verification steps. We can talk about the confirmation with the mathematical, the validation, and I will be talking about the benchmarking, which is an intercomparison of models, and most of PDC models have been verified, validated with a confirmation mathematical, but we never did any benchmarking before. So this is why this study is here, and we had to split it, this initiative split between dilute PDC models, more turbulent, and concentrated pyroclastic density currents. And this is this study that I will be talking today. So it's in 2 steps, and I will first show you the first step of this project, which is the synthetic benchmark. We did publish 1 year ago and built in a volcanology. And the idea was to evaluate only concentrated PDC models, and we selected probably the most common approach, which is the shallow water approach or depth of ridge. And for that, we selected 4 very used numerical models for that: Titan 2D, VolcFlow, but also ShellTop, used for mass flow modeling, and the new model from Tommaso and Mattia, Emacs, SFlow 2D. So we try to create synthetic topographies that will best mimic the topographic features that we see on PDC is the overspill. So the overspill is the capacity of PDC to escape their confines and leave the valley. And this is very common after either a bend in the channel, either a bend, a break-in slope, an obstacle, or the constriction of the valley. So we have a narrowing. So we tried to use these 4 topographic features, created these simplified topographies, and test this model. Are they able to reproduce this overspills phenomenon? And of course, we had to do a control test with just a simple flat incline. And to test also the importance of the mass flux in the valley, we just do 3 simulations for each cases with a low, medium, and a high mass flux rate at the source here. And we will see if we have a big difference for the formation. So let's go very quickly about the result we have for, first of all, the flat incline case, the control case, and the bend case. So we have the result for Titan 2D here, Vogflow, Shaltop, and Emacs. And the colors are for the different simulations. So in red, we have the low mass flux. In yellow, we have the medium mass flux. And in blue, we have the high mass flux. They're just superimposed on the map, so we can see all the results in one result. Here we have the result also for the high mass flux, medium mass flux, and low mass flux for the thickness at the point number 1 here, the velocity of the center of mass and the velocity of the front, and the colors, sorry, it's not super clear here, but each color is for one code. The idea here is that Vogflow, Shaltop, and Emacs have very close results, pretty much the same extent here, but not Titan, kind of faster. You can see the curves here and spread much more. And here's the result for the bend case. Good thing we reproduced the overspill phenomenon at the bend for 3 models, but we don't have exactly the same results. But they're still close, and again, Titan 2D seems a little more, little faster again. I would just focus on break-in slope result and obstacle, not for the constriction case because we had a problem with Titan 2D, but this is just an overview of the results. Here again, we have very close result for the break-in slope for these 3 codes, not really for Titan 2D. And finally, the obstacle, we almost have overflows before the obstacle because we have the accumulation of mass before the flow can cross the obstacle. And it's not exactly the same dynamic between Shaltop, which is really accumulating and then overflowing, and the other codes who are actually crossing the obstacle before with a very thin front. So we have already on the limits of this depth of range approach. So just to conclude as quick as I can, it's good for hazard assessment that Vogflow, Shaltop, and Emacs give close results, but Titan 2D was always faster, and this is a very good point for the benchmark because we have identified actually a bug in the definition of the Vermeer rheology for Titan 2D. So it's been corrected, and there's a release paper, a common, that's been actually released months ago, I think. And they also clarified the source of this code. So this is the first application for the benchmark. Question we asked, why do we still have discrepancies between Vogflow, Shaltop, and Emacs, even though we use the same approach? So in the paper, we have identified 3 sources that could be responsible for these small differences. The difference is in the velocity projection. We have models with, for example, velocity tangent to the topography, or Shaltop, who is actually doing the 3-dimensional velocity. We have different topographic curvature calculation. Vogflow is using an approximation of the curvature. Shaltop is taking the full tensor of the curvature. Emacs wasn't using any curvature term at that time. And finally, we also have the numerical scheme that can induce some little discrepancies. So overall, the synthetic benchmark was very useful. We saw that for Titan 2D, but it seemed very difficult still to quantify the differences between all these models. We can just compare them together in these maps, but we have nothing to compare with and then quantify the differences. And this is why it's so important to create an experimental framework to compare with. And this is the second step the project that we're still working on is developing an experimental data set that is going to be used for the next benchmark. This has been submitted a month ago, and this is the new experimental apparatus that I created in Tampa, in Florida, in USF. The idea, it's a long flume, 6 meters long, where we have a reservoir over there, where we put the particles and then we release them with a sliding mechanism. It's a dam brake configuration, and we have a long channel here with a transparent part, and this particular part here is where we are going to try to reproduce the overspill phenomenon, and you recognize the bend as we did for the synthetic benchmark. So we have a large bank in wood here to try to study the overbanking flow if it occurs. And again, we're using the same particles as Natalia and Pete, the 90 micron glass beads, because we are fluidizing them in the reservoir. So they are granular flow, but initially fluidized flow. Okay, it's moving. So I will present you very quickly the result of 20 experiments, and this is the result for PIV calculation on the transparent part of the channel at 1.5 meters from the reservoir. We've measured the thickness and the velocity of these flows, and the only thing we change in these 20 flows is the slope. So, so we are trying at 3, 6, 9, 12, and 15 degree angle. So the slope is very gentle, but it's pretty much what we see on the field. So it was interesting. So yeah, actually the color here, the colors is the slope. So what we see here is we have an important thickness variation, an important velocity variation through time, and we can identify the passage of the front, the passage of the body, and what we can call the tail, so the end of the flow. And it's pretty clear with the velocity that the higher the slope, you can see here in dark is 15, in green is 3, the higher the slope, the higher the peaks. So we really increase these 2 peaks when we increase the slope, so we increase the velocity of the flows. Now, if we combine the velocity and the thickness, we can calculate the discharge rate, and this is the result for discharge rate evolution through time. Again, we can still see these 2 peaks in the discharge rate, so volumetric rate, one for the front and one for the body. So again, the slope increases the height of this peak. It's pretty clear here. So all this unsteadiness in the internal properties actually is one of the causes of the overspill. And we were successful at forming overspill at the passage of the bend. Here is a photo on the top of the experiment. We can still see the bend here. And this is the passage of the front of the flow. And we have 2 types of overspills. The first one you're going to see here is what we call the front splash, which is mostly a deposit. Nothing is moving. It's just the front collapsing on top of the valley bank. And this is very thin. And we only observed that for 9, 12, and 15 degree experiment. Now, if we push to 12, we actually can start to see this emerging from the first edge of the bend. And this is a secondary flow, which we call the overbank flow. So it starts to form at the first edge and propagate in the same direction of the channel, pretty much like we can see in the field. And this was only for 12 and 15 degree angle. So this is funny because we can correlate these 2 overspills with the 2 peaks in the discharge rate. We can have the front overspill when we have the front that is going with the first peak, and then the overbank flow with the second peak. So this is very very rapid packing of all the results. I will just try to summarize that as the generation of overspill in Pyroclast is linked to the velocity of the parent flow. So if we increase the slope, we increase the velocity, and some that we have a threshold. After 2.93 meters per second, we start to have overflows. And we have a lot of unsteadiness in this flow. So with this variation of thickness and velocity, it can cause this called the super elevation of the flow at the first edge of the bend. And then if we have enough speed, we're going to have an overbank flow. So the dynamic of these overbank flows are actually followed. We'll have more data in the next years, but here it seems that the maximum overbank flow runout is correlated with the maximum channel as flow runout. So it's pretty important. Now I'm going to just give you some perspective for this work. It seems that the generation of overspill is a good test for numerical models. I think it was very interesting to have that in the benchmark. And I think it should be still integrated in future benchmarking exercises because it's a very important control point for concentrated PDCs. And now, as I said, we are starting to constitute a data set with all this experiment. We'll have different configuration, not only the band, but also an obstacle and everything. And this will be available for modelers who wants to do a future benchmark exercise with finally a reference case usable. And this is a try with workflow here. So this is the potential. Thank you for your attention.
Thank you very much. And we have a question from the online audience, from Carlos Laverde, indeed. He said, "Hi, great talk. What value of basal friction angle do you use in your benchmarks with Titan 2D? A low basal friction angle value could be to explain your results?"
No, it's, we are not using we're using a basal friction angle, but we're using Völmi rheology. So we have a little bit of some sort of turbulent friction too, and the angle is 30 degree. So we're trying to fit everything with 30 degree, and this little friction with the Völmi rheology, but the big was from the implementation of the source exactly for the Völmi rheology. So it cannot be explained with anything. They did a lot of tests, Abani and his students, and yeah, it was a small problem for the source, but yeah, it cannot be explained.
Any other question from the audience? Yeah, Tommaso?
Thank you, Valentin. Great to see that these advances, and we are looking forward to see the data and to have this data available, obviously. Question about, okay, you have shown this, I agree that overbanks is something, models are very sensitive to this, and we have noticed together, so yeah. I think that it's very good stress test for the models. But have you already done experiments without any bands or any obstacle or anything? I was wondering whether you see any pulse in the flow at this scale. This would be really interesting to
very good question
to know.
Yeah, actually we designed the thing with the band immediately because we wanted to see if we can have overspill. So we dimensioned everything correctly. Now that we have it, that's the next step, because I want to verify if we still have these two peaks, if we have a straight channel, because it might be just because it's the fruit numbers are super high, so we have a lot of wave interactions, and the waves are actually super fast. So probably that we're going to have the same unsteadiness if we have just a straight channel, but maybe the intensity of the peaks will be a little bit different. And maybe the interaction with the band will be actually a little easier to see. So it's the next step. Yeah, kind of a control experiment. Thank you.
We can move to the next presentation by Tomohiro Tsuji. Does water enhance pyroclastic flows traveling? Multifaceted study on deposition temperature of ASO4 pyroclastic flow, Japan.
Hi, this is Tomohiro Tsuji from Yamaguchi University, Japan. And this research is the work of us, especially in the Kento Osawa of our laboratory. And the figure is pyroclastic flow entering in the ocean at 1996 Soufriere volcano. And the key question is, does water enhance pyroclastic flow traveling? It's a very important issue to discuss the ability of a large-scale pyroclastic flow and yes. And there is an idea that the water enhanced pyroclastic flows traveling. That's because the magma water interaction can promote the fluidization of PDC. And flat surface of ocean facilitate the moving of PDC. In contrast, there is another idea that when magma water interaction occurred on the flat surface of ocean, the direction of PDC is not controlled so that it doesn't facilitate forward moving. So what is the true story? And then we discussed the influence of water on the long running of PDC based on the occurrence and the position temperature of ASO4 pyroclastic flow deposit here. And ASO4 eruption occurred at 87 Ka at Aso caldera, Japan. The very big eruption. The eruption volume is 930 to 1860 cubic kilometer, and this is the second largest in recent 100 year. And the eruption produced ASO4 pyroclastic flow deposit and the widespread tephra, this and this. The ASO4 PFD is very unique because it travels 170 kilometers, very long distance from the source. And it is thought that it traveled across the Seto Inland Sea, this map, and this is a Kyushu. And this island, Yamaguchi Prefecture, is here. And the black dots are outcrops. There is the distributed at the central part of Yamaguchi Prefecture and not distributed at eastern part. So this is important, and I discuss later. And the 8 units have been recognized at the western part of Aso caldera, and 3 units have been reached to Yamaguchi Prefecture here. So ASO4A is valley fill, and ASO4Y and ASO4T is low aspect ratio in green bright. So the methodology, well, we observed and sampled ASO4 PFD and measured the temperature. And we, so there is many approaches, and we chose the charcoal reflectance and some remnant magnetization and Raman spectroscopy. The Raman spectroscopy is already published at Osawa Tsuji 2021. So today we talk about these 2 methods. We observed ASO4Y unit on the Yamaguchi Prefecture. So, and the ASO4Y is beige colored massive clay rich layer, including minerals, glass shards, lithic fragments, and charcoals. And shell fragments and accretionary pellets, that is evidence of seawater PDC interaction, are not included. This is a charcoal reflectance procedure. We sampled carbonized wood and washed and separated using heavy liquid and filled in the resin and polishing and measured the reflectance, and the result is here. The average reflectance is 0.82 to 1.29. This is good concentration. And this is a procedure of magnetic analysis. We sampled with constant orientation shape the sample at fixing by plaster. This is the sample preparation. And some of the magnetization is carried out at Koch Core Center. After measuring the magnetic susceptibility, the stepwise sum of the magnetization and measurement of magnetization orientation is repeatedly carried out. And they reconstruct the magnetic orientation, made Zeiger-Belt diagram, and temperature was estimated. This is the result of magnetic analysis. And the stepwise demagnetization was carried out at 18 steps from 220 to 600 degrees. Especially above 300 degree, we measured the orientation at the interval of every 25 degrees. And the red and blue lines are horizontal vertical components. And the lines ideally go to the intersection from lower to higher temperature. And we recognized the thermal remnant magnetization based on the linearity on the Zeiger-Belt diagram, and concentration on the equal area plot. Then the temperature was 325 to 525 degree. Discussion of the charcoal reflectors. These three diagrams are the experiment heating the wood and measure the reflectance. The difference of these are the duration of the time, and the heated the wood and hold the maximum temperature for 24 hours, 1 hour, and 0 hour. And the pink arrow means our measured reflectance. And the converted temperature is over 400 degree in this figure, and 400 degree in this figure. Then in this study, we use these diagrams. The maximum heated temperature of charcoal was 337 to 523 degree. This is a summarized temperature, and the blue colors are charcoal reflectance, and the black magnetic analysis. And we also, the Raman spectroscopy result also plotted as red to yellow color. This is relatively lower than the others, and it's based on the Lahr et al. 2005. That is because the sensitivity of the temperature under 300 degree is not good in this experiment. So we, except this data, the temperature of four pyroclastic flow deposit on Yamaguchi was 300 to 520 degree. Now we plotted the data on the diagram of distance from the source to the temperature. And the data on the 0 kilometer is magma temperature, and these are from previous studies. The temperature decreased from Aso caldera to Yamaguchi, and there is no big obvious temperature gap between the Kyushu and Yamaguchi area. So what does it mean? The SO4 eruption occurred at marine isotope stage 5B, and the sea level was 40 meters lower. In addition, the sea level was considerably lower than minus 21 meters at Ariake Bay here. So based on these, we made the map of parallel sea level. So the pathway of SO4 pyroclastic flow from Aso caldera to Yamaguchi become land. So it suggests that the SO4 pyroclastic flow traveled on land to Yamaguchi Prefecture. Conclusion, SO4 at Yamaguchi includes no sea-oriented particles, and the temperature was estimated to be 300 to 520 degrees. This is close to that of northern Kyushu. At the timing of SO4 eruption, the sea level could have been about 30 meters lower, and SO4 PDC could have traveled onshore and reached Yamaguchi Prefecture. This can explain the no distribution of eastern part of Yamaguchi Prefecture's SO4 PDC. Then it suggests that the seawater could have impeded rather than facilitated the long-distance traveling of SO4 PFD. That's all. Thank you.
Thank you. Impressive measurements. Any question from the audience?
I have a question, Matteo.
Yeah, please.
Hi, nice talk. I was curious if all the charcoal fragments that you measure were full charred, and if you sample it in different parts of the pyroclastic fluid deposit in order to, I don't know if you see any variation in temperature from proximal to distal parts.
So the temperature of, sorry?
No, I want just to know if you see any variation in temperature with the reflectance analysis.
This variation, these figures. So
I can't see, sorry. Oh, yes, yes, that's it.
Yes, higher the temperature of magnetic analysis is the deposit temperature, and the lower 300 degree is the temperature from transferred from the pyroclastic flow to the wood, carbonized wood, and the carbonized wood shows the relatively lower temperature. That means the maximum heated temperature of wood, not deposition temperature.
Okay, thank you.
Thank you.
I also have a question about the interpretation of the data. So how do you interpret the fact that the temperature is decreasing? And also if you can, from this data, if you can say something about, for example, the fraction of partial collapse or total collapse, or the dynamic of the column in general?
It's difficult to interpret the from this data. Yeah.
Okay. Thank you very much.
Thank you.
We can move to the next presentation. It is from Alfredo Esquivel. Reconstruction of the pyroclastic density currents during April 1993 eruption on Lascar Volcano by use of computational physical models.
Hi everyone, good afternoon. Well, firstly, why this volcano for the reconstruction? Lascar volcano is the most dangerous and the most explosive in the central volcanic zone. Is of the Nearest village is 17 kilometers away, named Talabre, with 90 inhabitants. Its eruptive story of Lascar volcano is contained with 33 events, and always between BI1 and BI3, but the one that concern us today is the most explosive, the high explosion in history in 1993 with a volcanic explosion index 4. In the April 1993 eruption, well, it's a subplinian explosive eruption with a duration of 32 hours and with a column, eruptive column about 25 kilometers above the crater. And every time the eruptive column was greater than 10 kilometers above the crater level, the column was a partial collapse, the column. And in this table, we can see a recopilation of a lot of papers with dates or a description of the eruption. It's a summary of the PDCs generated during the 1993 Lascar eruption with date, local time, PDC direction, and the column height observed or calculated in kilometers. We can see it occurred in 2 days, April 19 and April 20. And I want to highlight 2 or 3 events in all the night events or night pulse eruptive pulse. The first one, which one is the 13:15 to 13:25 hour in April 19, with a column height above 20 kilometers above the crater level, with southeast and west and northwest direction. And the second I want to highlight is the April 20 at 9:12. It was formed the most energetic, voluminous, and far-reaching flow in northwest direction. The main areas of this PDC deposit in 1993 Lascar eruption, I like show you pictures of the deposit for look the composition, the extent, and the direction of these flows. And before we can go to fieldwork, but before we did image processing with Landsat TM image before the volcanic eruption with in RGB 42 combination corresponding to March 1, 1992 in picture 8. In picture B is a Landsat TM image 2, but after the volcanic eruption in RGB 42 combination 2 in May 7, 1993. In the picture C, we can see the detection of change at 2% per pixel between the pre-eruption and post-eruption of Lascar volcano in Landsat TM image. And finally, the D picture is the Landsat TM image with band radio image 54, 31, and 57 and RGB after the volcanic eruption of Lascar volcano. This image processing was made for look or decide the exact place for go and measurement the thickness and the characteristic of the deposit. So, moving on to the field work and the methodologies. Fieldwork target areas and points measured from the PDCs. 3 target areas for the research were established in the Talabre zone, in the A zone, Talabre zone, and in the west or northwest zone is the Piedras Grandes zone, and the southeast in the Lejía zone. The data collection was at 55 control points, and each control point was measured thicknesses and frictional angles. For example, in these images, we can see the measure of the thickness in this area, in the northwest area, in west area, between 1 to 3 or 4 meters of thickness. And we can see in these 2 pictures the measure of the friction angles, especially for the Titan 2D model, working with the friction, the basal friction angle and the internal friction angle. Okay, for comparing numerical models, we worked with EnergyCom, the most simple formula or numerical model, ball flow, and Titan 2D. The original idea was working with IMEX with Tommaso and Mattia, but the COVID and pandemic is limited to three models. So the most simple the process or most simple numerical model, EnergyCom, is for essentially limit or understand the maximum scope of eruption with a fit in the topography, especially in the northwest section here. So in result for in bulk flow, I want to, for time, now show you the 9 events, but highlight 3 events with bulk flow. Firstly, the first one, the initial eruptive pulse in 10:12 a.m. We can see in these 3 images in simulation at 60 seconds, 120 seconds, and 300 seconds, with a scope in northwest of 26 kilometers, in southeast 3.28 kilometers, and a probability of the thicknesses between 2 to 3 meters. Moving on the pulse or produced by the highest eruptive column with a height of the 23 kilometers. We can see a scope of the almost 6 kilometers, 4 kilometers in west direction, and 4.65 in southeast. And the simulation in this picture of 260 seconds, 300 seconds, and 600 seconds. Oh, okay. So in this simulation is the longest pyroclastic flow with a northwest almost 7 kilometers in this direction, and with thicknesses from 3 to 4 meters. Moving on to Titan 2D, the simulation of the initial eruptive pulse changed a little bit. The scope, or the longest scope in northwest to 245 kilometers, and so it is 3.86 kilometers. And the thicknesses is similar with world flow, with up to 2 meters. And in the scenario of the pulse, eruptive pulse with the highest eruptive column, we can see a difference with world flow. Here in northwest direction, reach to 5.31 kilometers in this zone, and world flow is not in the same way, or no produce the same result. And conclusions. Obviously, the first one, or the more simple, is with EnergyCon. We have a better adjustment, or better fit can be observed in its maximum rank to the northwest with EnergyCon. It's explained in considering the slope and the topography with the flow is the transport. With EnergyCon does not deliver that or maximum final speed nor transport time, making it impossible to compare these characteristics with the other, obviously with the other dos models, Titan 2D and Blowflow. Titan 2D resulted a final maximum velocity of 4.93 meters per second that occurred in the 13:15 a.m. eruptive pulse on April 19, while in ball flow it is 2.65 meters per second, and in 9:20 a.m. It's a difference in both models. This is due to the different approach that each model has with the characteristics relate to cohesion, density, and viscosity. Ball flow being much more complete in this sense, while aspects such as the internal basal friction angles that determine the scopes and the speed. It is in Titan 2D a parameter of fifth order and of much more sensitivity. And finally, the accumulated volume, with, after all of inversal modeling, generating all the eruptive pulse simulated by Titan 2D result in 0.018 kilometers cubic, while in ball flow it was 0.022 kilometers. This is considered for the simulation as an initial mass pile on the crater in the case of Titan 2D, and as a volume with a constant rate function or constant feed rate in the case of ball flow. And the maximum time that the simulation took to stop for some flow associated with a specific eruptive pulse was in both cases for the event that occurred at 1:15 p.m. on April 19 with 8 minutes, and in Titan with 9 minutes. The different approach that the cause have to friction, viscosity, and cohesion. So, would you like to be in contact with the New Millennium Institute? We will be happy to collaborate with you, and thank you.
Thank you. We have time for one quick question. Tommaso.
Very nice work. Thank you for the presentation. Two quick questions. I haven't caught or understood maybe. So the first question is about the source mechanism, if it's just collapse of a source or if there is an inlet velocity or something like that. And the second question is, there is a nice paper by Karim Khelfoun a few years ago about the impact of the rheological model on the distribution of thickness along the propagation. And so I wanted to know if you have tested this on this amazing deposit at Lascar, which is really unique in the world, I would say, in terms of preservation and things like that.
Yep, thank you. I saw that paper of Karim. It was description of the, like you said, with rheological composition and description of the entire deposit. And the first question, my original idea was always made this model or this modeling with a approach in inversion model, because for that reason I visited to many points in deposit 55 for I have an idea or a complete idea of thicknesses in each section of around the volcano. So the source parameters or the inputs was chosen with the idea to complete the result with the deposit, the final deposit with the thickness measured in the work field, in the field work. Yeah. Thank you.
We can move to the next presentation by Pete Rowley. Channel edge effects in gas fluidized pyroclastic density currents.
Okay, hi everyone. So the last talk I gave was by a PhD student. It was a very nicely wrapped up piece of work that really went in the direction it wanted to. This project has not done this, and you might note the author list on this is a little bit different to the one in the abstract book, with the addition of an extra few names as I try to tie this story together. COVID got in the middle of this quite badly, and it's turned out to be quite a complicated set of things going on. But I'll take you through it and we'll see how we get on. So we're going to be looking at some experiments very similar to the ones we were looking at before. Exactly the same apparatus, but what we've started to do now is use polymech charges of multiple grain sizes to start to look at more natural, or perhaps the way more natural systems behave and fluidize and sediment. And I've talked a little bit about velocity profiles in the previous talk. This is just a quick animation to show you one of these very simple currents with in this case, we've got a slightly higher doping of large particles in here. We get a nice uniform velocity gradient running through it. And when we first started running these experiments, everything seemed to be running beautifully and everything's good and great and lovely. And similar with when we ran the single grain size experiments, as we started running with multiple grain sizes, we got the same kind of depositional patterns, we got the same kind of bed forms generating, but now we were starting to be able to maybe look at sorting behaviors. So this is a series of different, this is a single deposit with an interpretation underneath. We've got three different particle types in here. We have a white silica ballotini, all the fine materials we've talked about before, that kind of 65 to 90 micron material. We have a slightly larger, I think it's 100 or 200 micron orange particle to simulate pumices, large pumices in the current. And we also have a darker, large, dense particle to simulate the distribution of lithics. And we get some quite interesting little bed forms, but more importantly, when you start looking at it, we actually start getting grading situations. So we're getting a range of quite unusual, or unusual for these experiments, normal and inverse grading patterns. But that's not what I found weird about this image. What I found weird about this image is this deposit is supposedly having been put down by the same material. This is a single charge that was released from the hopper, flowed down the flume, and created this deposit. And it was uniformly mixed when it was released. But what you can see is the lower section appears to be completely absent of the orange and black particles. And that's quite weird. So the only explanation we could come up with for this is that essentially squeeze expulsion is happening. It's an effect where we have different grain sizes, you have a shear velocity occurring across a boundary, and the larger particles will get lifted away to then get filled by the finer particles. And the more extreme your velocity profile, the narrower your velocity profile and the higher the shear rate, the more able you will be to pluck out these large particles. And in that previous deposit, this lower region is laid by the first part of the current, which is much faster than the later parts of the current which deposit early on. So we have a much higher shear rate, and we remove those large particles. Now the problem becomes we start removing those large particles, and now we're changing the entire grain size distribution of the charge in different parts of the current. That starts changing how it fluidizes, which changes how it moves, which changes how it comes to a halt, which changes everything about how this current behaves. So this gas fluidization is getting absolutely chaotic. And the system we have in this flume for gas fluidization was designed, in a flume I built in 2012 for monomic charges. It's designed to provide a uniform gas flux. And once you start getting to changes in the mixture parameters, fluidizing the material becomes a problem. So essentially what we did was we started running experiments that didn't behave very well. And this beginning of exploration of grain size variance has also meant that now I've stopped trusting sidewall observations in flume experiments. And in these flume experiments, the sidewall is the only way I can see anything. So I started looking down on the experiments. So this is a frame of high-speed video looking at the top of the flow in the hope that I could start to understand maybe some of the processes that are going on. And one of the very cool things I noticed, which I've been running these experiments for years, it's the first time I'd really looked at the top of the current. And what we get is a whole series of really, really cool waveforms. And these, some of these get preserved in the final deposit, but a lot of them travel with the current and then get erased by the current as it's coming to a halt or getting overridden by further pulses of the current later on. But essentially we see two different things. We see quite long linear waveforms we've got here in red with fairly low sinuosity, and towards the flow front in the faster region of the flow we get these kind of shorter, coalescing, very sinuous waveforms. So these are quite cool, and I started thinking, well, maybe we can look at the velocities of these relative to the flow and start thinking about Froude numbers. And maybe I can also look at the velocity of these things relative to where the sidewall is and start quantifying the width of this sidewall effect. And what we find is that actually there is quite a strong sidewall effect at pretty much all times, and it spans usually something in the order of about 20 centimeters away from the sidewall. So our flume is 15 centimeters wide, it's 3 meters long. That's a fairly normal aspect ratio for these experiments. There's a lot of different flumes in the world, but they've all got the same kind of aspect ratio. And these sidewall effects I think there'd been a sort of thinking in the community once we started playing with fluidized granular flows that, oh, it's fine, we've got loads of gas in there, it's really mobile, it's an acrylic sidewall, the friction's going to be really minimal, we can probably ignore the sidewall effects. No, the sidewall effects are a big problem here. Now, that's pretty much as far as we can get with this. We've got a grant, we're going to be building some new equipment to start looking at essentially depositing these currents, setting them and sectioning them to actually really understand in 3 dimensions what's going on here. But a kind of cautionary tale that these sidewalls are a big problem for us. And particularly when you're starting to use mixed grain sizes. I think in monomic charges where you have a single grain size, it's less of a problem. But once you're into multiple grain sizes and you can pluck these larger particles away from the sidewall, we have problems. So in the nature of all good Monty Python scripts, when the plot reaches an impasse, we have an intermission and we move to something a little bit different, because I ain't on my 15 minutes yet. So, what we did is we had a look at these waveforms, these surface waves, and thought about them in terms of the wave velocities versus the flow velocities. And what we find is, as everyone else has said, these currents are supercritical 98% of the time. But this trend line, as you can see, starts trending back. You have to get to fairly low flow velocities, but we do start approaching a point where the wave velocity starts coming down to 0. So that means the wave is static in the tank. And that has to be defined by a Froude critical number. We need a Froude number of, or around about 1. And we can look at the properties of a generalized PDC and essentially work out what kind of flow thicknesses and flow velocities you need to achieve a critical flow in a PDC, and we can think about whether standing waves are actually a thing we might experience in the field. So this plot, very simply, is just a surface showing what the Froude number is for different flow velocities and flow thicknesses. And as you can see, there's this really narrow band. It doesn't really care about flow thickness too much, but we need to be less than 10 meters per second, which is a pretty slow PDC. So I think the lesson we can take from this is most PDCs are going to be supercritical, and if we do happen to find some standing waves in Ignimbrites, they're going to be quite unusual. This is the Pozzolana Rossi. Guido Giordano's group took us here when we told him we were looking for bed forms. He said, oh, I've got just the thing. And he brought us here. And what we can see here is a really unusual stack of beautiful, beautiful bed forms, which all stack one atop the other. All of the peaks are sat above the peaks. All of the troughs are sat above the troughs. This section's about 15 meters thick. You go around the corner, and so this top panel is a much smaller section that fits into the bottom left of the lower panel. But this car park provides a really nice 3D section. So the flow direction is going in towards those garages. So we've got the cross section again of the waveforms on the left. You can see they're stacking on top of one another. Lower in the section, that's actually not happening. So we have a supercritical flow, which then becomes critical, and we start building these standing wave bed forms on top of one another. And that's telling us that this current must have been metastable for certainly minutes, maybe hours, without any real pulsing happening. Above this, it then seems to go supercritical again. But we have standing waves in the field, which is a pretty nice find. But it is a little bit of a detour, and I was just adding that in because I had some time. So, sidewall effects in fluidized currents can be significant. particularly strong impacts on polymit currents. The sorting effects are probably going to change flow mobility quite substantially. And I do wonder if channelization is going to be as effective at concentrating flow energy as we think. Because as you channelize, you're going to be concentrating that center of the current with larger particles, which are going to defluidize more quickly. I think we need to be quite cautious about sidewall observations in flume experiments. Don't write abstracts before global pandemics. And extra bonus thing, standing waves are possible in dense granular flows, and their signature, although rare, does exist in the field. And that's me done.
Any question?
Actually, many dense granular flowing volcanology are channelized by themselves. So they have the side effect by nature. So sometimes it's useful to see the side effect on the channel because you have the natural channel doing the same job.
Yeah, I totally. Yeah, the dense currents I think are very often channelized, and seeing the sidewall is useful. I totally agree. What that does for the largest fraction of the material you're transporting, how representative the sidewall is of what your bulk current is doing, becomes problematic. But yeah, I agree.
Yeah,
So what was your initial purpose of having multiple grain sizes together?
So the aim of the grain size variation is essentially to see if we could start developing realistic ignimbrite sedimentologies. So could we generate reverse grading, normal grading, and flips between those sedimentation types as the energy and the current changed. So it was to start looking at sedimentology more deeply.
With the kinetic sieving you got and also what you expected to get, do you think there might be thresholds in velocities and volumes that might differentiate what's in the field with what's at the small scale?
Ooh, good question.
Because I've had experiments ruined by this, that's why I'm asking.
Yeah, no, so the scaling of these lab experiments is always going to be problematic because essentially we're dealing with the same material in the field, but we're missing 3-4 orders of magnitude of particle sizes. I think the biggest problem for these experiments is because the flow is so thin and it's very problematic to use the really fine-grained materials. The defluidization timescales on the currents are really quick. So everything wants to come to a halt a lot faster than really it should. And any kind of particle segregation enhances that and speeds it up in the flume. So I think we're going to be able to see real processes. I don't know, I think we're going to have to think quite carefully about the dimensional scaling of lengths and thicknesses and relative particle diameters. I think the scaling of it's going to be quite problematic. But as a first order idea of where do the large particles go, where do the dense particles go, I think there's scope for work.
Okay, thank you very much.
Yeah.
So I was just wondering the amplitudes of when you had this top view and the amplitudes of the waves close to the sidewalls, were they larger or were they smaller compared to the ones away from the sidewall?
The amplitudes I don't know. So this was shot with a single camera. We had oblique lighting so I could see where the waveforms are, but in terms of the amplitude of the waves, I don't know. We're going to go down the route of shooting photogrammetrically so we can actually capture these things in 3D, but we're not there yet.
Okay, thanks.
Okay, thank you, Pete.
Thank you.
We can move to the next presentation by Alessandra Penza. The lethal high temperature of early ash cloud surge entering the ancient city of Ercolanum during the 79 CE Vesuvius eruption.
Can you see the screen? And can you hear me?
Yeah.
Okay, perfect. Okay, thank you so much, and thank you for waiting for the last talk. I'm Alessandra Penza, and today I'm going to share with you our last research on temperature of ash cloud surges that oh, sorry. Just I'm trying to move this one. Okay, perfect. So I'm going to talk about the little high temperature of early ash cloud surges entering for first into the Herculaneum city during the 79 CE Vesuvius eruption. So I don't know why it's not working. Okay, that's it. As you know, ash cloud surges are among the most lethal volcanic phenomena, and they are highly turbulent and able to detach and move independently, even across rough topography, making their paths highly unpredictable. Ash cloud surges also are responsible, unfortunately, for some of the deadliest volcanic disasters, such as what occurred in St. Pierre in Martinique in 1902, or in Merapi volcano 2010, and more recently at Fuego Volcano de Guatemala in 2018, and at White Island in New Zealand 2019. Despite their dilute and turbulent nature that enhance the fast mixing with ambient air, ash clouds can maintain very high temperature as long as they are coupled with a high concentration basal flow, which is instead thermally conservative and continuously transfer upward both mass and thermal energy. This implies that if and where the detachment of the ash cloud surge occurs due to the topography effects, their initial temperature can be as high as the parental basal high concentration current. Once detached, we know the ash cloud surge are short-lived events which very often leave on the ground only a few centimeters of ash before lifting off. The little preservation of these deposits has led to a limited number of studies on such kind of deposit and phenomena, and also the small representativeness within the stratigraphy of such short events led also to the underestimation of ash cloud surges hazard, especially in terms of their thermal impact. Here, I just wanted to display two examples of Mount Unzen in Japan eruption in 1991 and at Fuego de Guatemala in 2018. And we can see that in the images with the car, the high concentration pyroclastic currents is confined within the Paleo Valley, while the oversplit of the ash cloud surge left just few centimeters on the ground, but having a huge impact for the temperature on the objects, such as here in the car. Instead, on the left, there is a video, hopefully that is working, about Volcán de Colima and Volcán de Fuego in Guatemala. And you can see that the ash cloud passage just left less than 1 meter of very fine ash, but despite the time after deposition, is still steaming. So the thermal transport is very high. To deepen such a relevant topic about ash cloud surges temperature, we choose two archaeological sites as Herculaneum and Pompeii as the most spectacular and famous historical cases of interaction between pyroclastic currents, settlements, and humans. Despite this eruption has been widely studied in different ways, still we don't know the exact timing and the causes of the death of inhabitants of Pompeii and Herculaneum, and still the communities of volcanological communities, archaeological and anthropological, are still debating about that. So we focus mainly our studies on the Herculaneum city, and as Pompeii, we know that Herculaneum was destroyed by a series of pyroclastic flows generated by the partial collapses of the Pineum column during the 24th and the 25th of August. And contrary to Pompeii, Herculaneum was not covered at the beginning by the first Plinian pumice fallout deposit, but was firstly hit by ash cloud surges that Sigurdsson et al. In 1985 and subsequently by Cioni et al. 1992 were identified and called as S1, S2, but we are just calling Ash cloud surge for not making the mistakes. And there are so many studies about the assessment of the emplacement temperature of pyroclastic flows at Herculaneum by using both thermal remanent magnetization of lithic-clast and also by the reflectance analysis of pieces of wood extracted from the deposit, and they infer a temperature and emplacement temperature about 350 and 400 degrees. But however, there are no studies on temperature of the poorly preserved ash cloud surges that firstly enter in the Herculaneum city and killed almost all people. As I said, the major part of the skeletons, unfortunately, were found within the Fornici chambers. I don't know if you can see the arrows here. That are the Fornici chambers where the Romans used to store boats. And this is because here is the shoreline, the waterfront where the sea was just reaching this point. Instead, this is the thickness of the pyroclastic deposit that buried completely the city after the collapse of the Plinian column. And so we are just here on where are the blue dots. So the corpse display lifelike posture due to the thermal induced damages on skulls and bones as an evidence of a very high heat exposure and a sudden death that has been approximately estimated 500 degrees by anthropological studies. This temperature is quite higher respect to the TRM reflectance data that we previously seen, but lately has been corroborated by the finding of vitrified brain fragments that we found at Collegium Augustalium, that is in the northern part here, where are the red dots, in a chamber where this guy was just lying on a bed, and the discovery of the vitrified brain fragments tell us about the evidence. It's an evidence about the existence of an early very high thermal event and the subsequent rapid cooling of the early ash cloud surge that occurred. We again try to test the reflectance analysis of charcoal to try to detect this very high temperature event, and also to assess the progressive burial temperature at Herculaneum city during the eruption. So what we did was to collect samples from furniture, from bed frames, support beams, and house beams. And in total, we could collect 40 samples of charred wood. For who is not familiar with reflectance analysis, the measure of reflectance is considered a very robust and constrained proxy for temperature at which the charcoal form. And usually this method has been widely applied as geothermometer in different carbonification contexts, especially in burial diagenetic environment, but lately has been used also for assessment of wild bushfires, natural and anthropogenic fires, and also volcanic environment. The standard treatment of reflectance data to retrieve paleotemperature consists in collecting from 50 to 100 measurements for each samples in order to have a good representativity, statistical representativity, and also to calculate the mean reflectance value is standard deviation. Here, just few images about how the charcoal looks like under the microscope, and the reflectance is the measure about this, the light that is reflected by these the fragments underneath, and this is then represented into a frequency histogram, and then the reflectance data is transformed into temperature data by using the different pyrolysis curves that are available in literature. And I just wanted to point out, without going into details, about the direct relationship between reflectance and temperature. So higher is the brightness, let's say, of the charcoal, higher is the temperature of burning. So we had a chance to test the validity of reflectance as a geothermometer in different volcanic environments, such as Fogo volcano, Merapi, Doña Juana volcano, and last at Colima volcano. In this last site in Mexico, reflectance analysis of charred tree burned by another ash cloud surge revealed the presence of both unimodal and polymodal data distribution that is indicating the capacity of charred wood to record multiple thermal events. And this is due to the not retrograde nature of the process of carbonification that records over time the maximum temperature experienced by the tree, the piece of wood, or also the furniture. This has a great importance in terms of timing of charring events, as the charred wood can record multiple pulses event, displaying in this way polymodal distribution of reflectance data. Therefore, we attribute the highest reflectance population values to the moment of the passage of the ash cloud surge as the highest thermal event experienced by the fragment, and the lower reflectance population as instead the moment of emplacement and the moment of the records of lower temperature. So based on this assumption, we apply the same idea for our charcoal reflectance data at Herculaneum, and as you can see, we had both unimodal and polymodal data distribution. And what we add to this research was that we didn't use only the average, the reflectance average, but we used the main modes and the average of the three maximum reflectance value to evaluate the maximum thermal event. In this way, as is summarized in this table, I'm not going to details for the time, but in this way, we could detect, in fact, the highest thermal event, especially in the northern part of the cities, where is the Comando Maximum and the Collegium Augustalium, and by using the highest values, reflectance values. And what we discovered, it was a range of temperature between 495 to 555 degrees. This range is perfectly in agreement with the temperature estimation made by the anthropological studies based on the damages of skulls and bones. Instead, for the rest of part of the cities, that is just from the center to close to the waterfront, the temperature are a little bit lower, but anyway are comparable and in perfect agreement with the theorem and reflectance analysis that have been mentioned before and suggested by the other studies. So just to summarize, what is the most likely scenario for the ash cloud surge at Herculaneum is probably that the ash cloud decoupled from its parental high concentration valley confined pyroclastic current just in the proximity of the city, and so that the ash cloud could form at very high temperature that could be close to 550 degrees, engulfing the city, and then just going downstream with respect to the northern part towards the waterfront. And exactly in the moment of the waterfront, Herculaneum has a cliff of more or less 5 meters, where the fornici are just here located, and before entering the sea, it reached the Fornici at a very high temperature, close to 500 degrees, and unfortunately killing instantaneously the people and then entering the sea. The interaction, as showing here in this video, of ash cloud surge and seawater caused the surge inflation and also the development of inward eddies that promote the settling of cooled ash immediately after the impact at Fornici. And this is the reason why along the pre-eruption beach we found a thicker S1 deposit respect to the outcrops within the city. This interpretation, so therefore, is an agreement with the stratigraphy findings and also with both anthropological and volcanological results. So in conclusion, by comparing the pyroclastic stratigraphy and the thermal stratigraphy recorded by the polynomial distribution of charcoal effectants, we can reconstruct the succession of PC events that impacted the city of Herculaneum. The first ash cloud surge entering Herculaneum city was very short, ephemeral, and reaching the coast at the Fornici chamber, that it was still at a higher temperature, close to 500 degrees, leaving almost no deposit, but killing all the people that were finding shelter there. Contrary to the zones exposed to very high dynamic pressure of high concentration and high velocity, the area impacted by short-lived detached ash cloud have potential for survival if the shelters have been constructed in a way to prevent infiltration of hot dusty gases. And finally, I think that the results of the study have an important implication for the mitigation of volcanic risk at Vesuvius volcano and possibly elsewhere. Thank you.
Thanks, Alessandra. Any question? Yeah, per Francesco.
I hope that I'll be so long. Didn't count it.
Hi, Alexandra. Piero Dellino. We need to be very clear about the terms of the temperature of the deposit. That's what we are measuring, the temperature of the ash cloud. And I think that you agree with me that when you mean that the ash cloud is diluted, it means that it entrained much air. So the air is cold. Yeah. So the air is cold and mixed with the hot gas. When the air is much more than the gas, the temperature of the cloud is low. But the particles maintain their more or less the original temperature. So when they are deposited, you are measuring the temperature of the deposit. But it's quite possible that the temperature of the cloud that can have a very low particle concentration is much lower than that. The problem is that if you are in the deposit, you feel very high the temperature. If you are in the cloud, you feel a completely different temperature. We need to be very clear about this, about the terminology. So the ash cloud could be lower temperature, but the material that is deposited for that can be very high temperature, which is something that is quite clear, for example, at Herculaneum. At Herculaneum, the massive flows has the same temperature of the deposit because they are very high concentration. At Vesuvius, the other part of the Pompeii eruptions have that the diluted part of the clouds is lower temperature, but always the temperature of the deposits is always something in between 300, 400 degrees. It's very useful to be clear on these things because it's quite useful this for risk assessment. As I was saying, against ash clouds, it's better to have good construction because they are not mechanically very strong, but be sure that you can prevent for being hit by the ash.
Thank you. I just want to, I didn't prepare a proper slide for this, but just to clarify this one. When we've been at Kolyma volcano, we collect samples of still standing trees from within the deposit where the pyroclastic flow hit the trees, and also the upper part where the flow didn't reach the maximum high. So what we saw is that even at higher height, let's say 3 meters that we could reach, here only the ash cloud hit the trees. So, and what we discovered also is that the burning of the ash cloud is very pellicular. So we collect just few millimeters from the let's say from the bark of the trees. And when I'm saying that charcoal can detect, is that doesn't need a lot of time for the wood to record the temperature, but in this case we try to do a kind of statistically thermal log from the bottom to the top to understand more or less the temperature of the ash cloud. And I agree with you that it's a mixing of cold air and the particles and other particles that are, you know, carrying the temperature, but you know, it's very transient, I can say, event. So at Herculaneum, all the skeletons were found within very few centimeters of ash, and these kind of events, they don't leave anything on the ground usually. And for this reason, all the temperatures that have been estimated after that on the deposit that were burying the skeletons were a little bit lower because they lost all the gases and all the gases that were inside the floor. And also, we don't, also there is this kind of mismatch instead with the damages of the bones that the anthropological studies they tell us. So what I'm saying is just that the polymodal distribution of charcoal can tell you exactly different moments of the passage of different flows and can detect the moment of the passage and also the moment of burying, because the difference is that during the passage you don't have a complete carbonification. Instead, when you're burying a tree, you have slowly the carbonification of all the fragments, and you can see differences between the bark and the inner place. Maybe too long.
Thank you very much, Alessandra, also for convening this session. Hope to see you soon.
Thank you so much to everyone.
And this is the end of this session. Thank you to everyone.
Bye. Thank you.
Your attention. You wanna? Maybe okay. We are late, but.
They can contact me anyway.
So
yeah.
You're free.
It's not for a question. No, it's not for a question. Sorry.
Okay.
Hi, Alessandra. This is Tommaso. I wanted to thank you and Matteo for the very nice session. And I want to make a small announcement. As a new member of the editorial board of the Bulletin of Volcanology, I really thank for this session. And I would encourage everyone to submit their paper on PDC on Bulletin. I will probably manage the papers on PDC in the next few years. So I promise to try to speed up the review process while keeping the very high quality of the review process that you have learned to
in this year and this responsibility. So I also want to remind that there is an open topical collection in Bulletin of Volcanology currently on pyroclastic density currents and benchmarking, and I invite you to contact myself or Andy Harris or Greg Valentine, who is the editor for this topical collection, if you want to submit to this collection. Thank you.
Thank you, Tommaso. Thank you to everyone. Bye.
So, good afternoon or good evening. So we are here now for the second part of the session, the combined session of unmanned robotic autonomous platforms, submarine volcanism, extant and extinct shallow submarine hydrothermal geobiology laboratories, and innovative and cutting-edge techniques for geological exploration. So the first talk will be by Sam Mitchell, and he will talk about pumice rafts and seafloor tephra deposits, tackling interpretative bias from analyzing microtextual data and sampling localities. It's yours.
Okay. Thank you everybody for coming to this talk today. So what I'm going to do is talk a bit about data sets that we've collected from a couple of recent submarine eruptions, but also talk a little bit more about bias around sampling and around the deposits and the data that we actually collect during submarine events. Because particularly for shallow systems, the deposits are submarine, but they are also subaerial. We've seen this in a number of recent eruptions, and that particularly comes in when we're talking about pumice rafts themselves. So just to give you a bit of an idea of some recent eruptions that have happened around the world that have produced what we call pumice rafts. So this is large amounts of pumice floating on the surface of the ocean, if you're not familiar with that term. Just a few to give you as an example. This was from 2019 along the Tonga Arc in Lataiki. Also Volcano F, that kind of area. We have the Havre 2012 eruption, which has produced one of the largest pumice rafts in recent times. There's the instance of floating pumice and lava balloons at Itagoro submarine volcano of El Hierro in the Canary Islands about 10 years ago. More recently in the news, we have Fukutoku Okunoba, which is a small submarine volcano in the Isu Arc off the coast of Japan. And this washed a large amount of pumice into the harbors and the ports of the Okinawa Islands and completely covered them. So this is an example of a submarine eruption that really had impact as a result of the pumice raft. And then, of course, much more recently, there was the Hunga Tonga Hunga Atapai eruption, which also produced a pumice raft, relatively small in comparison to the size of the explosion that actually occurred there. But all the same, it still produced pumice floating in the ocean. And in case you haven't quite seen that yet, basically these lighter areas that you see in these images indicate that those pumice clasts floating in the ocean. So like we say, pumice is produced during eruptions, but it's not exclusively at the sea surface. Some will float and some will also sink. So there's this complete separation of the material that makes it into the raft versus the material that ends upon the seafloor. And this is just a few examples of the material on the surface of the ocean, washing up onto beaches many weeks, months, even years later. But then a large amount of it ends up on the sea floor as well. So these are giant pumice blocks from the Havre 2012 eruption that was scattered at least 6 kilometers from source. And some of these are several meters in diameter. The largest one we physically saw was around 9 meters in size. And there's a whole range of, there's a whole lot of research that's been done into the physical nature of the blocks themselves. But I won't talk about that today. But because you get this separation of the eruptive products, there's a real problem that comes in when we talk about the submarine eruptive record, particularly when trying to look at things like key parameters that we talk about very frequently, mass eruption rate, plume height, because we have submarine plumes that also go above the surface. We saw that even in Hunga Tonga, the size of the eruption plume itself from a relatively shallow but still submarine volcano. Total eruptive volume, one of the key things that we use to classify and parameterize eruptions, is so difficult to constrain in the submarine environment. Tephra footprint, like I say, we have these submarine eruptions that produce tephra deposits on land and on islands around oceanic centers. And then magma production rates. When we're looking at a larger scale, the magma production rate of an entire arc or a particular region on the planet, all of these things rely on our estimates of total eruptive volume, mass eruption rates. All of these things we use to characterize and classify volcanoes over time. And so the first place we go to look at this is, of course, the material that we find during eruptions. But we need to make sure we're trying to couple both types of deposits. It's easier said than done, of course, because you have some very deep eruptions where it's very difficult to access the material. You have some instances where the pumice rafts just take the pumice thousands of kilometers from source, so you have no idea where it's even come from. And then for much older eruptions, if you go down to the historic record and look at a volcano that has, a thick sequence of pumice deposits in the wall, you have no idea how much of that eruption was removed by a pumice raft. It is so difficult to constrain active eruptive volumes for submarine deposits, and the amounts of volcanism that's created in our oceans, this is really a huge deficit to our field that we have a lot of difficulty constraining this. And so one thing we can do is we can, look in instances where we can compare what is in the raft and what is on the seafloor, and we can look at their textures, their geochemistry, try and match things up, and to see if we can get better ideas on, these eruptive parameters, air mass eruption rates, decompression rates, ascent rates of magma. And we can look at these things by doing a lot of chemistry and physical analysis as well. But this is an example from the 2012 Havre eruption where the raft and the seafloor pumice that was studied and produced around 70% within the raft and about 30% in seafloor pumice and effusive lava flows and lava domes. Pretty much everything had the same geochemistry, vesicle macro textures, density distributions of the class, so the porosity of the pumice being produced, and then the componentry within the deposits themselves. And yet some ended up in the raft and some ended up on the seafloor. So that's when we start looking at the micro textures. I know this is not a very physical volcanology kind of session, so we're just going to delve into that a little bit and then think about the broader picture of things. So one aspect that's really, really key for parameterizing pumice from submarine eruptions is this idea of connected porosity and how connected the pore networks are. So I've just got a small schematic diagram of basically a pore network within a pumice. The total amount of pore space is your total porosity. If you were to flood that sample with water, you have the connected porosity, which is shown in blue, and then you have isolated pores still in white. So those are pores that cannot be accessed by infiltrating water. And so you can look at something called the vesicle connectivity, which is simply the ratio of the connected porosity to the total. And what this basically tells us is how, when this pumice sample fills with water, will it actually float? Because there's enough isolated pores to keep it afloat because it's lower density than the water around it. Sometimes you can actually trap vapor inside the connected pores as well. That's more detailed work in some stuff I've done recently, and you can have a look at that if you want to. But for the purpose of this, we'll just think about connected versus isolated porosity. So this diagram here on the bottom right is illustrating basically that difference between pumice we found on the seafloor and pumice we found within the raft from the Havre 2012 eruption. This black line is a separation of floating versus sinking threshold. So if you are above that line, in theory, that pumice should sink. If you are below it, in theory, it should float. What you do notice is there's a lot of those orange dots for the rafted material that sits in the sinking region, and those can be accounted for by that vapor trapping within the pores, the connected pore space. But one thing that's really clear within this is there's actually a very big gap between these deposits. Oh, there is a pointer. There we go. There's a very large gap within this region here, and you'd expect for a single eruption where all of these other things are the same, so the macro textures, the geochemistry, the density, the componentry, you'd expect more of a smoother transition between these two units. And so that's something we'll explore in just a second. Another very key difference between these two types of deposits is the physical number of vesicles in a given volume, so your vesicle number density. So the seafloor deposits had much lower vesicle number density, around 10 to the 8 or somewhere within that order of magnitude. And then the rafted samples exclusively had much higher, up to an order of magnitude more vesicles within a given volume. So more smaller vesicles where the gas remained trapped or the water could not infiltrate itself. So we can see these really clear differences in the microtextures between these two types of deposits. And when we compare this on the global scale, the global data set of connectivity versus total porosity is not as clear as we would like it to be for more silicic deposits. So these are for all rhyolites. So all of the material that I've put now in the gray squares, this is all effusive material, rhyolite across the globe. And all of these crosses are filling in that data gap that we kind of saw earlier on here. This has been squished down because of a different porosity scale. So there should be, in theory, pumice within this gap that we see here. So the question is, why do we not see it in the deposits that we collected from Havre? And so one thing this comes down to is sampling locations. There is a lot of difficulty when it comes to submarine exploration. You're limited by your funds, the time you have, the contingency you have to do your days of science at sea. So it's not an easy thing to do at all. But just to give an example from this Havre eruption, the seafloor samples we collected were all within 6 kilometers from source. This is a 3D rendering, well, a backscatter rendering of the Havre caldera, the vent source here, and all of this rough region here is where a lot of the pumice was concentrated. But all of these clasts that we looked at were just less than 6 kilometers away from source. On the other hand, the pumice raft, which left the study area from Havre here and went all over the southwest Pacific, washed ashore in New South Wales and Tasmania, in Australia, all the way up to Samoa and Fiji. Say samples going all the way out here to Australia, and then up to Fiji, up to over 1,000 kilometers away. So the samples that I actually looked at for the work that I did, you just saw, were from Fiji beaches. So material that has been floating for up to a year and over 1,000 kilometers away. And so there's almost a bias in our actual sampling from taking the seafloor samples very, very close and the rafted very far away. And to kind of get this bias into perspective, we're essentially comparing the stuff that will sink the fastest and the stuff that will raft the longest without being able to study anything in between. And that's not necessarily our fault. That's just down to, the time and the money we have to do the submarine exploration, where we can physically ask someone to collect pumice from the beaches. And so we end up creating this region here. So I thought for a long time, okay, is this something to do with the eruptive dynamics? What's going on in the conduit? Are there two different eruptive styles happening during this eruption? But the more likelihood is this is just representing a field of all the material that's in between those two end members. And so there's a lot of characteristics of pumice that we may be missing out on by not looking at this field. So why does that actually matter? Well, potentially we're skewing our interpretations of these important parameters, things like mass eruption rates, decompression rates, total volumes, and also the general eruptive history of a volcano itself. And so that's why it's important for us to think about these things in terms of sampling. So we'll look very, very briefly at another eruption, one more recently. So this is the 2019 Lataiki eruption along the Tonga-Tofua Arc. So again, another pumice-producing eruption with seafloor deposits also sampled close to the site itself, but the pumice raft was actually sampled at a variety of locations. So this is just an example of where this is. 2 minutes left, thank you. So it's, again, on the Tofua Arc, north of New Zealand, and you have these samples that were collected very, very close to the volcano itself, and then there were raft samples collected in the earlier stages around the eruption. That's one key thing as well. If you collect sooner, you reduce that bias. And so that comes down to the need, of course, for more rapid response efforts in these things. They did some really interesting things along this cruise for them to get samples. Rather than a very large research vessel with lots of things on board, hundreds of thousands of dollars, potentially $1 million operations, it was a much smaller, low-cost surveying mission, which collected very similar data to what we got for the other eruption. For example, the samples they collected were using a sample grab off a smaller ship with GoPros attached to it, so reducing the need for a full ROV for the study. And so they didn't introduce a new type of surveying, but it's an example of how we can potentially look at some more rapid ways of collecting samples in this area. And so this is just another example now of the data from this 2019 eruption, the same diagram with the raft in the orange there and the light blue of the seafloor deposits and the Havre deposits shown underneath as well in the gray. So that area is still there. So there's still this field that we need to capture, and it's probably in the more medial to distal realm away from the volcanoes themselves. So it's highlighting this need for us to try and sample further away from these submarine volcanoes to build up a bigger picture of the eruptions themselves. Some of the limitations we have, like I say, a lack of reliable volume estimates, so uncertainty in the thickness of a pumice raft over time. We have very, very little data on how thick pumice rafts are and how that evolves over time. And that's how we calculate the volumes from these eruptions. We see the area very clearly from satellites, but the thickness to calculate that volume is a challenge. there's very little or even no evidence of rafts within the historic seafloor record. So when we go to these much older deposits, like we see over here on the right, you're only seeing the submarine component. You have no idea how much material was removed in a pumice raft, so it makes total volume estimates an underestimate. Very few studies have been able to couple both types of measurements. Harvey is an example of this from 2012, and the 2019 Tonga eruption is another example where we've just been able to couple those raft and seafloor volumes as well. Trying to do a better temporal and spatial resolution of sampling. There's very few sampling locations usually within a raft. This usually comes about at the very end when it's washing up ashore on beaches, as opposed to segmented over time within a raft itself. Proximal bias for seafloor deposits, like I've just said, it's more certain, we know what's happening, it's close to source, but the further away we get, the more potentially we fill in that bias field. And then, there's areas where we have unknown clast and deposit origins. That is one of the problems when you do go further away. There's no guarantee what you're sampling is from the volcano you want to sample. And so there's a lot of, ground truthing that you need to check on that. And then one of the biggest problems we have is the capacity of organizations and observatories to do all of this. Submarine exploration is incredibly expensive. So we need to see what we can do in the community to try and increase more rapid, low-cost surveying and response methods. And, there's ways that we can do this by collaborating, for example, in the recent Hunga Tonga eruption, where the Tonga Geological Services very much helped out by New Zealand, Australian authorities and the marine infrastructure that they have. So this is a really good example of how this can be done very well. But even still, there's plenty more volcanoes that desire our attention. I'm almost done. Yeah, I'm already over. Oh, okay. So this is a really, really nice diagram I just want to show, which was from Philip Brundle at Geomar, which is just showing, as an example, the number of volcanic centers on the Tofua Arc in Tonga and just how many recent eruptions there have been within this region, and just highlighting our need for more rapid, frequent, low-cost surveying and sampling. And so because I'm running over, I'm just going to put some of these solutions on this slide here. It's all very well for me to stand here, and talk about different solutions and frameworks that we can put in place in an idealistic situation. But for what we can actually do, one of the things we're hoping to do within the IFC Submarine Volcanism Commission is actually create more of a framework and network with technological partners, commercial partners, to be able to help us establish some of this. So this is an IFC conference, so I can put this in here as a little bit of a plug. But if you're interested in the Submarine Commission itself, I'll just leave some of that information here on view for a second, because there is more that we can do in this community to try and improve some of these biases that we may be creating, and to try and improve our surveying and sampling methods. So sorry about running over. Thank you.
So thank you, Sam. So if you have questions for Sam, later, please.
Alrighty, now we'd like to welcome Mr. Franco Villegas-Garin, PhD student at University of South Florida. He's going to be talking about UAS applications for enhancing the mapping, modeling, and hazard assessment of volcanic mass flows. It's a case study at Mount St. Helens.
Hi, how are you? Can you hear me?
Can hear you fine.
Great. All right, so let me see. Did double check before, but just making sure that you can see the screen right now.
Yep, see your screen,
Yep.
slides are up.
Great. Hi, how are you? My name is Franco. I'm a PhD student at the University of South Florida, and I will be presenting to you this research we put together, which is UAS applications for enhancing the mapping, modeling, and hazard assessments of volcanic mass flows, with a focus on Mount St. Helens as a case study. So I bet some of you that are in this room right now are well acquainted with UAS. Maybe some of you are here because you're curious about some of the uses of UAS within volcanology. So to give those that don't know much about it a little bit of an introduction, UAS stands for Unoccupied Aircraft Systems, also known as drones. And these have uses in hazard management for the past few decades, including volcanic monitoring and research. Originally, these were used for primarily monitoring volcanic plumes and active vents, but as optical sensors have improved over the last few years, we have began using them for photogrammetry, including structure from motion, which is a very common method of achieving this to capture three-dimensional maps of the Earth's surface, and therefore we can study a lot of volcanic features thanks to this. And it is important to mention too that other payloads have begun being implemented as of late, such as LiDAR, but that's still kind of new in terms of the drone realm, let's call it. So what are the advantages of using drones? One of the main ones is the quick deployment and portability. Given that you actually have a medium-sized drone, a lot of the drone products can be iterated daily, seasonal, yearly. And one of the great things is that you can achieve via photogrammetry georeference sub-meter pixel resolutions at pretty much any angle in a much more cost-efficient way compared to one-time purchase products. But of course, these products such as, let's say, Pleiades or Tandem X cover much larger swaths of land. So if you need more detail for specific areas, you can always implement drones to these specific areas to complement these larger data sets. And the other thing is they can also offer ground truth surface benchmark solutions for up and coming or novel remote sensing methods. We used a drone that's equipped with RTK, that stands for real-time kinematic, which increases the precision and the accuracy of the georeferencing, and it decreases the need for ground control points, which is extremely important as many of the areas that we do conduct research are sometimes very inaccessible. So I'm not going to go into detail in terms of the 1980 eruption of Mount St. Helens, as it's very near and dear to many of us, but I will point out that our area of testing was what you see here in yellow. So this stemmed from a sister project where we were analyzing, or we still are actually, ISRO data for eventually to be implemented as part of NISAR for NASA. And we were trying to find a way that we could validate and calibrate a lot of the results that we were getting from that. So the use of drones due to its high resolution was one of our first solutions, and it has worked out pretty well. And as we were capturing data, we realized that we could also evaluate the surface characteristics for a lot of these volcanic mass flows using this drone data. Initially, we started with things such as quite simple, just area, volume, aspect ratio, roughness, to mention a few. And to go into a little more detail about what I mentioned in terms of photogrammetry, we were using structure from motion. This is three-dimensional photogrammetry where you have a perpendicular, well, in our case, you can also have a one pass, but in our case, we did a perpendicular two pass flight with the drone in order to attain better resolution and less distortion of a lot of these features. And we conducted this in three areas, one for lahars, one for debris avalanche, and then one for a specific hummock, just then closer up in order to see what we could achieve with this. We used a software called Agisoft Metashape in order to create initially a sparse point cloud. Then we cleaned this up going through different filters, then a dense point cloud, and all the way down to actually generating a DM and an orthomosaic to look at these features. And our first target area was this debris avalanche section zone, where thanks to the high resolution of the drone, we were able to identify 41 hummocks, achieve a DM of about 5 centimeters, and then a tau model, an orthomosaic of half of that. Our initial measurements included these perimeters, areas, volumes, and then the axes for each of these hummocks, which you can see many of them have very irregular shapes. And thanks to this higher resolution, we were able to achieve greater detail, and we were able to observe a lot of the trends, even though we're in a pretty constrained and dense area in terms of the amount of hummocks that you could find there. And it also offered a better way to assess these volumes as opposed to relying on previous methods, such as just using the slope and the intercept and kind of estimating this volume of this irregular shape. Thanks to the software, we're able to accurately do this. And once we looked at the ratios between the surface area divided by the volume, we were able to see a clear distribution of these, where you had, for smaller areas, you had smaller volumes, and this basically decreased with distance and gave some insight into the flow mechanisms controlling the size of these hummocks as you move away from the summit of the volcano. Additionally, we were, thanks to the long axes of each of these hummocks, we were able to assess the general flow direction in more detail. We found that not in every case, but in many cases, those with a longer axis tended to basically sway towards a certain direction, while the ones with shorter axes, therefore they were less elongated, were going on slightly on a different direction. And this maybe gives a little bit of insight into some of the kinematics going on that locality specifically. But unfortunately, our fit wasn't nearly as good as it was for the previous slide that I showed you. So we definitely have to analyze a larger area for these. But we were able to assess a mean orientation for these flows, where it was west-northwest at about like 287 degrees. And looking back to classic studies, such as that of Glickens that he conducted, well, even though, it was published in the mid-90s, it was conducted mostly in the mid-80s, where he identified pretty much every single hummock here. But as we zoomed into these areas, obviously doing this by foot was much, much harder to do. With the drone, we're able to get a better perspective thanks to things such as the TAO model. We can zoom in and kind of change the perspective and be able to identify a lot more hummocks. And we saw that the orientation of these long axes was mostly in agreement with ours. So this is good news for us and what we're trying to achieve with this drone. Then moving on to our second target, which was Lahars, we were able to identify different types of channels, about a 5-centimeter DM once again. Very high resolution, but we ran into the issue that besides areas, we couldn't do much more with it as there's a temporal constraint on this. We don't know how much these channels are really changing. I mean, you can see on the picture on the bottom corner, on the bottom left corner, that even that active channel has shifted in comparison to just a base map from a couple of years ago. So the good news about this is that we could use this as a time series, and this might be useful to investigate these flow variations and its related dynamics between the dry and wet periods, or even when lahars take place, in order to use them for flooding hazard assessment, especially for the nearby villages and towns from downstream from the Turul River. And then the other great thing about them is that because of this high resolution, we're able to observe a lot of the blocks that were deposited here. So we could definitely do something along the lines of a block size distribution or componentry. And then finally, moving on to our third target, we ended up zooming in into one specific hummock. We were able to achieve about 1.5 centimeters per pixel. And I mean, that orthomosaic is on the millimeter range, which is crazy. But we ended up basically creating profiles for some of these hummocks, and we saw that because of this greater resolution, we were able to achieve much more accurate profiles for a much more accurate profile for this one, of course. But then we had the idea that we could come back here for something along the lines of internal grain size distribution or componentry once again. But since then, we have applied a lot of these methods to other volcanoes, and they kind of have evolved. So we're going to have an even better resolution when we come back here, as we're planning to do, in order to better assess these parameters. And finally, the last part of this was this ASAR-ISRO validation and calibration, where we were comparing this drone data versus this ASAR data. And in this case, ASAR stands for the A stands for airborne. And we were trying to see if we could get to begin with an initial match between the drone data and the backscatter, but as you can see here on this left-hand corner, it wasn't too good to say the least. I mean, the drone data looked great, of course, but then as a result, we ended up developing this in-house software in order to generate basically a roughness model from this ASAR data. And we found that as we increase the window of analysis of this roughness to be processed from this ASAR data, we were able to achieve a closer match to how the drone actually looks like. So this is great news, as we were trying to use the drone itself as a method of benchmarking, and so far it seems like we're going on the right direction with this. So if you want to see more about that in terms of the whole ASAR-ISRO, there was another talk focusing on that just did a quick mention to the drone stuff that I was just talking about here. Unfortunately, it's going on at the same time, so I hope some of these are recorded in case you are interested in seeing that. So as a conclusion, the application of these UAS structure from motion studies really gives insight into the kinematics and dynamics of some of these volcanic mass flows, or at least it seems to be quite promising so far. And due to this high resolution, which can be exploited, as you can see, as you saw in many ways, and we already have new ideas on how to implement this further, especially in terms of analyzing, for example, the spacing between a lot of these hummocks and things of the such. So definitely further studies on componentry, grade size distribution, and the heterogeneity of the area versus volume ratios would give us a better idea of the flow behaviors taking place here. The detailed long axis orientations will, if we go back and basically cover a larger swath, we'll be able to really follow those orientations at a long scale and basically get a better idea of a lot of these effects that it might have if, well, we'll say if it were to occur again. Data is great, but I don't want anyone to suffer because of it. In terms of hazard assessment applications, and then LAHARs have the potential, but they have to be studied as a time series. So besides this, also UAS, when coupled with this RTK georeferencing, as it is a lot more precise, it is a reliable method of ground truth surface benchmark for other up and coming remote sensing methods, or even well-established ones, since it does also offer this higher resolution. We saw that there's a progressive increase of the fitness between this UAS generated DEM but only when you have large enough windows of this roughness generated from the backscattering of the ASAR-ISRO data sets. Now, it is important to mention that you cannot go too big as then
Franco, we're running a bit short on time.
yep.
Thank you.
Yep, and I'm gonna finish right now. So what's next? We're just trying to go back there and cover larger swaths and note temporal changes, and then the application of this these studies to other volcanic mass flows such as PDCs. And that's the end of my presentation. Thank you.
Okay, thank you very much.
I think we don't have time for a question.
No, we don't.
So, sorry, but thank
No
you for
worries.
the talk. And we will
Thank you.
proceed now with Jean-Marie Privat. And his talk will be a review of island building eruptions and their frequency.
Okay, good afternoon. So this is just a small project that I've been working on just to keep my brain busy after the end of a postdoc position. So I guess I should have added a logo of the French Unemployment Office, which was my affiliation at the time of this project. So the idea for this project came by reading this paper, Fire and Water, by Peter Francis, published in Geology Today in 1995, where it tells the tale of the Ferdinandea eruption, which built an island off the coast of Sicily in 1831. And it begins the article by this statement: once or twice in a century, a new volcanic island is born. And when I first read that, my reaction was, wow, is it really that frequent? I thought it was a lot. So I decided to have a look at the literature to see if there was any compilation of island building eruption. And I couldn't find one. But the more I looked and the more I kept finding such eruptions, so I decided to build my own little data set of such eruptions. So the method was basically just going through the literature to try to compile every historical accounts of island building eruption, and then gather as much information as I could find, like the location of the island, its date of birth and death in many cases, its dimensions, etc. And then I used this data to plot frequency diagrams of island building eruptions. And finally, I also used this data to derive some secondary parameters, such as the lifespan of the islands, construction and erosion rates. This last part is still a work in progress, so I won't be talking about it today. Just a few selection criteria to know what I'm talking about exactly here. So in case if the magma source was not below the water, I did not include the island. For instance, this small island was built during the Lower Puna eruption in 2018 off the coast of Hawaii, but it was not fed by a submarine volcanic system, but rather by a lava tube entering the sea. So I did not include this kind of island in the data set. Mud volcanoes were also excluded. This is an example of an island born off the coast of Pakistan in 2013, triggered by an earthquake. And I did not include this kind of island also. I chose to focus on oceanic settings, so I removed, I think, 3 islands which were born in lakes, 2 in tall volcanoes like this one, and 1, I believe, in Vanuatu. And finally, I chose to include islands which were born as islands, but then were attached to land after growing. So this is a famous example, Capelinos eruption in 1957, which was born as an island, but then grew enough to get connected to the main island of Fayal here. I also distinguished islands and eruptions. So you have some eruption that can give birth to several islands, either successively. Again, Capelinos is an example of that. You had the first island, which was born and then lasted for a few weeks before being submerged back into the ocean. And then another island was born, and it's the one that is still alive today. So in this case, you have one eruption but two islands. And in some cases, you have, during the same eruption, several islands born from different vents. Sodze is a good example of this. There were actually 3 islands built during the Sodze eruption, but only one has survived. So in this case, you have one eruption, but 3 islands at the end. And of course, a submarine volcano can give birth to an island several times during the centuries. You have an island which is born and then submerged, and a few years or decades later, you have another island born from the same volcano. So this is what the data set looks like for now. So you have like the island name, volcano name and number, the date at which the island appeared, the date at which it disappeared. And from these dates, I can calculate the lifespan of the island if it disappeared, or the life to this date if it's still alive. And these are the morphological parameters that I'm still in the process of gathering from the literature. So since 1720, there has been, at least, I don't pretend that I have found all of them, but I have managed to record 48 island building eruptions from 25 different volcanoes, and they built a total of 63 islands. I chose to start at the beginning of the 18th century because this is where the records begin to get reliable. You have like ship's captains' logs and stuff like that, which are reliable sources. Before that, there are some records of island building eruption, but they are not so reliable, and they are more like legends or stuff like that. So if we plot this data on this diagram of eruptions per century, so you can see there were 5 island building eruption in the 18th century, and then 9 in the 19th century, 26 in the 20th century, and already 8 in the 21st century, which yields an extrapolated number of possibly up to 36 eruptions per century. This is the same data on a cumulative plot. So starting here in 1720, you have the first eruption, and then another one, and then another one, etc. So you can see that things are pretty calm up to the beginning of the 20th century, where the trend begins to really increase exponentially. And this is the exponential fit. So of course, this does not mean that island building eruptions are more and more frequent. This is just a bias because we missed the record from the previous centuries. Actually, the trend is very similar to the global volcanic activity, where you can see this apparent rise in volcanic activity, which is due to factors like the Earth exploration, population growth, and technological advances, allowing us to detect and report more and more eruptions thanks to planes and satellites, etc. So some result about lifespan of these islands. So of these 63, 45 have disappeared, and 18 still exist as of today. I've been able to calculate the lifespan of 32 of these 45. For the other, I miss most of the time the date of disappearance, so I was not able to calculate the lifespan. But for the 42 islands, you can see that the vast majority did not make it past the first year here. A few of them managed to live for a few years, and a few of them managed to live for a few decades before disappearing into the sea. Still have some time left, so I'm gonna show you a few selection of this eruption. So the oldest eruption in this data set is the Don João de Castro Simunt eruption in 1720. The island lasted only for a few months. So now, today, the seamount is about 20 meters below the surface. I think it still has some submarine eruptions, but not reaching the surface. The oldest island still alive in the dataset is Egoya Tufcon, which was built as an island but is not connected to the main Jan Mayen island here, which is almost 300 years old now. The most recent was the Fukutoku Okanoba eruption in 2021, which built this island here, which disappeared a few months later. And the newest island still alive is also in Japan, is the Niijima Island, which was born 9 years ago. Yeah. Here is a picture while it was still a baby, but since then it has grown a lot, and it's now connected to the bigger island here on the left. The most productive eruption, still in Japan, it's in the Aira caldera. There was an eruption which built 9 islands at 9 separate vents over a year. And the coolest eruption to me is the Unga Apai 2015 eruption. So there were these 2 old pre-existing islands here and here. And the eruption built a 3rd island in the middle, which eventually grew enough to connect both old islands. So this is an island building eruption which actually resulted in there being 1 less island in the world. So I thought it was pretty cool. Okay, this is just a quick summary of what I've just said. So they are actually quite frequent. 26 during the 20th century, sorry. And but they don't last for long, which is why we missed most of them during the previous centuries. Thank you.
Thank you. We have time for questions. Doesn't matter.
So supposedly most island volcanoes at some point started as islands like the ones you're describing, those that are still around. What's your thought about using minimum ages where known? We probably don't know the age that they were penetrating through the ocean surface, to see if there's some pattern there on that very long-term record that might show some similar characteristics in terms of data trends as what you're showing now, not in terms of magnitude of time, but maybe in terms of distribution. I haven't been thinking about that. What's your thought about that?
About the distribution of islands over?
Well, I'm just thinking there's a lot of ocean islands and ocean island arcs that at some point were meeting those criteria, and they're still around. So there's a large data set out there where we don't have the exact age when they penetrated the ocean surface, but we have at least minimum ages on some of them. Mm-hmm. So I'm wondering what your thoughts are on the value of doing that, or what, a lot of that data might be out there already.
Yeah, like I said, it was just like a little fun project to keep me busy. So
well,
I don't know if it has any scientific value
while
to the
looking for
community.
a job, this might keep you more busy.
But yeah, well, what I'm really interested in doing right now is like looking at building rates and erosion rates and also at why some of them survive while others disappear. I already have some hints, like obviously island built only of tephra tends to disappear rather quickly, but if you have some lava effusion at the surface, then you begin to have a layer of more consolidated rock that can keep the island alive. Then I think there is the tough palagotinization or something like this that can happen. Like at Sortze, they calculated that the island is gonna last a few more centuries because the alteration of the tuff makes it much more indurated. I don't know if I'm answering your question. Sorry.
No, this is all great. I'm
just
wondering if you can tease out information out of these data that help us understand what makes ocean islands survive longer term or disappear.
Yeah.
And so
yeah,
that's
a key question that I would like to answer. Like, what is the frontier between collapse back into the sea or survive and eventually grow to a full oceanic island? Yeah.
Cool. More questions or? Okay.
Thank you.
Thank you.
Alrighty, and then for the last, yeah. Now we're going to hear about Santori, not Suntory, unfortunately, but Santori.
Santori. Yeah, the name is Santori, but it's okay.
The Santori Seafloor Volcanic Observatory. Take it away, Professor.
Okay. So can I go? Oh, okay. No, it's no. Try. Okay, so thanks. So we're going to talk about Columbo, a submarine volcano just at the northeastern part of Santorini. And to tell you the truth, it was a small island that it was lasted only for a few days, and then it was disappeared in 6050 AD. So we are going to, that will be for the first time, this is the name of the project. It is funded by the Greek government, that we are going to deploy some instruments within the Columbo in order to monitor, not in real time. I'm going to show you which kind of instruments we are going to deploy. We hope to deploy the instruments in September, this September 2022, and then we will recover the instruments every 3 months. We will take the data and then we will deploy the instruments again. So something about South Aegean Sea. This is the synthetic topographic map, as you can see towards here. Okay, here is Methana. This is the peninsula of Methana. We have Milos, and at Dimilos, of course, Santorini. Here is Santorini. Here is the Columbo at the northeastern part of Santorini, and at the eastern part of volcanic arc, we have Yali and Nisiros. But except of onshore volcanoes, we have also submarine volcanoes very close to the onshore volcanoes. Okay, so these are some maps, just a few words. This is the submarine volcanic cones that we have found at the northwestern part of Methana Peninsula. All of them are inactive here in Methana. Here is Milos. This is very active. I will tell more about Milos submarine field tomorrow. This is in Paleochori, and of course in Nisiros there are lots of craters around Nisiros, but all of them are inactive, so we didn't find any gases on the seafloor. We're talking about Santorini, the famous island here in Santorini. So the most active part of Santorini is at the northeastern part. So except of Columbo, here is Columbo. This is a huge hole. Okay, on the seafloor we have lots of active fault zones, and one of the major destructive earthquakes was occurred in 1956. Here, this is the Amorgos fault zone here, okay, that caused a lot of damages in Santorini. So, in the neighborhood of Columbo, except of landslide, we have landslides, we have tsunami that was created from this eruption, but also we have lots of earthquakes in the area of Columbo. So, for us, this is the most important submarine eruption that we have in the South Aegean Sea, and of course in the Eastern Mediterranean, because we had fatalities in Santorini. So, 70 people were killed due to the fact that we have poisonous gases, and of course we had also tsunami with a height of almost 12 meters at the eastern part of Santorini. And that's why we will monitor this volcano, because we know that this is a very dangerous volcano. Okay, this is we published lots of papers with the University of Rhode Island, with Stephen Curry. So this is the eruptive model. So everything's starting from the seafloor, okay, and then we have the accumulation of the cone here, and then we have the subaerial eruption. But a year before, the people that they were living in Santorini, they felt lots of earthquakes. Okay, so then suddenly in September, to 29th of September, 1650, we had also the submarine eruption. Also here, okay, so we had lots of seismic profiles around Santorini in 2006, 2010, 2019, and so on, so on. So except of the last eruption of Kolumbo, this on the red color, we have found other eruptions. And we hope that now, with the IODP that we are going to drill here at the western part of Kolumbo, we are going to have more data about the latest eruptions of Kolumbo. So this is the swath map using AUV data. We did AUV mapping in 2017 on board Poseidon, and this is the diameter of Kolumbo is about approximately 2 kilometers. The depth is 500 meters, and the shallowest part is 18 meters. So in the AUV data, you can see lots of large rhyolite pumice scattered on the seafloor around Kolumbo, but the most interesting part is here. These are the remnants of maybe an older caldera. So this is a very detailed bathymetric map using AUV data. You can see that, okay, there are two parts, okay, of Kolumbo internal slopes. There are some parts, all of them are vertical, okay, but there are some smooth areas, and there are some other parts that they are very, you can see lava dikes, and we know that because we have diked there with ROVs, and we figure out that all of this part is full of pumice, different layers of pumice. These pumice have been erupting in 6050, as we can see also in this photo, and the rest of the rough areas are lavas. Okay, here and here, lava dikes. And also, just in the middle, and this is the most important thing for us, this we have found a hydrothermal vent field that it's full. This is a more detailed map using also the multi-beam system of the ROV. This is with a resolution of 0.5 meters. So we have found more than 110 chimneys that they are degassing at the depth of 500 meters. So all the crater floor is covered by this radius material. These are bacteria. Okay, so on these holes, the temperature is almost 70 Celsius at the depth of 500 meters, and you can see that the chimneys are degassing, and all the gases are CO2, 99% of CO2. So this is the reason why we will be there, in order to take more samples, more fluids, more gases, also from this very active volcano. For curiosity, we named that as Champagne, because it was degassing all the time that we were there exploring the crater floor using ROV. And also that we have found lots of chimneys. This is the largest one, with almost 4 meters height at the northern part. And of course, there are some videos. Click here. This is how it looks like, the crater floor of Kolumbo, full of degassing. So we used ROVs, but also submersibles in order to dive there. And we will be back in September to deploy instruments very close to the vent field. So this is the reason. Also, we have taken lots of, as I said before, on board Nautilus in 2010, 2011, we have taken gas samples, gases and fluids. As I said before, 99% of CO2, and of course we have many radios of helium in these fluids. So, for all these reasons, because also Kolumbo is very close to Santorini, of course, just only 7 kilometers, so you can imagine that you have a submarine volcano, very, very active, just 7 kilometers northeast of Santorini, not at the depth of 3,000 meters, not nowhere in Pacific Ocean, okay, but very close to a very touristic island. So for all these reasons, due to the fact also for its location and its importance, okay, from many different aspects from physical points of view, from geochemical point of view, from geological point of view. We submitted a proposal in order to monitor this volcano. So all of these are the objectives, and that's why it was funded. And now we are going to deploy some instruments within the Columbo. So it's, for us, it's a physical laboratory due to the fact that it's very easy to go there. It's not far away. It's not in the middle of the ocean. Okay, it has high probability for magmatic. So as I said before, in this area there are lots of earthquakes, not only due to the fact that we have a submarine volcano, but there are lots of active faults around. We have high potential of CO2, also the acidification hazard, and of course all these chimneys are made by sulfide and sulfate hydrothermal chimneys. And of course we need also to warn the people and to make them know the existence, except of the existence of Columbo, but if something happens, to inform the people earlier. So we are going to install, for example, lots of optical cameras, optical and high hyperspectral imaging sensors. We will put them very close to the chimneys, and they will record all the activity of the chimneys. And also in collaboration with INGV, we will deploy a new generation of automated geochemical recording system for all the gases that they are dissolved. And also we are going to have more samples from fluids and gases, and we will also take the samplers and go back to the laboratories to analyze all of the gases. We will also deploy some low-high temperature sensors in collaboration with ENS from France. And of course, we will deploy bottom pressure gauges and altimeters, because we do know that if something will change in the magmatic chamber, we will have some deformation on the seafloor. What we are not going to deploy, but we are in contact with Geomar, and we hope that we are going to have OBS, not in this cruise, but in the next cruises, in order to deploy OBS within the crater floor and outside of Columbo. And of course, that will be for the first time. We are going to have to measure radioactivity in the water column and also in the fluids and also on the sediments. So now with the Department of Physics, we are working on to have a prototype underwater gamma radiation spectrometer. So just to end, this is Sandori. So for us, this volcano, submarine volcano, it's very, very important, not only for the scientific purposes, but as I said before, we need to inform the people in order not to worry. And to tell you the truth, because I was born in Santorini when I was a child, most of the stories that the old people told us is not about Nea Kameni and Palea Kameni, not about this volcano. They would tell stories about Columbo, okay, about the 1650 eruption, and I do remember of my grandfather that said that we are not afraid of Nea Kameni. Okay, there is a volcano, but we do afraid about Columbo, because at that time the people, we have lots of historical references. So for 4 months they have seen, okay, the tremor, okay, the volcanic eruption just in front of their eyes. And at that time, they didn't know the existence of the submarine volcano. So we do hope that this Sandori will be connected also with other seafloor observatories all around the world. And that will be for the first time that we are going to have a shallow seafloor observatory very close in a very touristic area like Santorini. Okay, and that's it. I was on time. Yes? Yes. Okay, thanks. I was afraid of that. So I'm going to speak about Columbo. Okay, questions? I'm also a convener. And you are hungry, I know that. To dive, you can dive at the shallowest part at the 18 meters. Otherwise, you need submersible or the ROVs. I have dived with submersible. I have been up to 500 meters, very close to the chimneys. But the currents are very strong, are extremely strong, believe me, are very strong. No. You can dive at the 18th, and most of the The people of Santorini, they went there, they are going there in order to fish, okay, at the shallow part, not at the deepest part. Okay, yes, of course.
Have you seen anything interesting between Colombo and the northeast coast of Santorini?
No, because we have mapped the area also for the purposes of IODP. No, there are only some, not currents, like steps, small steps. All around Santorini, and so this is also a paper that we are working on, there are some step-like morphology all around Santorini. Okay, but nothing in particular, nothing interesting between Colombo and Santorini at the northeastern part.
The morphological code, which is obvious to exist at that corner of Santorini, is actually active, or?
It is very active. What I didn't say is that, I didn't mention that, and you are right, Colombo is in the line of Colombo line. So this is one of the most tectonically active area in Santorini. We have two tectonic areas, two tectonic lines, Colombo line and also Kameni line, okay, in the direction of northeast-southwest. And except for Colombo, we have also 25 submarine volcanoes at the northeastern part of Colombo, but all of them, there are some submarine volcanic cones, and all of them are inactive. We didn't find any gases, okay. So this, of course, this is a very active line, northeast-southwest. Yeah, not from you. No. Okay, come on.
Okay, so suppose you're done instrumenting it in the perfect instrument network, and you have an eruption of Colombo.
After 2023, okay, after February 2023, please.
Of course.
Stephanie is also here.
I'll set the timer. So then you would be at the start of a data gap at the time where you really need data. You were talking about the strong currents. Is there any plan you might have to have an outer shell of sensors or something at the coast of Santorini that will give you data when your core network is destroyed during an onset of eruption?
Okay, so in Santorini there are a lot of seismic stations and of course many GPS, okay, it's many GPS stations, so Santorini volcano is being monitored very accurately, okay, we know that. Okay, so if an eruption occurs, of course everything will be destroyed because you will be very close to the chimneys, so there's no way to be escaped, okay, to save some of the instruments, that's for sure. So the other, one of our dreams as a group, okay, is to have real-time monitoring. But for doing this, you need to have, except of the money, you need to connect all the instruments using cables, optical cables, like the axial C-mount, okay. But I think this is the future step. First, that was the first step, to buy the instruments and of course to have the crews and to deploy the instruments within the Colombo and start monitor this volcano every 3 months. So every 3 months we are going to recover the instruments, take the data and deploy the instruments again. Okay, but the future step, and we are working on some proposals, is to have real-time data, and we hope that if an eruption will occur, to save some of the data in the real time. And of course to have an observation institute in Santorini to collect all the data onshore and also offshore the environment, not only onshore, because now we are monitoring Santorini, but having only on-land stations, not offshore stations. Okay. Are we going to write a proposal together? Thanks. Absolutely. Okay, that's good. Okay, I like that. Yep. Sorry. Yeah.
Sorry. I read that last year in April there was a seismic movement around 4. Has been there activity like this recently or not yet?
Yeah, most of the time, as I said before, we have lots of earthquakes that are happening at the northeastern part of Santorini, but most of them are tectonics, due to the fact that you have lots of active fault zones in the area, and not due to the Colombo. Okay, so also it's very difficult to distinguish between volcanic tremor and also tectonic tremor, but most of them are tectonics.
Okay,
thank you. But we don't want to have earthquakes close to Colombo, okay? Yeah. We don't want.
Can you hand the mic over?
So you are not hungry, okay?
Thank
We
you.
can stay, because I was speaking very fast in order to finish. No. In Colombo.
Excuse me, can you see volcanic ash from Colombo on Santorini?
Yes, of course. Yes, of course. And we have published lots of papers. Not us, but tsunami deposits. We have found tsunami deposits at the eastern part of Santorini. Yes.
Oh, how thick?
How thick it was. If you dig, for example, in Perivolos and also in Agia Paraskevi, eastern part and the southern part, we dig about almost 1 meter, 90 centimeters, and then we found the tsunami deposits in a height of almost 1 meter, something like that. Something like that.
Thank you.
Yeah, there are lots. Only in the eastern part and the southern part, not within the caldera. We didn't find any tsunami deposits within the caldera.
Can you
from
see
Colombo.
in the field trip?
In the field trip. Yeah, difficult question. Yeah, we can try. We can try because we are going to stay very close to Perivolo, so we can go in an area that I can show you.
Thank you.
Yeah, that's good option to avoid the traffic. Okay.
Somebody's running away with the microphone. Do you have a name for your undersea observatory?
What? I didn't.
Do you have a name for your undersea observatory?
The name is Sandori.
Okay.
Okay, Sandori, most of the
project,
people are confused because we use Sandori from the name of Santorini, not Colombo. Okay, but we name as Sandori.
Okay.
This is the shallow seafloor observatory of Colombo.
Okay. So the observatory itself is the name, not the project.
No,
Okay.
it's also the project, but
Okay.
the project has exactly the same name with the
I
observatory.
cannot help but think of the Neptune project, of course, right?
Okay.
And you will certainly be better than that.
Okay, just to change the name. To have a new name.
But maybe, there's no Neptune 2.0, but maybe Poseidonis could be another name. But I like Santorini.
Okay.
It's
New suggestion. Okay, for me it's okay. I agree.
I like Santorini. It's not bad.
I agree. Okay, there's no question for that. Okay. So.
Okay, so I say no more questions.
You be tomorrow.
So I want to say thank you to all the speakers we had today and all the questions that came. And now enjoy your dinner.
Yes, of course. We have the plenary talk. No. We have the plenary talk. It's in the theater hall, and then we have the CAF commission, if I remember well. Not dinner. Sorry, guys.
I just want to briefly say, Effie, you did an amazing job with this conference. I just have to say that.